Hello, hello. Check 1, 2, 3, 4, 5. Hello.
Oh yeah, this works. Yeah, and the pen would be great.
Oh, okay. Actually, today we have exams. Do you have questions?
Yeah, I will give it to you later.
Okay.
I need three more. Okay. Is this the one? Yeah, okay. I can do it. Let me do it. Because I will also need some empty slides here for writing. Okay. Okay, so last day. I hope you are rested a little bit. I'm still sorry that I did yesterday I thought I have a half hour more for lecturing, and that I kept you away from lunch break so much. And so I promise today I have checked the schedule and I know how long I'm supposed to talk with you. And so I promise I will be in time. I think the microphone is gone again. It's not working. It was working until 2 seconds ago. Is it okay? Yes. Okay, good. So today you have two more lectures from me, and I would like to show you a few examples in two directions. So the first topic I would like to discuss is a little bit flow chemistry, and I would like to show you a few examples how that can be used and what might be really attractive in doing this. And then the second lecture today, I would like to discuss with you a synthesis which was done in pharmaceutical industry on large scale, but it was also done in academics a lot. There are many groups have developed a synthesis towards this molecule, and I would just like to discuss with you the synthesis and then simply compare and see maybe what considerations are when you develop something in an academic lab. And so that's probably your typical situation when you do something during a master and PhD thesis. But then if you would like to apply it in industry on scale, that then maybe there are factors you need to consider which you might not consider in an academic context. So let's start a little bit about flow chemistry, right? And flow chemistry became very attractive because it has this idea that you have your reactants as a reservoir, and then you, with pumps, and you dissolve your reactants, and then with pumps you pump it into a reactor, and the reaction takes place in that reactor, and then you remove it again. And so I'm not sure how much you have heard about this before, so let me see if you are still all with me. So what do you think is an advantage and what is a disadvantage? If you would like to say, rather, I'm not doing the chemistry in a flask, I use a flow apparatus and utilize the idea that I just have a reactor where my reagents flow through, and then I can do the reaction this way. And so let's just randomly collect maybe some thoughts about this, and then we can go through a few general considerations, and then I show you actually a few real applications in chemistry. So we have a new number, or again a QR code, whatever you would like to use. And let me see, it should work. Okay. So first idea is reactions might be faster than in a flask. And reaction speed indeed is a very critical parameter where I think we still need to improve in general a lot in. Because if we look at especially many of the academic reactions which are developed in academic laboratories, we read like 12 hours of reaction time, 24 hours, 48 hours. Sometimes 12 hours reaction time just might mean you go home in the evening and come back in the morning, right? Sometimes we don't know how fast the reaction is. But indeed, in many cases, a flow apparatus, a flow approach might improve yields, might improve the rate of the reaction. And indeed, one of the big issues people raise is that scalability is better, is easier, and especially one factor in the scalability. And I don't know if you ever ran a reaction in your lab, which you first do on, let's say, on a scale where you get 50 milligrams of your product, and then you do the reaction and you want to have 1 gram. And so then you might say, oh, I go and just make the reaction 20 times bigger, right? I use 20 times more solvent, I use 20 times more reagents and more substrates. But very often you find out that the reaction doesn't work so well any longer, because there are suddenly other factors, right? The heat dissipation might be different. For example, if you have an exothermic reaction, on the small scale you don't feel it because there's little heat which is evolving, but on a large scale suddenly that might dramatically change. And then especially if you then do the next step and go to 100 gram or even to kilo or ton, essentially it means that every time you try to scale up a batch reaction, you need to do a new optimization. And that can be very tedious and in many cases might not even work. And you all probably know when you submit papers these days, reviewers will always ask at least for a gram scale. We had recently a paper where we made 15 grams. We were very proud of us. And then the one reviewer said, 15 grams, this is not scale up. You need to do this on much bigger amounts. So it's a big consideration. And the nice thing about flow is that once you have a flow system running, all you need to do for scale up is just let it run longer. But concentrations are not changing, right? Because it's in your reactor, it has the same time, it has all the same concentration, it has the same energetic characteristics. And so from a scale up point of view, flow is not only offering that you can do a scale up, can run a larger reaction simply because maybe your flask is not long enough, but very important, the optimization to scale up a reaction is much better. Less reaction time, indeed. Safety is really a very important buzzword, and I show you reactions which definitely would be more problematic in a batch setting if you would from a safety point of view. Okay. Then the disadvantages. Also, some of you write something. Potential for clogging. Absolutely. Right? You have a tube reactor. You pump your reactions through. If for some reason you should have precipitation of a salt or whatever, it might clog your system, then you might have a real problem. And so clogging is a problem. Let's see. Another problem might be gases, which might evolve, right? And I nevertheless show you a reaction today which we ran where a gas is indeed formed. But of course, if you are in a closed system, when you have suddenly gas evolution, you build up pressure, right? And so but that is something one can handle. The one or two aspects nobody wrote for you here so far is it's probably more complicated to set it up, right? A flask, we take a flask out from our lab, just put the flask in the hood, reflux condenser, oil bath, add everything, and that's it. A flow apparatus usually is more complicated. First of all, you have to have the apparatus. You have to have pumps, which are pumping your reagents through. You need to do something about potential pressure upbuild. Very important. So you need something like a back pressure system which controls this. And when too much pressure is building up, then the flow rate needs to be reduced. And if that is to be done automatically, then you can also see it becomes more cost intensive, right? So there are a number of such issues. Of course, later, if you should work in an industrial company, very often cost considerations for equipment are much lower than everybody or some of you wrote, the reactions are faster. If you can speed up a process, and the most cost-intensive factor typically is the person who works on this, and not so much the equipment. So I have just put up some issues here, right? So typically you have a more complex setup as a negative here than just a flask. and pumps, valves, so you need a whole system, but I show you examples of this, that this might not be so complicated. Back pressure regulator. This is really important. This is this idea that if pressure builds up, then you need to have a feedback that the addition of your substrates needs to be slower in order to release the pressure, right? Extreme conditions. That is a very important thing. You can realize in a small reactor very high temperatures and very high pressures, and you expose your reactions only for a very short time. And that might be advantageous rather than heating in a batch for many hours your reagents, and then maybe you can, in the batch, you would do a lower temperature, but you speed up the reaction tremendously if you can apply high temperatures, but very often your products might not be stable to the high temperature. So high temperature, but very short residence time. This is the term people are using. The residence time is very important. Smaller reactors are possible, and you will see that this can be even nanoliters. Either can be really, really small reactors where you have very small, essentially a nano flask, you might say. And there also comes the safety issue into play, because if in your reactor the reaction takes place, but if the reactor is only nano or microliters or so big, then of course much less can happen, right? And so you have your starting solutions, but they are not in the moment reacting. They're only when you pump them in the reactor. But in difference, when you do it in a flask, you have everything in the flask already. And there's also, again, a cost consideration, because if you do a batch reaction, and let's say you do it on large scale, and let's say it's precious compounds, you have to add everything in your bed, in your flask, right, at the same time. And let's say something goes wrong, the electricity breaks down, so the heating goes down, or I don't know, you do a photoreaction and your lamp burns through or so. All your precious reagents are now already in your reaction flask, and they might be lost because you have an unforeseen event, right? Let's say even like your flask has a crack, or I don't know. In a batch reactor, you have your reservoir, and you commit only very small amounts at a time to the reaction. So in terms of something goes wrong, essentially only what is in your reactor is lost, but not the overall defeat you want to bring in. So this is like the lower risk of losing materials. Much better surface area to volume. This is especially important with photocatalysis. We discussed that when you shine lights into a reaction solution, that the light penetration might be only 1 millimeter into your flask. So what is the sense of having a big flask if the light is only only possible to reach the first millimeter of your compound? And so in a flow reactor, you can spread out, of course, your reaction solution, and this way essentially have a thin film or just a thin tubing, and so your light penetration might be much better. Okay, safety we discussed. We already discussed this. Typically, you can control reaction parameters better, and again, you only need to control it in a small volume in your reactor. The one thing which is pretty amazing in batch reactions is, don't know if you ever did it. So usually, how do we control temperature in a batch reaction? We have our flask, we have an oil bath, and then very often we measure the temperature in the oil bath, right? This is already the first thing which is essentially wrong, because the temperature in your oil bath is not the same like the temperature in your reaction flask. So there's already quite a big disconnect in this. Okay, so you can take an inside thermometer. That's typically the more accurate way to do it. But then if you especially have a large flask, your temperature in the middle of that flask might be different than the temperature on the sides. And we all know what we do. We stir rapidly. We try to stir this in order to have it homogenized. But again, if you're in a small reactor, it's much easier to keep your reaction parameters constant. Okay, so these are some general realization. Let me see if that works. I took, because I like this, and it's not working. I had a very nice video from the internet which shows like a, let me see if why is it not working? Because it's probably now got transferred to the computer here. Okay, let me see if I find it real quick again, because this was, what happened to the time when you could just open a browser and you would get and you would get the page. Let me see this. Let me see if I find it, because this was really nice. Oh God. Okay, let me see now. This was on YouTube, and this was done much nicer than I could do it because it was animated and everything. I wonder if I can see the URL which is behind this here. Okay, I'm afraid this would take too long now to find this back. I might add, oh no, here it is. Let's see if it works here.
Manufacturing chemical-based products is important to everyday life and plays a central role in the global economy. Combining chemicals with different properties and functions leads to
Not sure I
advanced
can get
products
this
in
louder,
areas like
but
medicine, food, textiles,
it will be very
and
short.
household products. Previously, classical batch chemistry has been simple and effective when discovering new materials. But using this method to scale up chemical production can be problematic. There can be issues with waste, for example, heat management, or even
what we have discussed, heat managing,
to cleaner, more
safety.
cost-effective chemical production is important.
But I wanted to show you what they show here
Manufacturing
just
in
as
Australia
a
and
general.
around the world. Flow chemistry is a smarter way of making chemicals. This is how it works. Pumps deliver chemicals to a reactor.
This is the first thing. You have feed tanks, but
continuous stream.
they are not mixed yet, right? And only when you bring it in the reactor, then you commit only a small fraction of your feed. And then also very importantly, very often you can run flow reactions in sequence. You do the first reaction, and then you see here in pink, you add the second reaction to a second reactor. And even the purification very often can be done automatically.
Provide much greater control over the
Here you have a schematic scheme, so you have your two tanks, and you then have to mix it. Very often you have a special mixer which mixes things very efficiently, and then you pump them through a tube, and this tubing system you can heat. What they do here, you can irradiate it, shine light on this, and do the chemistry there.
Because flow reactors operate continuously, making more products simply means running the operation for a longer time. Scaling up reactors is much simpler.
So here they give you two ideas. They say you can scale up either by what we discussed, letting it run the reaction longer, or use more than one reactor, use many reactors in parallel. And because the reactors are still small, this might again add to the cost, but it is also a safe way to scale things up, because again, you're not changing parameters. You use the parameters you have initially developed. Okay, so this is just as a small thing here. So let's talk about some more specific. Okay, this is not mine, right? No. Let's talk about a few more specific examples. And so the one example I showed you already, and I'm not going to discuss very much along, but we found that this rearrangement of this furfural alcohol to this hydroxycyclopentanone was a reaction which really benefited from flow, because one thing it clearly did is it reduced the side products, and the side products is something you can generate by eliminating this hydroxycyclopentanone under heat and acid conditions to the cyclopentadienone, and then it polymerizes. And the batch conditions called for heating up to 48 hours at 100 degrees. The flow conditions, we were able to do this at a much higher temperature, 240 degrees, and this way also a lot of pressure was building up in our system, but the exposure time was very, very short. So the components in the reactor were present for less than a minute, and that allowed us, and then they were out, you cool them down immediately, and this allowed us a high yield, very high purity, because we would simply suppress the back side reactions. And that is a reaction which by now has attracted various chemical companies who have used our protocol, and I show you actually how we do this in a moment. But they have much more sophisticated ways to do this. So in their case, this little box here, this is their flow reactor. And again, they can pump, they can cool it, they can heat it, and then they pump the reactions and you cannot see anything. Maybe here they pump the reactions through these little, through little tubings which you have here. We did this in a much more easier or much more low budget type of way. So again, this is the idea, right? You have a stream of two compounds. You have to have a mixture, so you don't want to just bring them together. In these mixtures, you again bring them through valves and mix the components efficiently, and then the mixed components then go into a tube reactor, which is essentially just a coil, and which you need to heat, and then hopefully out comes the product. And what we did is, our flow reactor was a GC oven. That was attractive because in a GC oven, 240 degrees, you heat your reactions to this all the time, right? You would not like to do it in an oil bath. This would probably give you a lot of fumes. And so we would simply use the GC oven, and our tube reactor was an empty GC coil. That's all we needed, an empty steel coil, and we used this and we connected the HPLC pumps to it and just pumped the reagents through this. And so again, if you have still an oven, and most of the labs have such ovens, and of course have coils which are not really being used, that's very, very easy and quickly to do. There are much more sophisticated things. So rather than having such coils, steel coils, for example, here is just an apparatus people have developed. It's a spinning disc reactor. So what they do here is they have the feeds, but then they have where the reactor takes place. It's actually not in a tubing that the mixing comes, because they have a very fast spinning, rotating disc, which essentially mixes their components. And then you can see they have different ways, different inlets. They have inlets for the substrates and for the reagents. And you see N-butyl lithium, usually a compound which we of course have to handle very carefully. You can use this in flow type systems. And you see they bring it in here, and then it comes to the spinning disc, it spins, it gets mixed very efficiently, and then goes from this to this, and at some point you can also quench your reaction automatically. And so here they feed in methanol to quench the butyl lithium and ultimately get out the product. Again, more sophisticated clearly, but again, very, very efficiently. And I'm going to show you a few examples, especially on handling of N-butyl lithium, which I think are quite impressive. So let me see, I think these are my empty slides I want to show. So let's look at a few reactions, at some real type chemistry. And one of one of the types of chemistry which has been developed is being called ultra-fast organolithium chemistry. And that is something which really impressed me, especially when in the earlier days of flow chemistry. And this is the chemistry which has been developed by Professor Yoshida from Japan. And he has shown that you can do organolithium chemistry really in a spectacular way. And so look at the reaction he's doing here. And he's doing multiple steps with organolithium reagents. You see here like with N-butyllithium. And so he's starting with a bromonitro, with a bromocyanoarene. And then by adding butyl lithium, he's doing a metal halogen exchange and makes the lithiated compound. And look at this, it gets mixed. It's done at minus 40 degrees, so also low temperature in flow can be very easily realized by putting it in an appropriate cooling bath. And then look at the contact time, 0.2 seconds. That's nothing, right? If you consider that typically we run reactions at least on a half-hour scale or so, 2 seconds, the lithiated compound has been produced, and then he's trapping this lithiated compound with this component here, which has an aldehyde and a ketone. And you probably all know that an aldehyde is more reactive than a ketone, so the reaction of the lithiated compound will take place on the aldehyde. Then he is getting this coupling product. And again, look at this, look at the reaction times. 7.2 seconds. That is, again, very, very short. And then he is starting to generate a second lithiated compound in the same way like he's doing the first one in yet another reactor. And so this time you have a nitro-iodo compound, N-butyllithium makes the lithiated compound, and then this again gets added to this compound here, where now the aryllithium will react with the ketone and form this product, right? And so what he is doing here is he's generating two reagents and is doing two reactions, right? So in a way it's 4 steps. The overall yield 61%, that's still very decent. And the overall reaction time in the longest sequence here is less than 15 seconds, right? That is very important. That's of course only exposure time. And now if he wants to do lots of this product, he of course has to pump in more reagents. So the overall reaction time is of course longer, but the time you need in order to have your compounds exposed to your reaction conditions are only in the second range. And I show you, I have a picture in a moment of some of these reactors he's using, and they're commercially available, and they're very, very small, they're very tiny, and so indeed that makes it not so expensive. Have a look here at these reaction conditions and the reaction. Besides the fact that we are very impressed, at least I'm very impressed, that you can do this chemistry in ultra short time, and if you would do it in a batch step by step, it would probably take much longer. But the question I would like to ask you, and this is the question I think I have here on the next one, so this is now, should be now possible to do this, and I showed you the reaction again. Would you be able to carry out, even if it takes longer, and the working time of students is essentially free, right, or more or less free, but could you even do the reaction in batch, right? What they can do here in flow, or would there be a problem in doing such a reaction step by step in batch? That would be my question here. So have a look here, and then you can answer hopefully here. If you would run that sequence in a batch setup, would that have worked? You see? I can see you're all confident with your ability, so you think, yes, I could do it. Have maybe a close look. What could be problematic to do this reaction in batch? No answers? I can see you guys are on strike. Give you a hint. Look at this first lithiated reagent which he's been making. Do you think that reagent is stable? So think how you would do it in batch. You would take your bromocyano compound and you would maybe take 10 grams of this, and then you would add 10 the equivalent of butyllithium, and you would form this, and this would take a certain time, and only then you would start adding your aldehyde. You see, the beauty here is, if you do this in the flow type reaction, it's enough, you use a tiny amount, you form this, and then you add essentially a few seconds later the next one. You don't need to wait if you do it in batch, you don't need to wait until you have made the lithiated component first and then add your aldehyde, right? So temperature variation in batch reactions is always harder to control temperature. But I think if you do it carefully, you can do it, right? You would do inside temperature measurements, you would add the butyllithium very slowly in order that you're not getting up the heat. I think that would be okay. And so if you would, for example, have made the phenyllithium from bromobenzene, I think you would have been absolutely okay. But you're making it here from para-cyano-bromobenzene. And a cyano group will react with a nucleophile, like an alkyl lithium or an aryl lithium. So you would have the problem that once you make this in batch, and it takes a certain time, that your aryl lithium compound would, with another of either of the starting material or already with the formed aryl lithium compound, the phenyllithium here, the phenylamine, would add to the cyano group. So you have a group, functional group incompatibility here. That is something we see very often in organic chemistry, and then especially in batch chemistry, that we have maybe certain functionalities in our reaction setup which are not compatible with each other. And that is the case here. So the phenyllithium would not be compatible with a cyano group. But in this flow approach, where you mix a small amount very fast for a very short time, and then bring your trapping reagent in there, that is a very good way to overcome such limitations. So that's another option, or another advantage of flow chemistry, is that functional groups which might not be compatible with each other might be okay simply because the exposure time, and then you add the next reaction, and an aldehyde is more reactive against the nucleophile than a cyano group. But you could not afford maybe to form over half an hour or so your lithiated compound. Okay, I don't know where this came from. Okay, and so the group of Yoshida has done this in many other variations. So if you look at this reaction here they're taking an alpha bromo ester, and they again do the lithiation, so they do the halogen lithium exchange on this position. And then in the next step, they're adding electrophiles. So they're generating the phenolithium here, and then they're adding something like methyl iodide. So they do the alkylation. And so I don't think I have to ask this again now, although I had prepared it. But you see, again, an example of functional groups which would not be compatible, because an aryllithium, an alkyl lithium compound, of course, is going to react with an ester group if you give it enough time to do so. So the one thing which is important to realize here, I would also like to mention, is such metal halogen exchanges, or exchanges from a second butyl lithium to a bromide. This is very fast. This is faster than the reaction with an aldehyde. So whenever you exchange halogens, this is very fast. But then if you give it time, the aryllithium, of course, will react with an ester group, right? And so again, he was able to show this here, that this is possible. So he takes the bromo compound, he takes butyl lithium, and then you see here you have these mixtures, and you see also the diameter in this mixture where you bring the two components together and where they get mixed, 250 micrometers. So we are talking really about very, very small amounts. And then the lithium-lithiated compound is formed. Residence time is overall is 2.24 seconds. And then because here now he's bringing in the electrophile, and the second mixture brings this in and is able to get the compounds. And again, a reaction which has a total residence time of 2.4 seconds. And you see, depending on the mixtures he's using, the diameters are very, 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 very small to do this. Okay, so again, can you send it? Then one thing which is also quite attractive is that you can run reactions in sequence. And here's an example of a Migishi coupling. And we said that if solids form, you might get clogging. That is absolutely okay. But you can, of course, use solid reagents. And then your tubing is different. You have like a bigger column fit or so. And there, of course, you can have heterogeneous or even solid reagents in there. And here's an example which shows both, because here you have a stoichiometric reagent, zinc, so you have activated zinc powder, and so you essentially push your reactions through the zinc powder, and you're forming from the benzyl bromide here, you're forming the zinc compound. And so here the zinc is reacting as a reagent, but then here in the second step you have a heterogeneous palladium on charcoal, which is doing the cross-coupling reaction. And so that is, of course, only a catalyst. And so again, of course, the clogging is important. You need to make sure that you don't have a powder which, once it becomes wet, it will not allow you to get this through. But I think here a palladium on silica was used, which is porous. We all know that when we do a column, we can push solvents through a silica column quite well. And that also, of course, works with flow, right? And so that was an example where they showed that you can do palladium-type cross-coupling chemistry quite nicely. And I'm not sure, yes, I could probably also ask you if this is would be possible in flow or not. See here, you're generating a benzylic zinc compound, and you do this in the presence of an ester group. I don't know how much you have heard about these organic zinc compounds. One of the advantages of the organic zinc compounds is they are not as reactive as Grignards. So if you would have tried to make a Grignard reagent here, instead of using zinc, using magnesium, you could not have done it probably, because you have the ester group here and it would react. The organozinc compounds are less reactive. That's one of the big advantages of the Migishi coupling. Migishi got the Nobel Prize for developing palladium couplings with these zinc reagents. And one of the big advantages is that the zinc reagents are less nucleophilic. It's a transition metal, it's not a main group metal, they are less ionic, and so therefore this would be compatible with an ester group. So this reaction you could carry out also in batch, but of course was nicely shown here that such couplings are possible in flow as well. And so again, here is one of these Yoshida papers, and here you actually see one of these reactors, and you can see it. You can put it in a hand. It's 2 by 2 centimeters, and it's only a few millimeters high. And in fact, this is a reactor which has an inside volume of nanoliters. So it's a really small. It's a really small inlet. And let's look at the reaction which he did here. That is a paper which made it into Science. So something must be really good here. And you see already the tagline here, sub-millisecond organic synthesis. And the question is that needed in this case or not? And he chose a reaction where he is generating with phenolithium, the lithiated compound here. And once you have this lithiated compound, there's a reaction which is called freeze rearrangement. This lithiated compound would like to transfer this group here, which is shown in red, this amide group, would like to transfer this very rapidly to your lithiated compound. So essentially you can think about that the anion attacks on the carbonyl group and then throws out the phenol, which is a really good leaving group, right? And so then you would transfer the amide group into your arene, and then you could trap the resulting O lithium with an electrophile. This is actually a very decent reaction to introduce carboxylic acid functionality, so carboxylic amides, into the ortho position of a phenol. So if you can go through the halogenated compound, if you would try to do this directly, it might be more challenging. But what he did here is, if the electrophile he is using is the chloroformate here, and so he was questioning if that electrophile could compete with the rearrangement if you make the reaction time, the exposure time, really short. So you generate the organolithium compounds, and then essentially immediately you add your electrophile to this. And so he has these type of reactors, and he has, in this paper, he has a little bit different types. But the important thing is, look at this here. So he's considering the volume of the reactor, and he makes it successively smaller. So in the end, he has only a volume of less than 1 microliter. And the residence time is also getting smaller and smaller. And see what happens if you have still, compared to batch chemistry, a tiny volume, 79 microliters. And you have an exposure, a residence time that the phenolithium and these two meet, and you make the lithiated compound before you add your electrophile. He has a residence time of 628 milliseconds. You could not do this even in batch, right? Because this is calculated, of course, by the flow intake of your reagents, and then you can calculate how long they must reside in your chamber. And you see here's how it's done, right? The first compound here, this compound goes in here, the phenolithium goes in here, and then essentially the electrophile comes in here, and then at that point you have everything mixed and the reaction can be done. And so even if the residence time is as short as well under a second, right? So you have 628 milliseconds, so that's about half a second. You still get exclusively the rearranged product. You cannot compete, the electrophile cannot compete with the intramolecular cyclization. But then if you go down with everything, you go down with your volume and you go down with the residence time, you see here now we are a factor of 20 lower, then it is possible to suppress the intramolecular reaction because you're offering your electrophile at a very short time after you have generated the phenolithium, and then suddenly you change the course of the reaction completely and you are indeed getting the electrophilic substitution, the electrophile introduced here without that the rearrangement is taking place. Right? And that is, I think, simply shows you that you can change normal reactivity, which we are all used to when we consider reactions, by fast mixing ultra short residence times in order to do this. Okay. So again, could you set up this reaction in batch up? We just said he shows us that even in the flow reactor, if you have very short reaction times, it's not possible. And so here's one more example where I could also ask you if you could do this. So again, they're making an aryl lithium compound, and then they reacted with a acid chloride to make a ketone. And of course, the danger is that this ketone might react again with the lithiated compound, which you form here, and instead forms the alcohol. Right? And we all know that normally when we react an organolithium compound or a gradient compound with an ester, we are not forming the ketone, because the ketone is more reactive than the ester, and then we are forming the alcohol. Here they might have been a little bit better off. Here they're using an acid chloride. So if you compare reactivity, you see what you're making here. Let's go just quickly back and just write a little bit. So when you have carbonyl reactivity, we are typically in the situation that the most reactive, and I will only put up a few, so the most reactive carbonyl compounds I don't know what's wrong with this. I'm not touching anything here. So the acid chlorides, most reactive, and I will only put up the components we are considering. We are considering here aldehydes, ketones, ester. So this is typically the reactivity against nucleophiles. And so if we go and have any type of carbonyl compound, and we hit this with a nucleophile, then there are two aspects to consider. The one aspect is you get the addition product. And the question is this stable or is this not stable under the reaction conditions? If you have an aldehyde or a ketone, then your X would be a hydrogen on R. This is not a good leaving group. So that would stay, and if you quench it, it would typically give you, so if you have X equals H or alkyl, and you quench this now, your reaction with H plus, of course you get the addition product. But if you have a good leaving group here, so for example a chloride or ethoxide, then you will be forming the ketone, but the ketone is more reactive, or might be more reactive, it depends what you're using here. If you have started with an ester, then your ketone is more reactive than the ester, and it will add a second nucleophile here, and then ultimately give you the alcohol, which has added two nucleophiles. And so when you have an ester, you cannot typically prevent this because the additional intermediate you have is very unstable. This breaks down by elimination. We all know why that is, because the carbon-oxygen double bond is so much stable than a carbon-oxygen single bond. So it wants to form back. It's very rapid, but then you generate the more reactive carbonyl compound than you might have in the beginning, so it's not working. So if you have, if X equal, if you start with an ester, for X equal ester, this is inevitable. It will happen. If you have X equals acid chloride, you might be okay, right? Because you go from an acid chloride, which is more reactive, you go to the less reactive ketone. So in this case, in principle, it would be possible to add to a acid chloride, for example, an alkyl lithium compound or a Grignard compound, and end up with the ketone. From the terms of reactivity, this works. From the terms of practicality, it does not work very well because the reagent differences are relatively similar, the reactivity, and especially when you start adding your alkyl lithium compound, and that moment you generate a lot of heat at that, and so you are not at such a low temperature as you might be. So in practice it is difficult. People have reported this. Very often they use ultra low temperatures, minus 100 degrees. How do you make minus 100 degrees? Minus 78 is easy, right? How do we make minus 78? Sorry? I don't understand you. How do we make minus 78? No! Liquid nitrogen. No, liquid nitrogen we can make minus 196 if we have to. No, how do we make minus 78? You all have probably done this. Dry ice acetone. Right? This is what we do. We take a dewar beaker, we take acetone, we put in dry ice until it's not going anywhere and until we have solid dry ice in there. And then if you put a thermometer on this, then it's minus 78. So that is pretty cool. That is a reaction we discussed that industry still doesn't like it. But in the lab, to do minus 78 is trivial. Might not be sufficient for adding an alkyl lithium compound to an acid chloride because it's still not cold enough. You need to make it as cold as possible to have the reaction differences between the acid chloride and the ketone you're forming. So how do you make minus 100? Liquid nitrogen is a good idea, but liquid nitrogen, if you would immerse your flask into liquid nitrogen, you would be at minus 196, and you would probably your flask would break and everything. So you need to put the liquid nitrogen into something. Sorry?
Dewar glass.
In a dewar glass, but still, you still don't want to put your flask into the liquid nitrogen because then you're having minus 196. You need like we do with acetone, you need also a solvent. But you need a solvent which is not solidifying at minus 100. So what has a very low melting point? What type of solvents? Alkanes. So typically you take something like pentane or hexane. So if you want to do minus 100 degrees, very often you use, I'll put it up here, so minus 100 degrees, so as I say, minus 78, trivial. Dry ice, acetone. We all know this. If you go at 0 degrees, trivial, right? Normal ice. If you do minus 20 degrees, still pretty trivial. It's ice and something like sodium chloride. We make an ice method. Minus 78, Already a little bit more sophisticated, but dry ice is relatively available easy. Minus 100. This is typically pentane, liquid nitrogen. And you might say this is still easy because I have the liquid nitrogen tank outside. You guys have probably here, you must have a liquid nitrogen tank somewhere outside. And so, okay, then I just take a beaker. You don't take a Dewar glass because this might break at minus 100. You take a plastic, big plastic bin or so, and then you do it there. There is an element of danger in here, very, very severe danger. And that is especially, let's say, you come in the morning, you get in one of these Dewar bottles, you get your liquid nitrogen. And then on the afternoon, you decide, I'm now doing a reaction at minus 100 degrees. And now I take this from my liquid nitrogen bottle and I pour it into my pentane vase. So the question is, do I still have liquid nitrogen in that bottle, which you have gotten in the morning from the big nitrogen tank, and that was probably all liquid nitrogen. The point is you don't have it any longer because during the day you start exchanging with air. And so you have a significant amount of liquid oxygen in there. And now if you mix liquid oxygen with pentane, you have an extremely explosive mixture because pentane, of course, is flammable. And now you have an incredible, because it's liquid, you have an incredible high concentration of oxygen. And so you need to be really careful. If this sees some spark or so, it will ignite. And so first of all, if you ever should do it, because there's no way, you always need to go fresh to the big nitrogen tank and get it, because you don't want to take a 1 day old the one from your normal bottle. But in general, it is hazardous, and so that is in general we try to and we should avoid such low temperatures, right? And so again, flow chemistry might be able to be a way around this, because again, the short reaction times might make it possible that here you have the acid chloride and you just mix, you make the phenol-lithium, then you bring the acid chloride, you bring it into this, and it will react immediately, but then you bring it out of your reaction system so that it doesn't have time to do a second reaction with a little bit less reactive compound. And so again, this is possible to do this in a good way. Okay, so then photo flow reactions. I see again we are running to the tea break. Let me do this here. So photo flow reactions are, of course, that is one of the best ways to do photochemistry. And we did here, it's an example from our lab, we did chemistry with the diazo compound. And so with the diazo compound, there is this danger of developing gas. And so we were also wondering, and we were very careful in the beginning, because there was also, when we did it, there was very little reported in the literature how to handle the gas which is being developed. And so what we have here, and you have essentially an oil flow apparatus, you have something like a back pressure regulator. And so when there's too much, when the pressure gets too high, it will reduce the flow intake of your compounds. And so this is here what we had. We had again 2 feeds. It's only shown here as one. We had the diazo compound, and we mix this, or in fact, because we do it on a photoreaction, only under light these diazo compounds decompose. So we have the diazo compounds, we had alkenes, or again furanes, you know that we like these, and we feed it into our flow reactor, which we can irradiate, and we could do the cyclopropenations. And you can see we could measure this. The pressure builds up, but we were able to keep it in a range which was okay for this photoreactor. And so this way we could, again, very short exposure times. Usually when we did these reactions, it was also on some hours, could do this type of reactions. And the last example I would like to show you, because also I learned quite a bit of how especially industry is evaluating these type of compounds. We had developed 4 years ago an iodoamination, photochemical iodoamination. And it's very attractive because it's so easy to do. You take N-iodosuccinimide, this is this component. You take a protected amine, which has only one NH available, so we can take this N-methyltosylamine, and we take an alkene. And under irradiation, the iodine the N-iodosuccinimide gets reduced by the amine, so you have an electron transfer. You're making these N-centered radicals, and the N-centered radicals can add to an alkene, and then the residing radical can start a chain reaction and abstract an iodine from the NIS and make the final compounds. And so we thought we had this, and this is a really great reaction. Again, works very broadly with all types of alkenes. And so we thought we should demonstrate scale-up. And the way we wanted to demonstrate scale-up, obviously, was flow. And so we did this chemistry in flow, and in a almost trivial way, we took the three components, and we thought it's ideal because you don't need a catalyst or anything, and so we just pumped this through a photoreactor. I showed this, the low budget photoreactor, I showed it to you right away. We are forming the iodoamine here, and then we thought, why don't we add a second flow step to show something in addition? And so we then pumped the product through a tube which has potassium carbonate in there, and this will deprotonate the amine, and then in a nucleophilic substitution, you are forming aziridines. And so we thought that's pretty cool. This might be a fantastic demonstration for flow, and so easy because, again, no catalyst, you just shine light on this. And so here's how we did this. It's a photo which is a little bit misleading because we have two syringe pumps here, but in this case we only need one because we can mix it all. Without light, nothing happens. And so we mix it. You see here is again such a mixture. If you go from 2 feeds to mix things properly, but we only go from 1 feed here. So we mix this, and then here's our LED setup. We can cool the LEDs set up from the inside. You see this block here where we can put water or cooling liquid through this so we can keep it cool. And then we have, so the light goes into this tube here. And then you see what we have done. You cannot see so well. Maybe you can see it a little bit better here. We just take Teflon coil. Teflon coil is great for photochemistry because it's transparent. We just do Teflon coil and wrap it around that photo lamp. So very small, very easy way to do this. And of course, the idea is that you increase the surface area, right? And so we did this, and the reaction works great. And then here's the second step, right? This is even easier. So our photoreaction comes in here, and then you see we just have a tube which has potassium carbonate in here, and we just pump this through, and we have done this at 60 degrees in a water bath, so we have just put it there. And it worked very, very nicely, and so we were very, very happy with this. And then what you typically do is you check. After a time, you check always the yield, and so we let this run for a total of 4.5 hours, and we checked every 30 minutes. We took like a sample, and we saw, oh yes, the yield is high, and then the red samples, we actually isolated the product to compare in situ formation NMR yields with isolated ones. And so also we were very happy about this, and so we could produce very high yield, 3.04 grams per hour, and we could do this. But we had done this batch reaction before. We had done it in batch, and the one reviewer had read our paper very carefully, and he said, we all know that you can do scale up and flow, but your batch reactions seem to work in a similar way, and in the batch reaction, the scale up, we only made 2 grams. And so the reviewer said, so where is the advantage of flow? You should think more careful about if there's really an advantage. And I think he had a very good point. And the other thing is, we were very happy that this would run so constant over time without decrease in yield. And so in our paper, our title was a robust photoiodoamination. And the reviewer comes and says, you guys know this does not qualify for robust. Because yeah, we know this is any flow reaction in this case is robust because you're just over a longer time you're doing the same reaction. Why should this be robust? And he said, and we checked and we saw that many people used the robust in the way we did it, but this person was probably from industry and he said, robust means that you are not sensitive against certain influence of parameters. And so I show this to you then what we did in a moment. So we repeated the reaction in batch on a larger scale this time. So the one thing we saw is that the yield breaks down, and I think we know why that is. Because if you irradiate, especially when you have iodine or iodinated compounds over time, you start, the reaction becomes dark. And then it becomes dark, and we could also see this in the UV spectrum. This is the initial reaction solution, but if we irradiate this for a time, then we build up and probably iodine and things like this. So the reaction becomes dark, and so that might explain why the efficiency in the batch is not as good, because you're forming colored compounds which you're not getting out like you would do it in flow, and so you suddenly start penetrating, your light penetration might not be as effective again. So a very simple consideration. We were very grateful to the reviewer that he pointed out that we need to make a better case why the flow is really helping us. And then when it comes to robustness, there is something which has become popularized by Frank Glorious, again, who's doing a lot of photochemistry, as the robustness scan. With robustness, it is really meant that how sensitive is your reaction setup against outside parameters or so. So it is. And then you typically have these robustness diagrams where here in white, this is like your standard conditions and there's no deviation of yield. So that's your benchmark, right? That's 0%. And then under certain reactions, the yield might actually even increase under certain conditions. But very often, if you have certain other conditions, the yield might go down. And so we tested this. And so one impurity of this type of reaction could be is that your NIS might have NHS present as a contamination. So here in this case, we added 10 more % NHS, and then you see we start here and the yield didn't change, right? And then we used undistilled styrene. Very often when you do alkene functionalizations and in a radical type regime, photocatalysis, you need to be aware that styrene very often is, when you buy it, has radical inhibitors in there because they want to prevent polymerization. So normally we always distill our styrene because we want to be sure, because we want to do a radical reaction, we want to be sure that there's no inhibitor in there which presents it. But in this case, you see, we took the undistilled styrene and saw if our chemistry is still working, and yes, it does. A typical contamination might be water. So we added some water and saw, is it doing anything? We changed the light wavelengths. We did the irradiation at 530 nanometers, and we saw that if you go to blue light, a little bit more energy intensive, we talked about this, you might form easier iodine. And so indeed here was the only type where we saw that the reaction yield went down a little bit. We recycled the solvent. And we saw that when we do the solvent recycling, the reaction still works well. We degassed the solution rather than running it on oxygen like we did originally. And again, it had a little effect, had actually a little bit of a positive effect, but so small that we decided that running the protocol under air, and especially when you do it in flow, to be sure that everything is degassed might be a little bit more difficult. Okay, so just a few ideas on flow. Tea break? I've talked again too long, right? God, it's so bad with me. You will hate me. Okay, that's okay. So that's last day. I go home tonight. So, okay, so let's have a small tea break, and then I promise you we will just have a small discussion about an industrial and an academic synthesis of a very important compound, which cost our government 50 million euros a few years ago. Okay. Last one. Last Let's see if I open this. Okay, so indeed, 5 days, it's almost over. And I just heard today that you guys were making a pizza party later this evening. And unfortunately, I cannot come because I have a flight to Delhi at 8:50. And although it's only 25 kilometers or so to the airport, it takes forever, right, to go there. And then, so I need to... Unfortunately, I was negotiating with Professor Sarkar if you leave at 6 or if I leave at 5:30. And yesterday we went only a quarter of the way and it took already half an hour. So I think I need to leave at 5:30. But anyhow, so I enjoyed very much being here with you and interacting with you. And if you should have any questions, doesn't matter if it's for the course material or if you would like to discuss maybe applications or so, send me an email. Write maybe in the header, in the subject line, write something like Gian course indoor or so. Because I'm getting so many emails with applications and so on, and I always try to read all of them and I always try to answer all of them, but it really gets too many. And so if you write in the subject line of your email, if you want to contact me and want to make sure that it catches my attention, write something like Gian course indoor, and then I do this, right? And so please, if you have questions or if you would like to, I don't know, you want to apply somewhere and show and send me and say, is it a good cover letter or not or so, then just contact me and then we will have a look at this, right? And unfortunately, as I think stated also before, I would like to take many more students from India and postdocs. Funding is so tight in Germany these days. And I don't know if you look at the news these days, I mean, we are running from one bad news into the next, right? It's unbelievable that this happens. I'm almost a little bit sad for you that this happens. When I was your age, that was like 1989, 1990. I thought the world is becoming a better place. Germany was reuniting, Soviet Union was crumbling down. I thought we were doing a lot better. And now look at this 30 years later, with so many crises and so many conflicts. Okay, but anyhow, you guys are the next generation. You might make a change, and you might make a change with chemistry. And since it's probably unclear at this point if you should go to industry or academics, let's take just an example and discuss both. And this is the compound I would like to discuss with you, because there are probably 200 syntheses out there for this compound, both from academics as well as from industry. It's just one of the compounds which, I'm standing in front of it, one of the compounds that really made a big impact. And although you can see it's not such a complicated compound. Do you actually know what we are looking at? Do you know that compound? So now new number here, careful, or new QR code. Okay, so one brave answer, two brave answers, three brave answers. So as you can see is that all these compounds I have put up here had some significance during Corona, but also even earlier when the first, and at that point we were afraid that it would end in a pandemic, but it didn't. Around 2004, 2005, when the SARS epidemic hit, which did not turn into a pandemic, and so on. Okay, 77% for remdesivir, 23% for heparin, 0% for propofol, 0% for oseltamivir. The last one would have been the correct answer. So 0%. So that's good. So you haven't seen this compound. So that compound, oseltamivir, is Tamiflu. And let me just see. Okay. All the other compounds I have put up here, remdesivir was the one antiviral drug with relatively complicated structure, which during Corona was thought it's an antiviral compound and might battle Corona, and it's still up today. Again, millions were used for this drug. It was not clear if it really helped. There were studies who said if you have Corona and you don't take remdesivir, it takes 2 weeks, and if you have Corona and take remdesivir, it takes 14 days. And so it was not really clear the benefits of this. Heparin as a blood thinner was also not really clear how much that worked. Propofol is an anesthetic. That is when you undergo surgery, you might get propofol in order to have that anesthetics. Michael Jackson overdosed on propofol because that also, when you take it as a recreational drug, makes you more happy, more relaxed, and so he apparently took too much of that, and so that's what he died on. And during Corona, indeed, propofol was very important because when you had this lung problem and needed to get intubated, that's of course not a very nice situation. You had to be put under anesthetics, and that's what they used propofol for. And we ran worldwide, we started to run out of propofol. Although propofol is a very, 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 very trivial, very, very trivial compound. And then again, it takes you, let me just give this to you, just to show you sometimes how simple problems can be, and still how complicated it can be to have word supply. This is propofol. Cannot really be a lot easier, right? 2,6-diisopropyl-phenol. And still we suddenly had during Corona, we had a worldwide shortage because we couldn't produce it long enough. But especially a shortage in Germany because many of the drugs actually are being produced for Germany in India. And suddenly everybody needed this, right? And so that was a very grave situation. So again, let's look at the compound again. This is oseltamivir. That's the rational name, or the name which was used in the literature. It's not the trade name. The trade name is Tamiflu. And so Tamiflu is a drug against influenza. But it was also thought that it's very good to battle SARS. And then one of the first drugs which were evaluated when Corona hit us, that they looked also at Tamiflu for Corona, but found immediately that it's not effective. But in 2004, when we had the SARS epidemic, then Tamiflu was supposed to be the one compound which everybody thought that this might be good. Our government in Germany, we bought for 50 million euros, we bought Tamiflu doses. So in order that our government said we need to be able to have a dose for every citizen in Germany, and we have about 80 million, and so you can see what we did. Unfortunately, we didn't need it, and so they stocked up on Tamiflu, and we didn't need it, and so you could say, oh, not a problem, so next pandemic might come, so we use it then, right? Not possible. Tamiflu expires after a year. You cannot store it for longer than a year. So essentially, we bought it, and we didn't need it. Fortunately, this is a good side, of course, but we could also not store it. It had to be destroyed. Okay, so this is Tamiflu, and at that time, 2004, 5, 6, many academic groups who did natural products broke up in a frenzy and said we need a synthesis, and then obviously industry needed that too. And in Europe, especially Hoffmann La Roche was the one company who really produced it. And as you say, we bought just Germany alone, we bought so many doses. We are talking ton scale here. And so, simple compound, right? It's a cyclohexene derivative. If you analyze this, it has 2 amino groups. It has an alcohol group. The alcohol group has a funny ether connection, whatsoever, but it has a funny alcohol. And then also it has an alpha-beta unsaturated ester. So, if that would be your master or your PhD project, throw onto me a few general, I don't know why this is black here, was supposed to show the structure of Tamiflu again. Throw onto me a few general approaches. You don't need to be very specific. Like, how would you consider, how could you think about to make this compound? Right? And I showed them to you on the previous slide here, right? You have a cyclohexene ring with lots of functionalities. What would you consider to build up in general such a compound? What type of strategies would you think might be good? I have it even two times. Funny, okay. I'm not sure what is happening here with the poll. I have it 2 times. The question is on different. No ideas. Can't be. I don't know. Think about this. Shikimic acid. I'm not even sure what this is. Someone must be very good here. Shikimic acid. Very good. Let's see. Maybe I know what it is. We will see about this. So shikimic acid. So what you would do if you think about this, and shikimic acid is a good point, you would look if you have available from nature some compounds which might be already pointing into the right direction. So a so-called chiral pool approach, right? You take a compound which might have good availability, and then you say, okay, maybe I can modulate this, and then I can do this. So shikimic acid, indeed, and that was something Hoffmann La Roche did. Initially, at least, they had a synthesis starting from shikimic acid. That was an interesting thing. I show you shikimic acid in a moment. Then they did the calculation and say, so how much do we need if we want to satisfy at least Germany for the doses? And they found out initially that the world supply of shikimic acid would not satisfy this. But in general, chiral pool is a very good idea. Quinic acid, yes. So somebody's sitting here who knows all the compounds which have a similar structure to Tamiflu. So indeed, quinic acid and shikimic acids are the 2 ones Hoffmann La Roche immediately considered to use. Yeah, also tamiflu phosphate, that's the product, of course. If you think about the structure, right? 6-membered ring, cyclohexene ring. What comes to your mind as a general strategy for a reaction? What type of approach could you consider to? How do we make 6-membered rings? One strategy which might come into mind is Diels-Alder, right? Diels-Alder, butadiene, some kind of a diene, and an alkene might make a 6-membered ring. Where else do we have 6-membered rings available, and where can we actually manipulate 6-membered rings very well? What type of compounds? What type of compound classes? Aromatic systems, right? Arenes. And we know very well how to put functional groups into arenes. We have all these tools, electrophilic substitution. We know how to put in nitro groups. Because look at this again. We have amino groups here on that 6-membered ring, right? So maybe putting in an aromatic system, putting a nitro group, reducing it to an amine. That's something we can do very well. Putting in alcohol groups, phenols, we know how to do this well. Putting on ester groups, right? Friedel-Crafts type chemistry. So arenes might be a good possibility, but here, of course, we have a cyclohexene type ring, and so, but we can hydrogenate an aromatic ring. So then this might be also a good approach to synthesis, to such compounds. And I will actually show this to you. I think that is something Hoffmann-La Roche developed in an also academic, spectacular way, how they used an aromatic starting material to make this compound out of this. So let's look at a few, and I know I need to be careful that I'm not again running over. So let's look at this idea of cycloaddition, exactly. And so now you are walking in the steps of Nobel Prize laureate E.G. Corey, because E.G. Corey has one synthesis out there which makes use as the key step, makes use of a Diels-Alder reaction, and here is this sequence which Corey is using, and this is, I think, it's a very, very nice synthesis. But we need to think about now, if you go to your boss in your company and you say, we should produce on ton scale now Tamiflu, and who could do this better than a Nobel Prize laureate, right? So let's do on ton scale the synthesis E.J. Corey and his group had published in order to make this compound. Let's consider how useful this is. So let's look at some of the reactions. So Corey is using butadiene and this acrylate. And you can see here already the first step what he's doing is he's using not a normal methyl ester you might have been used, he's using the trifluoroethyl ester. Why is he using this? Because that makes it even more electron deficient, and butadiene, and we talked about this, and in a 4+2 cycloaddition, you need to come as homo-lumo gap, you need to come as low as possible, and so he's taking an electron deficient, even more electron deficient ester with this trifluoroethyl group to bring that gap together, right? Because butadiene typically is not the most reactive, diene in the Diels-Alder reaction. And then very nicely, look what he's doing is he's catalyzing this with a boron-Lewis acid. And the boron-Lewis acid, of course, is coordinating to the ester group, and in this way brings that even further down. And Corey is using a very interesting type of Lewis acid. So we all know that boron, which has boron with 3 ligands, is Lewis acidic, right? That's because it still has the force coordination side open and can act as a Lewis acid. But look what he's taking as a ligand. He's using a ligand, it's essentially a proline type ligand, but look at the nitrogen. That nitrogen when it coordinates to the boron, is a positive nitrogen. So that is not a very strong ligand that in order to do this coordination. So essentially he's coordinating with a tri-substituted amine, and this way he builds up a positive charge here next to the Lewis acidic center. So that makes it even more reactive. And then he is the Lewis acid he's using is chiral, so it has a chiral center. And this way there's a chance to do this reaction enantioselectively, and that's what he's able to do. So he's able to do this Diels-Alder reaction, and you can see he gets 97% yield. That's pretty cool. He gets 97% EE. This is really nice as well, and so he's able to do this. And then very instructive, I just want to go over a few issues here. It's very instructive how he's introducing the nitrogen, the amino groups, and that is something which will concern us in the industry synthesis also a lot. So what he is doing is he's converting this ester into an amide, and then he's using a reaction you might better know if you have a carboxylic acid here, but here's an amide. He's using an iodolactamization. And this iodolactonization works in the way that you have iodine. We talked in the electrochemistry a lot that this is like an equivalent for iodine plus, iodine minus. And so if the iodine is coordinating to the double bond, let's get some of the pens here. So you are forming the iodine plus. Here it goes up, and you've seen I've drawn this with an iodine on top, but I could have also drawn this. The iodine could also have come from the bottom, the I plus. So we have the NH2 here. And the beauty of this reaction is that this is reversible. And iodine, the iodide minus you will still have there, will not attack this iodonium ion, because making a iodination on an alkene is thermodynamically not good, because it makes two weak carbon iodine bonds. And so the beauty of this is that once you have these iodonium ion, you need a better nucleophile, and the better nucleophile is your amino group here and the amide. And you can see here then, this attacks the iodonium salt and forms this lactam. And the good thing is, because this stereocenter is down here, it can only do this, and only can reach this center if it also comes from the bottom. For the iodolactonization, it doesn't matter if the iodine comes from top or the bottom, because it's reversible. And only when it comes from the top, then the nucleophile will kick it in and kick it out. If it comes from the bottom, nothing can happen, because it's an SN2 reaction, and then it comes back. And so that's an interesting fact here, right? This is the first amino group Corey has installed, and in this case. And then he's doing a couple of more reactions. I do not want to go through this, but if you're interested, it's interesting to read the paper. It's a JAX communication which has only 2 pages. Half a page are references. So pretty cool. You could see how important that chemistry was considered. All he had to do is essentially say how to do it, and then he gives some explanations to these type of reactions. So then what he's doing is, let's just go quickly. He's protecting an amino group. He is eliminating. He's now eliminating this iodine to the double bond, because we need a double bond here in the end. Okay, it's not seen, the Tamiflu here. And then he's doing an allylic bromination, brings this back, and he's doing another elimination. So you see what he's essentially doing now, he's converting this iodocyclohexane by addition-elimination chemistry. So first elimination gets the double bond, then allylic bromination, and then another elimination to get the diene in here. So he gets this intermediate. And you can see, and also he's cleaving the lactam. And now you see he has a stereocenter here. The stereocenter here originally here is lost, but he had transferred the chirality to this position. And then again, he's doing a bromoamination. I showed you our variant of an iodoamination. We are actually interested in see if we would make this compound, if our protocol for the iodoamination might also work here or not, right? And by this iodoamination, you see now it's interesting to see he's installing the second amino functionality he needs here by making an aziridine, and then he opens up the aziridine with this alcohol we need in the Tamiflu. And we have 2 possibilities to open up the aziridine. The nucleophile has to come from the bottom because it's an SN2 reaction. And you see if it would come on this carbon, then the neighboring substituent would be in the way. So this is sterically more hindered. If it comes onto this carbon from the bottom, it will install this. And then what he had to do is, and then again very cleverly, he has two different protecting groups, how he brings in the amino functionalities, and one is very acid labile. He can selectively deprotect the WOC group and then make the ammonium salt, ammonium phosphate, which you need. So very nice. I think in his title he says something like a short synthesis of Tamiflu, and I think we can count the steps. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 11 steps. So I would say it's a medium-sized synthesis. So now, as an employee of the company, you have read about this publication, and you go now to your boss and says, okay, I know, or Corey has shown us how to make Tamiflu. Now we make a ton out of this. How would you evaluate this synthesis? How would you, if you look at what was accomplished, do you think this is good for ton scale? I thought I had a question to this, but anyhow, maybe we leave it there. What do you think are weak points to do this chemistry on large scale? If you look at the sequence. Sorry?
More steps.
It's many steps. Yeah, but we will see. You will see that it's a relatively complicated structure with stereocenters, groups, and so on. You will see that the industrial synthesis I'm going to show you, that also has steps. There's no difference in that. But are there any steps where you would think maybe that is not so suitable if I would like to do this really on scale, if you evaluate this? So you have a lot of steps where you fiddle around with the functional groups. But I would like to draw your attention right away on the first Diels-Alder reaction he's doing. What do you think if you evaluate parameters for that as a catalytic Diels-Alder? How would you evaluate the conditions that catalyst is operating? Look at this, what we're needing. You need 10 mole percent. That's already a pretty high catalyst. We can probably calculate the molecular weight. You see, 10 mole percent means one equivalent will be converted by 0.1 equivalent here. So the mole percent is the one parameter you want to look at, but the weight percentage is another one, right? And look at this. You have a product here which has 6 carbon, 7, and let's count the oxygen as a carbon as well. So 6, 7, 8, 9, 10, 11, and then 3 fluorine atoms. Let's say we have about 14 atoms and more or less molecular weight of on average on 15. So we're making a compound which has like a molecular weight, let's say, of 320 or so. Look at our boron catalyst here. So this has, again, it has 5 atoms here. Then it has 2 phenyl rings, so 12 more coming. So that's 17, 18, 19. Then the boron 20. We have a toluene group that has another 6 atoms here. 7 because it's a toluene. So 23. So that catalyst has a higher molecular weight than your product. So if you not consider mole percentage, if you consider weight percentage, you are probably around more than 100% of weight percentage. So in other words, for 1 kilogram of product you might make here, you will have 1 kilogram of catalyst. It might be recyclable, but it might also be waste. And so that is one point which is of course difficult here. Look at the reaction time, 30 hours. This catalyst, it's attractive, it's room temperature, But this catalyst, it makes 10 turnovers in 30 hours. This is 1 turnover every 3 hours. Think about this. That's a pretty lazy co-worker, right? You would not, amazing. So this step alone is, I guess, very difficult to scale up and make that useful, right? I think all the other steps are okay. What is nice, of course, is that you are installing the stereochemistry. You start from very inexpensive starting materials. These are clearly pluses, but the catalysis which is involved here is not really good. So let's look at this, and again, let's look at the approach of Hoffmann-La Roche now. And I very much, it's public domain, it's open access. I very much, if you are interested in reading more about the story, this is a fantastic article by Karpf et al. These are the Hoffmann-La Roche people, and they do not just list synthesis by synthesis, they also tell the stories around this. And I think this is always very valuable just to hear a little bit about this. And it's fascinating to read. And so in making these antiviral compounds, they considered oseltamivir, but there were also other compounds available. But it was clear that this is probably the best. And so that's what they, assessed. So. And so then there was first the discovery process. And in the discovery process, they said, it's enough if we have a few grams. Let's get that compound as fast as possible so that we can evaluate this. And here you see, here's one of the compounds which people have mentioned, the quinic acid. And here's the Tamiflu again. And if you look at the structure of quinic acid, I think you will immediately agree that this is maybe a very good starting material for this, because you need to somehow eliminate that hydroxyl group. And then you have the 3 other functionalities. You somehow selectively have to exchange 2 of the hydroxyl groups for the amino groups here. So that looks doable, right? And nevertheless, look at the steps. In the end, somebody just said steps. So that's 6 steps. They made this epoxide. So essentially, they did the elimination, and then they had to differentiate somehow the hydroxyl groups that they could make the epoxide only here. Then it took them 4 more steps by ring opening, ring closure reactions to convert the epoxide to an amine. Took them 4 more steps to introduce a second amino functionality, because we need in the end a diamine. And then they were open again, like Corey did. They were able to open the aziridine on this position, get the alcohol in there, and then get it on there. So that's again, it's 6, 10, 14. I'm not sure if this was done in one pot or not, but let's say it's not. 15, 16, 17, 18 steps. Ooh, that is, so Corey is right? And he publishes and says short synthesis. So his stepwise, his synthesis is definitely shorter. But the nice thing is here, you bring in the chiral information from the chiral pool. This was good. And so it allowed them at that stage to evaluate the chemistry. And one thing they were interested in is this alcohol, this 3-pentanol, is relatively expensive. And so the interesting question was, could you exchange that alcohol for something simpler? Easiest case, could we make a methyl ether here, right? Using methanol, ethanol, propanol. You see what they tried. And the interesting thing is, indeed, the biological activity is very dependent on that alcohol group. The smaller the number, the better, right? These are the IC50 values in nanomolar. This has an IC50 value with this alcohol of 1 nanomolar. If you go to methanol, you go 3 orders of magnitude, you go down. So they very quickly decided that this is indeed the target they should pursue. Okay, so this was quinic acid. And then they had a few more issues, and let me tell you about this. So the quinic acid came from a bark of a tree, and they said, they calculated and said, how much do we need? If we develop a chemistry based on quinic acid, how big can our scale up? If we close our eyes and we can do it as big as possible from the chemistry we want to develop, will we have enough quinic acid in the world in order to do this. And they did the calculation and they decided, no, we don't. There's not enough quinic acid on the world to satisfy the demand we have. And then let's look at, again, what people think about sometimes in industry. So nevertheless, they had this synthesis I just showed you before. They made a few steps, but they had also a few low yielding steps, right? So that is something which was not so good. And then they did also some protection chemistry where they would, for example, exchange this acetal, which they had made in the beginning of the synthesis. This is an acetal of acetone, where they would exchange it for the pentanol. That was the ether, this funny ether group you need in the end, right? It's here still as an acetal. In order to do this, they use, as an acid catalyst, they use perchloric acid. That's not a good idea either. And so perchloric acid is explosive. And so you don't really want to use this. And again, a word of caution is, we had, especially at universities, we had terrible accidents with perchloric acid. And I tell you how that happened. Especially our friends from inorganic chemistry like to use perchloric acid a lot. And so all is fine, small amounts and so on. They didn't really do it a lot, but the point is, it's kind of volatile. And so what happens is the perchloric acid gets absorbed very, very well by wood furniture. For example, by the wooden hoods, right? I'm not sure, I haven't seen your labs, I think. Your hoods, they have plastic polymer also, or they still have wood outside? They are plastic already, right? There's a good reason for this, because the wood is absorbing very often lots of chemicals. It's porous and so on. And so the perchloric acid, if you would have a wood hood, would go into the hood and into this wood of the hood. And over time, it would accumulate more and more and more. And then finally, the university came and said, hey, we renovate your labs. We give you money for new hoods, and we do this with, we use the plastic, the polymer-like coatings. So in order to dismantle the old hoods, then some workers came in, and then with axes and so on, they dismantled the hoods, they destroyed it. So they went there and they cut, or with a saw also, they cut the hoods. And then that was the moment it exploded, because these wooden frames had absorbed so much perchloric acid that then when you would go there with force, so that's sensible against pressure and also against fire, when you went there with an electric saw, it would just blow up, and really in a terrible way. So that is, again, so the safety concern here to use this acid, again, this is what the people did in the lab on a small scale. You go to your process people and they say, no, we don't want this, right? And then there are some other issues. The introduction of the amino groups is being done with azide. And that is a terrific nucleophile. If you use azide as a nucleophile, you open up, for example, this aziridine here. These reactions were really fantastic. But again, the point is that azide is is dangerous. They had some more issues here. They were reducing this azide to an amine, and they did a Staudinger reduction. You can do this with palladium on charcoal. You can make an azide to an amine. They were kind of afraid that they might hit the double bond here. So a very reliable way to reduce an azide to an amine is that you use a phosphine. You do a Staudinger reduction. Trimethylphosphine stinks terribly. And so again, that is a great reaction, but in a production setting or so, where you might not be able to control always the emissions, it's not a good reaction. So again, the chemistry worked, The lab people were proud on themselves, and the process people said, no way. There's so many red flags in your synthesis. And so that was essentially the first generation, the summary. So here you see the quinic acid. The shikimic acid already has the double bond installed, and this is the double bond you need here, right? So the shikimic acid and the quinic acid are differing by the elimination here of that hydroxyl group. And the quinic acid, anyhow, because it comes from the bark of a tree, was not so attractive starting material. But for the shikimic acid, in the beginning, you couldn't find good sources, but very quickly it was found that it is in plants in China. You can grow this and extract it from that plant. But also, because obviously in Europe we didn't want to be so much dependent on the source from China, Hoffmann La Roche also found out very quickly, and they are very great in fermentation technology. They found a way to make shikimic acid on ton scale to do this, to have it as a starting material. And so with this, they had quite a number of good syntheses, but there were issues, and one of the big issues is to avoid azide in industry. And so rather than opening up the epoxide with azide, they wanted to open up the epoxide with the amines. But let me ask you this, what is in general, so you have a leaving group, what is in general the problem if you want to open up, I don't know, let's say an epoxide, in general the problem in this nucleophilic substitution of amines with epoxides or halides or so? Why is that something which is not straightforward in difference to the azide? And if you think back maybe in your basic organic chemistry, you have not done this for an amine synthesis. You did something like a Gabriel synthesis. That is, right? So if you think back about Gabriel synthesis, you are not using ammonia or an amine. You were using the potassium phthaleamide. And then maybe you do the nucleophilic substitution, you generate the phthaleamide, and then you hydrolyze this, and you're getting your amine and phthalic acid. So why can you not do it directly? What's the problem if you use directly an amine? Why do you have to go through a phthalic acid, ester, or the reagent? I'm not sure if I have this. Do I have this as a question? No. Any idea what is the problem? It's first year organic chemistry. I know, it's the 5th day here, so you guys are hanging on the ropes. I fully understand this. Why can you not synthesize amines by nucleophilic substitution with an organic halide? And the reason for this is that when you generate your amine, you see here in this case, the example I've chosen, this is a primary amine. Now I do the opening, it has an alkyl group here. This is a secondary amine. Which one is the better nucleophile? The primary amine or the secondary amine? It's a secondary amine, right? Because it becomes more electron rich. The alkyl groups are donors. And so the problem is that this secondary amine will now react preferentially with with your electrophile, for example, with the epoxide. And then you are forming this tertiary amine. Now you have a tertiary amine. Which one is the better nucleophile? The tertiary amine, the secondary amine, or the primary amine? It's the tertiary amine. So you go from a less reactive component to a more and more reactive component. And that is in general the problem in the amine synthesis. And this is why we need to use phthalimide here. That's the Gabriel synthesis. You see this one here, this has here of course 2 electron pairs. This is nucleophilic. But once I do the first substitution, this is not nucleophilic any longer because that lone pair is now distracted in the resonance here. And the same thing with azide. Azide can only do one nucleophilic substitution. This is why azide is so great, because it's a great nucleophile, but it cannot give you this over-alkylation. And so then, nevertheless, what they tried here at Hoffmann-La Roche is, and they came up and they tried conditions, adjusting the amount of benzylamine. They used very good Lewis acid, ytterbium triflate. Ytterbium is very oxophilic, so this activates epoxides very nicely. And they were looking at this, and so they could, in a way, they could get the monoamination going, but they activated the epoxide with the ytterbium so much that it would open up in an SN1 type reaction, and you would have a rigor selectivity problem. So you see they got this. And then actually once under the Lewis acid interaction, they would start seeing elimination of the alcohol, and they would eliminate so many of the groups here, both the water and also the amino group, because it would go into an aromatic system, and there was a severe side reaction that they could not do it. So again, this was a problem, and then in the end, don't really ask me why, but they found conditions. They found that allylamine was really good to not give them these over-alkylation chemistry. They found very specific conditions to do this substitution, and then continue on in the synthesis with having where they introduce the amino groups, and they do this again. They do this in the second type. Also the second amino group ultimately is introduced by nucleophilic substitution of the allylamine, and they had conditions which allowed them to overcome this problem of over-alkylation. And so this way they had a good synthesis, and you see here now, it's the overall yield is spectacular. The number of steps is still pretty high, but the yields they have overall, the worst sequence they have here, one step is 70%, one step is 77%. Many of this is quantitative, so that is pretty good. Okay, there's some more things. Now I would like to show you a shikimic free route, and as I say, this is, in my opinion, a synthesis which is not only from industrial relevance, because they could do it on a really good scale, but it's also from an academic point of view. It's a fantastic synthesis, in my opinion. And so what they did here is, you see, they start from a aromatic precursor. They start from a phenol which has these 2 methoxy groups outside. This was commercially available, and so you could buy that, and for relatively little money. They installed, in the first step, they installed the alcohol group. They need here simple William ether synthesis. You deprotonate the phenol, and then you do a nucleophilic substitution on the mesylate. And then also very nicely, they do a very selective and high-yielding dibromination. I could ask you, why are the 2 bromines, so you do double bromination, why do they go in these 2 positions? Why are they not going into this position? Can you see this? What is the reason that the selectively this goes into these 2 positions? I need to, okay. Any idea? How do we analyze this when we go and say auto-power method selectivity of in electrophilic substitutions? A phenol is a donor or an acceptor in the OH group. It's a donor, and that is auto-power, right? Very good. So then we have already probably everything. So this methoxy group here, this methoxy group, and this methoxy group wants to do auto-para direction, these two. This methoxy group wants to do auto-para direction. And only this hydroxyl group wants to do the direction here. So two groups say, hey, bromine, this is where we want you. And only this group says, you should go here. And so because the plus M effect of these two groups goes to these two positions, this is indeed what you're observing as the product. And then also very nicely, what they do is a type of palladium catalyzed installment of an ester group here. And this is again a really, really, really good reaction. This is, you have the aryl bromide here. And let me show this. This is like one of these palladium coupling reactions, but it's a palladium coupling reaction which is a carbonylation. And so in this case, you make the oxidative addition with a palladium zero catalyst, as you always have, and then once you have this, if you have carbon monoxide as a pressure there, carbon monoxide pressure, what you do is this coordinates first to the palladium, and then it does an insertion. And then in the presence of methanol, or ethanol, because they're making the ethyl esters, you exchange the halide group you had here, so your X is originally the bromide. You exchange this for the alcohol, and then if it's doing a reductive elimination, it is installing the ester group. And look at this. This is a pretty good. So first of all, I think I don't know if you know it or not. All these type of palladium couplings is palladium zero, right? But you see here that what they start here is a palladium 2 plus salt. But that is in all these palladium coupling reactions is very easily possible, because if you use a phosphine ligand, and you typically use a little bit of an excess, palladium 2 gets reduced by phosphine ligands very rapidly. There was a publication who showed this. If you use palladium acetate and triphenylphosphine, and you need traces of water, you make essentially palladium 0, 2 molecules of acetic acid, this is where your acetate goes, and you make triphenylphosphine oxide. This is, by the way, something you need to be aware of if you do asymmetric palladium catalysis, that if you start from a palladium 2 precursor and you have a chiral phosphine ligand, you destroy, in order to make the palladium 0, you destroy part of your ligand. So you need to adjust for this if you want to do this approach. And look at this. This is pretty spectacular in my opinion, what they have been able to accomplish here. They have installed these two ester groups, 95% yield. That's pretty cool. They do this with 0.5 mole percent of palladium. This means because they do it twice, right? That's 0.25 mole percent for each of the ester groups. So 0.5 mole percent, but doing this twice, that would be a turnover number per ester group of 400, right? I think, I'm not sure if I calculated this right here, but I think so, right? So that's a very, very good reaction. The other thing to realize here is the reaction times are still relatively long. High temperature palladium chemistry is really robust against high temperatures, so they could do this. And this DPPP is their phosphine ligand, which they were using. So they're making this, and now they do a hydrogenation of this arene molecule. And the interesting thing is, if you do a palladium, or they do ruthenium on aluminum oxide. So essentially, you have a support. You have your support and your ruthenium catalyst, and the same is true for palladium. And then if your arene is approaching this, and your catalyst is activating hydrogen, the hydrogen is simultaneously delivered all from the same side. So if you hydrogenate an arene, it's always a cis addition on the whole arene ring, because you can think about this, it comes like an UFO, right? It comes down, and then the hydrogen, it picks up the hydrogen from the same side. So then they are able to make this compound here in this hydrogenation reaction. Now here's my question. Now we have here 5 stereocenters. Is this a chiral compound? Why is it not a chiral compound? Has a plane of symmetry, right? Has a plane of symmetry. So if we look at this, this is still achiral. And so they still are not dealing with any types of stereocenters at that point. And for some reason, in the next point, they take off the methyl groups here with a good nucleophile. Let's not go into this. And then here comes the decisive step. They're doing a desymmetrization. So what they do is with an enzyme, the enzyme will only saponify one of the 2 ester groups. Now, is this molecule now chiral? Yes, it is, right? Because I have broken the plane of symmetry by going from the ester to the carboxylic group. So now they suddenly have an enantiomerically pure compound, and they have found an enzyme which is doing this, and it's the most cheapest pig liver esterase you can buy from Aldrich, and it costs nothing, right? They found, and it is hydrolyzing esters very well, and they found that it is very selective in doing this. Let me just when do we start? When are we supposed to stop? What does the time schedule say? Because I don't know, I don't want that all you remember from this course is that he always did too long. So this says 12:45, that will be in 3 minutes. 5 minutes. Let's quickly think about that strategy. A desymmetrization compared to a kinetic resolution. What is the difference? So if I have a desymmetrization, and this is what they are having here, then you can have a symmetrical compound. Let me use this diol. This is achiral. And now you need a chiral reagent. A chiral, like in their case, it's an enzyme or so. You need a chiral catalyst. And let's say you need, and you use a acylation reagent. So let's say we're using acetic anhydride. And now what it needs to do is it needs selectively to react with one of these two enantiotopic alcohol groups, right? These two groups are enantiotopic because if you selectively functionalize the one or the other one, you will produce enantiomers. So enantiotopic, right? These two groups here. This pen is terrible. Next time I want I write so nicely. Here I have my old lecture notes with me. I write so nicely with my iPad. This is much harder here. Okay, so right, and so the idea is that my catalyst will differentiate between the two enantiotopic alcohol groups, and it will make this compound. And so this is now chiral, of course. And the maximum yield I can have in principle is 100%. And this strategy differs from the strategy of doing a kinetic resolution. In a kinetic resolution, what you usually do is you're not taking a achiral so-called meso compound. In a kinetic resolution, you start with a mixture of enantiomers, and now again the same idea. You have a chiral catalyst, you have a reagent, and now you make use that your chiral catalyst will react with one of the enantiomers faster than with the other one, right? The interaction of the chiral catalyst with your chiral substrate is a diastereomeric interaction, and so chiral catalyst with enantiomer R and chiral catalyst with enantiomer S are diastereomers, so the rates might be different, and therefore you might end up with the one enantiomer which is untouched, and the other one which is functionalized. So this is the so-called kinetic resolution, and here of course the maximum yield can only be 50%. Right? So the desymmetrization typically is a nicer approach. And then finally, there's something like a dynamic kinetic resolution. If you have conditions which might equilibrate your two enantiomers, and I give you again a very well-known example which comes from Nobel Prize winner Noyori. He looked at the reduction of malonates. I'm afraid I'm too low on this. So you see, let me. So the dynamic kinetic resolution this is the example from Noyori's lab. He could take a racemate of these beta ketoesters. You see, this has a stereocenter, but you could use it racemically. Let me nevertheless give you one stereocenter, and let me draw both enantiomers here. And what he could do is, with his famous ruthenium binary catalyst. So these are this is in this case here the chiral catalyst. And with hydrogenation, he could hydrogenate the keto group. And he could do this enantioselectively, so the delivery of the hydrogen would be enantioselective on that keto group, but the catalyst would only react with one of the two of these enantiomers. But then if you do this under basic conditions, you can equilibrate these two, because this is a proton which has a pKa of about 10. And so under very mild basic conditions, you deprotonate, reprotonate. So you equilibrate this, and then your chiral catalyst will only react with one of the two enantiomers. It's doing selectively the reduction. And so this way, from a racemic molecule, you come to the enantiomerically pure molecule. And in this case, again, the maximum yield can be 100%, because we're equilibrating now the two enantiomers. This is a very strong, very strong technology, and and then selectively we're able to hydrolyze one of these reactions. And look at this, yields and enantioselectivity is really fantastic. And so we're not going to do anything a lot more now. In order to, once they had this, they have been able, you see now they are putting in the carboxylic acid, converting the carboxylic ester into the amino groups, and they do Curtius type rearrangements. I'm not going to go into this reaction. If you don't know, don't worry, but you can rearrange a carboxylic acid into an amine with this type of reagent, DPPA. Again, the difference, the problem with the DPPA is it's an azide reagent. It's this reagent, and it takes a carboxylic acid the acyl azide, and this in the Curtius rearrangement will convert to the amine and carbon dioxide. Lovely reaction, but again with the problem, it's azide chemistry, right? But still, that's how they got it on, and then they had to do a few more steps in order to produce it this way. And so, at least for Germany, they have been able to very rapidly satisfy the amount. So our government says we give 50 million euros, but we want one dose. I'm not sure how many doses actually they got for each. I think that it was on the range of 1 dose per person. So it must be 80 million doses or so. Pretty expensive. Of course, Hoffmann-La Roche wanted to also to showcase that they can do it. The strength of Hoffmann-La Roche is indeed they have a biotechnology. They are very strong in biotechnology. So all these enzyme type chemistry, they are very, 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 very good at this. It's a terrific. I'm not sure. Is Hoffmann-La Roche also in India? You have branches here. I don't know. It's a fantastic. It's a great Swiss company which has also one site in Bavaria, relatively close to where Regensburg is. Okay, so only 10 minutes too long, right? But we started a little bit faster. So overall, I hope you like this. I enjoyed teaching here the last week very much, and so thank you all for coming here. The one thing I hoped I could do with this course is I didn't show too many reactions at you. I think if you want to learn about reactions, you can take a textbook and just read about this. I was hoping more to get across ideas, right? What are people, do you consider what is a good process, what is a bad process under safety issue concerns, under renewable resources. We talked about photo and electrocatalysis, which is hailed to be a new type of green methodology, right? And so we didn't do too many examples, I think, but hopefully you like to think about the ideas why this might be good technology and maybe not. And so I'm sorry that I missed the pizza party. I had already twice at this Domino's place where you will have it tonight. I already had twice a pizza, and unfortunately, I'm going to miss it. And they have the pizzas are very good. I can tell you, it's very, very good. So anyhow, again, if you want to get in contact with me and discuss some things on future perspectives, send me an email, do the subject like Gian course indoor, otherwise I might overlook it. And then maybe I have the chance to see one or others of you too. Again, at least from the students from indoor, I will come regularly. It's already my third time. I will probably come back this fall again. It's always lovely to be here, and so I enjoyed myself very much. So thank you very much for coming here.
So you are all fine and enjoyed the IIT Indore stay? No? Yeah, okay. Okay, shall we start? Okay, very good afternoon to you all, and I think we are in the last session of the Gian course, and this part of the course I felt that I will dedicate to organocatalysis, okay, and so with the discussions what we started yesterday is on the sustainable chemistry part, that we are in a place where we need to think of lessing down the metal catalysts. We know about Hake couplings, we know about Suzuki couplings, and the reactions are extremely rigorous with high yielding reactions with high enhancer selectivities. But again, we come to a point where we need to think that we should think of economic protocols and most importantly, the environmental concern. So this is the place. That's why I feel that students coming up with organic synthesis background should think about organocatalysis. I've given a name. See, it's written as enzyme catalysis simplified. So we know that how enzymes have been so active. They create stereocenters very, very, very specifically. But the only thing what we feel is, the time. The time required is really, it's too lengthy, and I feel that we should think of reactions where we should find a substitution of this faster or this slower reactions. So I think that this is the place where we start attempting organocatalysis, and to simplify some simple words about organocatalysis is that it's an acceleration of reactions with an organic compound and does not contain a metal atom. So we feel that we should have an organic substrate and also an organic reactant, preferably a catalyst, and that drives the reaction, and we get a fantastic product with very nice enhancer selectivity. So we talked about enhancer selectivities yesterday. Also, we saw molecules of multiple chiral centers. So if you look into this, the first one, what we discuss about the reaction pathways, and the first thing what comes to my mind or any organic synthesis mind is an iminium catalysis. So you can see that it goes through via a covalent activation complex. You take a carbonyl, you take an amine, form an iminium, and then there is a deprotonation to generate a new organic fragment or new organic ammonium molecules. So this happens to be through non-covalent activation complexes, basically hydrogen bondings or ion pairing, and most importantly, it generates a CC bond forming reaction. So we feel that if there is a carbonyl, there is an activation of proton, and then further it generates a carbon-carbon bond. This is where we achieve an organocatalyzed CC bond generation. Okay, so what are the advantages of organocatalysis over metal catalysts? Many metals are poisonous, we all know, which often present a problem with production process in chemical and pharma industry. So we discussed about, yesterday, making of molecules, the cost related with molecules. Again, you see this, we use a binap, this is what is a chiral ligand in the synthesis. What do you generate? You generate an L-DOPA. So what is L-DOPA? L-DOPA is a drug which is given to hypertensive patients, especially when they, female patients, when they undergo pregnancy. So this is something which decreases the high blood pressure, particularly in pregnant women. So it's very important drug, but you see, how do we synthesis? How do you synthesis? The first step, just see. Do you know what is we use a rhodium cyclooctadiene BF4 as a catalyst in this industrial state. Not only this, we use a 3 bar pressure, 50 degrees centigrade, very high yielding, enhanced selectivity definitely. But what is the cost of this? It's too high. If you intend to buy rhodium cyclooctadiene complex to go for 1 kilogram reaction, we need at least 3 lakh rupees for this catalyst. So you can understand that when you generate L-DOPA through this metal catalyzed reaction, the expense for making this old L-DOPA tablets becomes very high. Thus, we feel that there is definitely a need to replace very high expensive transitional metal complexes in such reactions. Not only this, it's also very poisonous and it pollutes the environment. So all these things lead us to a place where we feel that organocatalysis comes to be very, very important. And thus, we feel that what are the replacements? So we know about stannic chloride, we know about BF3. You can ask me a question, sir, why not stannic chloride? Why not Lewis acid like yttrium triplets? But if you please check this catalysts, they don't give us very high enantioselective selective conversions. They react very badly with substrates. If you have an alcohol and if you add yttrium triplet, it's going to dehydrate an alcohol. For example, all such transformations where we use Lewis acids like aluminum chloride, yttrium triplets, stannic chlorides, all these suffer from many side reactions, what we don't want. Metal-free reactions can typically run under aerobic conditions. Okay, so the best way we talk about publication in journals like Green Chemistry. Why do you do that? Why green chemistry is very important to us? It's important because that gives us a way to support the environment. Often chemists are targeted, especially organic chemists are targeted that we don't follow environmentally, saving protocols. But it's not that. So we feel that organocatalysis, which are substituents to metal-free reactions, you can run in aerobic conditions. I'll tell you a story. When I was doing my postdoc in Stanford, every weekend we are a bit in trauma. What is that? Why I was in trauma as a researcher? Every weekend the cop will come. What is a cop? police, and you know the American police is much healthier than us. Okay, they look like police. Okay, and they come with a white handkerchief like this, very clear. They come to me or every researcher, and we had a sink where we used to work. We had a fume hood, we had our reaction table, and we had also a sink, and the sink had a pipe like this. So it comes straight, there is a curve, and then it falls down. What the cop is to do, it's come and he will tell you that, okay, I'm going to check your basin. They will take this white cloth and just wrap where it is you. And if you find some metals which is stuck there, you are going to be fined. Okay, they're straight away going to fine you with $500 because actually you did not follow the protocol, because you had things where you can dab your metal rests, where you can dab your solvents. You have not done that. So we're very cautious. Definitely, you know, the foreign or, you know, abroad people were much conscious earlier. That is why they are, you know, they already have been maintaining so many sustainable strategies in chemical synthesis from the very beginning. Now, when we start organocatalysis, the first thing what comes to our mind is a phase transfer catalysis. So what is a phase transfer catalysis? Phase transfer catalysis is a catalysis which is done in between the two phases, right? What is that? What we know in chemistry is one aqueous phase and what is other is an organic phase. So if you think of phase transfer catalysis, I personally feel that cinchona alkaloid derived catalyst comes first. Then there is a guy called LIGO which has sufficient contributions on such catalysts, and then comes Marwoko from Japan, and I will show you one by one, and we will see that slowly we have been developing these organocatalysts under the phase transfer catalysis, and these two persons, LIGO and Marwoko, have been, you know, very, very strong contributor on that. You can ask me, then why did the Nobel Prize go to Macmillan and Benjamin List? That's definitely true, that Nobel Prize in organocatalysis have gone to these big stalwarts, but again, I'm telling the progress. So it started with LIGO and Marwoko. I will also show you that what contributions have come from the List laboratory. Okay, but I personally feel that LIGO's contribution and Marwoko's contribution has been immensely active in case of organocatalysis, particularly phase transfer catalysis. And the second part of organocatalysis deals with something like proline catalysis and imidazolidinones. Okay, now let us come to one by one. So the picture shows something like what do you mean by a phase transfer catalysis. Was this, you can find an imine and an ester and a quaternary salt here. Okay, so this is what is in the organic layer, and this is what is an aqueous layer. So when you do something here in between the interfacial, or you find the aqueous reagents entering this layer and the organic layer coming as well and doing this catalysis, is called a phase transfer catalysis. And see, the reaction happens here in between these two, and that is actually the reason of giving very highly enantioselective reactions. Coming to the next part, what we call is cinchona alkaloids. So you can see that it's nothing but comes from natural products. Okay, cinchonine is about $22.9, 25 grams, and cinchonidine 22.70, but actually there are fantastic natural products having chiral centers here. Okay, fantastic backbones achieved from natural products, and you can use it not only catalyzing your reactions but also inducing enantioselectivity. See, fantastic starting in 2004 by O'Donnell. So this is, I think, the first report what has come to us about cinchona alkaloid catalysis. People did not name that time as organocatalysis. They just told that this is cinchona catalysis. If you go through his review in Accounts of Chemical Research, he mentions that cinchona catalysis. So this is where I discussed with you how synthesis progressed throughout the years. So this is where we should understand, we should know the timelines, how the chemistry has evolved out. So it's 2004, and it was not List nor Macmillan. It was this guy, okay, who started the concept of actually organocatalysis. He termed it as, you know, cinchona catalysis. Now let me come to this. he immediately prepared 3 catalysts. The first one he termed as generation 1. We call generations like we feel no? That our grandparents, then our parents, then us. So these are what generations, what we mean when we talk about our society, our families. But in catalysis 2, we term them as generation 1 catalyst, generation 2 catalyst, generation 3 catalyst. We know about ring closing metathesis. What is the catalyst? Grubbs catalyst, Robert Grubbs, who won the Nobel Prize. But was that the first catalyst which was discovered? No. Before them, there were series of catalysts. Even after Robert Grubbs, Richard Schrock developed molybdenum-based catalysts, and they also used it for ring closing metathesis. So what we develop is, there is a continuous development of catalytic chemistry. Generation 1, generation 2, generation 3. The same thing happens in transition metals as well, but I feel that in phase transfer catalyst, the first one is this one, which we called as generation 1. And the second one, what they tried, particularly the Ligos group, they substituted this OH with an allyl bromide. So this is a simple reaction. If you treat this with sodium hydride and allyl bromide, you get this O allyl, and this is what is the second generation catalyst. The only difference was the allyl bond. Okay, nothing else. Now this slowly came, they thought that why not make it more bulkier so that the enhancer selectivity generates very high. In that case, they replaced this benzyl with what? What is this? What is this backbone? What is this backbone called? Anthracene. So, see, I always tell my students to visualize molecules. Can you visualize this molecule? So, you cannot visualize molecules methane like CH4. The moment I say CH4, what should a synthetic chemistry student feel? It's that pyramidal geometry, right? You should not write CH4. The moment we say methane or ethane, what should come to your mind? You know, the staggered formula, right? Similarly, can you visualize this molecule? So complicated, so big. Like this part is actually covering, so there is a small cavity inside where the reaction should happen. This way. So we have to visualize the organocatalysts. These are the cavities, we generate the cavities so that the enhancer selective transformations happen inside. Okay? So I think that these 3, first one is the generation 1, second is an allylated molecule which we call as generation 2, and the third one they replace the benzyl with an anthracene and we call it as the generation 3 catalyst. These are all based on the Syncona based for phase transfer catalysis. Now let us see the first use by Donald. See, fantastic, JAX 1989. You see the enhancer selectivity. What they do, they go for a substitution. They take an imine carboxylate, use generation 1 catalyst, simple base like sodium hydroxide, dichloromethane, room temperature 15 hours reaction. No high temperature involved, no exhaustive condition involved. Reaction in a phase transfer system where you have DCM and sodium hydroxide in water, and you use this catalyst, the generation 1 catalyst, and you get a yield about 95%, but 64% enhancer selective excess. When you crystallize it, when you crystallize the molecule and deprotect the ester, you get an yield of overall 50% and very high enhancer selectivity, 99%. See, we generate this molecule, but there is no metals involved. Did you find any metals here? No metals. No metals, room temperature reaction, organocatalyst. Organocatalyst means very small use of this catalyst. I have not given you the catalyst amount. I did not mention the mole percentage because they have also not mentioned, but what I feel is it's very less amount they have used. But see the overall reaction, 99% enhancer selectivity. Even we struggle. Even in today's day, when we try to develop asymmetric reaction in our laboratory, it's very tough. We struggle to get 80% enhancer selectivity with all modern instruments. But you see, 1989 in JAX with the first generation catalyst, he gets an enhancer selectivity of 99%. Very, very fantastic results, I feel, in that time. Now, when he does the same reaction in generation 2 catalyst, see, just remember, we use an allylated one in this case. So he tries this reaction with generation 2 catalyst, 95% yield, 81% enhancer selectivity. There is a catalyst, and you can see that what I mentioned is an experiment 1, 2, 3, 4, 5. When they take the catalyst like tetrabutyl ammonium bromide and there is no benzyl bromide, the product is 100%. The racemization percent is 0. Generation 1, generation 2, generation 3. What they want to say is that the racemization study to detect what is the active catalyst species, and they end up with nothing. See why this table is given. So we do the reaction. We do the reaction here. But how does the enhancer selectivity come? How does the enhancer selectivity arrive here? 81% enhancer selective. How does the reaction go? So what I mean to say is that when we started this chemistry, when we started the organocatalytic chemistry across the globe, what appeared to us was it's not a simple carbocation, it's not a simple carbon ion, it's not a normal simple iminium ion intermediates. The reactions, we knew only few things. The reactions were happening in catalytic mode, there were no metals, reactions were happening in water, inside the phase, but how does the reaction happen? How does the enhancer selectivity come up? We were not sure about it. What is the mechanism? Because we need reactions, we need understanding of mechanisms. That what is, so in an SN1 reaction, what do you generate? You generate an SN1 reaction. SN1 reaction. The intermediate is a carbocation. How do you understand? You understand with a reverse observation. What is the observation? You end up with a racemic mixture. Okay, in SN2 reaction, you don't get a racemic mixture. And we think about, okay, this is the first one is an unimolecular reaction, the second one is a bimolecular reaction. But what type of molecularity or what type of mechanism was actually operative in organocatalysis? We didn't know. We did not know what is the intermediate. We only knew that, okay, we are using generation 1 catalyst, we are getting this yield, we are using generation 2 catalyst, we are getting this yield, this is the enhancer selectivity. Now, the third generation, please see, Corey comes up. So I told about you in Corey, he's one of the big shots, Nobel Prize winner, fantastic contributions in organic synthesis. So far, Corey was not into organocatalysis, but when he found that, okay, some other groups like LICO are very prominent in organocatalysis, he comes in with his first publication in 1997 in JACS, and this is the report what he shows, that the first one, same transformation, you see the transformation, you have the imine, you have an alkyl bromide, and you have the catalyst. In one case the catalyst A, what they use 10 mole percent, and the other case is the catalyst B, they use the same 10 mole percent, 50% of potassium hydroxide, toluene, cesium hydroxide, and DCM. Room temperature is 18 hours. Coase condition shows minus 78 degrees centigrade, 23 hours. LIGO says 94% enhancer selectivity. Coase says 94% enhancer selectivity. 68% is the yield, 87% the yield. Now you tell me which is better. LIGO, a young person that time. Coe, a very big shot in Howard University. And they propose a simple reaction. Catalyst A by LIGO, catalyst B by Coe. But what is the difference between catalyst A and catalyst B? What is the difference between catalyst A and catalyst B? Is there any difference in the counter cation? What is the difference? In the first case, you have. Can you find the difference? Very interesting chemistry. Why did I pick up? Very interesting chemistry. Try to understand. The backbone is same, but you change the anion. In first case, the anion is. The second case, see, you try to feel the chemistry. In one side, when organocatalysis started, don't know what intermediates they're following, because we read what? We read traditional intermediates, carbocation, carbanion, okay, nitrines, carbenes, and suddenly we come up with a reaction where we find that there is a catalysis, and that's done by another organic compound, and they are showing fantastic observations like the one which is reported by LIGO in one side has a chloride anion, and the other one reported by a very big shot like Professor Kore, and his change is just bromine, and there is a competition between these groups, and both of them report in 1997, right? One, LIGO, young guy, so it could not publish in a very big journal. Okay, it goes in Catalan letters, and Kore, his name is sufficient, goes into JAX. Okay, but my question to you is, what is the better reaction? LIGO is the better reaction, but it went to, okay, and what do you think is not a good reaction goes into JAX? Okay, so it's not 2025, it was also there in 1997, and it will also be there in 2050. So you should accept it very sportingly. Okay. Now, but the other important thing is that when we find that a 50% KOH and room temperature reaction does fantastic enhancer selectivity, only the yield is little bit less. Whereas why do you use a lot of energy, minus 78, 23 hours, to give us 94, so same enhancer selectivity, a little better yield. But that's okay, that's fine. But organocatalysis is something we should look into in a different eyesight, because here not only the cation but also the anion was playing an activity. We normally leave it, whatever you have. We don't think about bromides, we don't think about anions like fluorides in the system, and we concentrate only on the cationic part. So this is a message to all of you who have been working now in research labs, in industrial labs, and also in future. Don't leave a reaction just sir ye nahi gaya hai. If this type of change in organocatalysis or this type of beautiful reactivity can be seen by just changing an anion which is quite far from your reactive center, then you should try all sorts of variations in any methodologies or any total synthesis you're working on. So this is my message to all the students, that a small change, what we cannot expect, is also does it. Okay, you did not follow one more change in the catalyst. One had a double bond and the other did not have a double bond. But again, it's a straight one. It's a straight 2-carbon system. So it's very tough to explain that what actually catalyzes, but later on it was cleared, but it's definitely the anion catalysis. Okay. Now, to understand the systems, there was a lot of deliberations that how these reactions are catalyzed, what is chlorine and what bromine, and there's some explanations which are also clear in these 2 papers, but there is a long explanation. It's nothing but due to the cavity where inside which the reaction happens, and they say that we are really sorry to make you that we are unable to understand that how chloride and Br minus is actually giving so much of difference in the system. So this remains unexplained, even if both this group has written 1 or 2 reviews on this article. Okay, but one thing was understanding the ion pair. So there was something which was playing the cation and the bromide interaction, or the cation and the chloride interaction. So there was something what was playing the ion pair interactions is very easy. Where it was something which was I'll say that very important for understanding this enhancer selectivity. So please take home a message from this reaction that it's not only the main reactive center which plays an important reaction, important decisive systems in your reaction, but also the anions which are playing very important. So if you set a series of reactions to understand your systematic methodology, I will suggest you, even in photocatalysis, you should try with systems which have different anions. Okay, it's not only the cations. Okay. LIGO has been, as I told you, that we all know about Macmillan and Benjamin list, but I think LIGO's contribution was immensely powerful. You can see that he has prepared a huge library of his organocatalysts, and he does it, or he starts from this, this type of tribromo biphenyl type molecules and go for a boron and palladium couplings to finally give up this type of 7-membered ammonium counterparts, and the term is catalyst. I've given as catalyst A, but you can understand that they can have a series of diff, they can change the substitutions, the R's, and they make a lot of libraries. Okay. So, now the next part. So, see the transformation. Okay. 10 mole percent. This 10 mole percent. Just see this. Catalyst A as 1 mole percent. So, see the change. 1997, 2023 and 2022. So, we come up a place where we have started developing in the organocatalysis fragment. How do you develop? How do we say that we are developing? We say when developing when we find that we are using very minimal amount of catalyst. So, there should be a mark. Often students, and when we deliberate lectures or we compete, we give competing lectures with other faculties, we try to establish ourselves. How? We say that our systems, our synthetic methodologies, our tolerance is better. But what is the quantification? When can I say that I have done the same natural product is done by Professor X and Professor Y, and I say that I am the best? How do I prove that? I prove that saying that when I use the minimum amount of catalyst and my overall yield is very high and the enhancer selectivity is also very high. But the main decisive factor is what amount of catalyst you are using. So you see that now they have come to a place where the organocatalysts, so organocatalysts, as I told you when we started, enzymes, less timing, more amount of enzymes. See, I have a whole series, I can deliver a lecture on enzyme catalysis. What type of enzyme catalyst we use? We can use whole cell catalysts. We can isolate enzymes. But you see how much of enzymes we require for a transformation of 1 gram material. You can visit industries like AstraZeneca, Novartis. You can see that they have series of labs in enzyme catalysis. But how much of enzymes they use? Huge amounts. Ultimately, in the whole 2 days or 48 hours reaction, you will find that 1 gram of material has been converted with very good enhancer selectivity. No doubt with enhancer selectivity in enzyme catalysis. But time, 48 hours, 72 hours, yield 20%, 30%. So, how do we develop? We develop when we say that we have developed in a sense that we have come to a place where we are using a catalyst with 1 mole percent. 30 degrees centigrade, room temperature, close to room temperature in some cases, and delivers complete conversion of the product. And this was done already in 2002 by this group, by LIGO, okay? Not only this, he tried to manufacture different fragments. He incorporated CF3s, trifluoros, tertiary butyls, methoxides, try to increase bulkiness, molecular complexity. So he wanted to increase complexity in his catalyst. And you see 97% enhancer selectivity, 92, 86, 55, 89, 95, it's fantastic yields. But again, it's not the carbocation chemistry, it's not the carbon ion chemistry. If you ask me, so why did it go? When I take ethyl, you can ask me, so when I change the alkyl group to ethyl, you see that enhancer selectivity reduced to 55%. Why did it happen? And frankly speaking, at this moment, I am not in a position to answer this, and neither the authors, because they have tried to explain using ion pair interactions, because we cannot tell any other mechanisms involved in such organocatalytic reactions. There's something what we achieve after we do the reaction. We try to explain, but exactly it's very tough to explain that why we change R with tertiary butyl, very high yield in 89%, enhancer selectivity is 97%, the yield has not decreased so much, but why did we get 55% enhancer selectivity? That remains a question. Again, if you just change the alkyl halides, for example, benzyl bromide, naphthyl, 2-naphthyl bromides and many others, times enhancer selectivity yields, you see that it comes 71%, whereas in this case it's 100%. So tabulation of reactions in organocatalysis like this, it's we don't have a pattern. You cannot expect a very dedicated pattern as we talk about stirring hindrances in our classical chemistry. We cannot explain in that way in organocatalytic approaches, particularly when we talk about this type of very old catalysts. Okay, we know. So what is a Michael reaction? We talked about Michael additions yesterday. So this is a very nice fragment, I would say. What is this? It's an alpha beta unsaturated ketone. Why this is important in chemistry? Because I told you yesterday that it's a fragment where we can do 1,2 additions, we can do 1,4 additions, and you have the independence to add 4 carbons all together. See what we do. When I started my lecture, I told you that we are very powerful people. Why? We can make molecules, we can give birth to molecules. And how do we give birth to molecules? We need fragments, we can add them. We know the art how to add them. We know the art how to make rings. We know the art how to open the rings or how to close the rings. Okay. So we know it. But again, we also need, as I told you about toolbox, we also need fragments. One fragment is this, alpha beta unsaturated. The other fragment is cyclopropanes. We can open it very easily, add it anywhere. So this type of fragments, I feel, is very nice, and we should give a special consideration in creation of chiral centers in asymmetric Michael reactions. The same was done by this group, by LIGO, and he says that if he adds 1 mole % of his catalysts. So how do you do a normal Michael reaction, MSc students? How do you do? You need a base, right? Why you need a base? We need to generate a carbon ion, and that adds to 1,4 or 1,2. If it's Michael, it's 1,4. But what type of base we need in Michael reactions? Do you remember? If you want to generate a carbon ion, for example, alpha 2 and carboxylate ester, what base you use? Very non-nucleophilic, it's fine, but very strong base, isn't it? Like potassium tertiary butoxide. So potassium tertiary butoxides, and what is the condition? You cannot open potassium tertiary butoxide like this and open it. You can do it, but there are a lot of problems, like it absorbs water very fast. So what is the best way you do? To generate freshly prepared potassium tertiary butoxide, you have to cut potassium. How to cut potassium? Can you cut the potassium like this? Like you cut a cake? ऐसे काटते हो? कैसे काटना है? Very tough. How do you do? We hold it like this, put it inside a hexane or plate ether with one hand, and you catch another hand or knife, put it, and then the moment the solvent goes, what happens? And I have the very worst experience, I was admitted in 17 days in hospital during my PhD. I had a skin grafting, skin from here to there, because there was an explosion. And there was also a potassium tertiary butoxide. So it's not easy. So please, why I'm telling you this story? Because it's not easy to do this classical reactions. For example, this Michael additions with potassium tertiary butoxide. I'm talking about, my accident was in 2008, and that time we did not have freshly available potassium tertiary butoxide what we have available now from Sigma Aldrich. So I remember that it was a festival day, and I came to my lab with my slippers because I thought that I will just put the reaction and go back to my hostel, and I went to the hospital. So so it was severe problem, but that is okay. That's a part of hardships we take in research. That's okay. But the thing is, what I want to make you realize is that the classical chemistry was not so easy. We needed, for a simple reaction like this, we need to have such reagents, and the availability of reagents were not so easy, unsafe, very, very dangerous to use, but we were compelled to use. See, I was doing a 1 gram reaction. But just understand, if I need to do a 100-gram reaction with potassium tertiary butoxide, in those days, how much of potassium I need to cut and set this reaction. So very, very unsafe. But you see, when organocatalyst came up, It became so easy. And they did this asymmetric Michael addition, cesium carbonate, very stable base, no need of potassium tertiary butoxide. Just 1% of Ligos catalyst does an asymmetric Michael reaction with very high enhancer selectivity, in some cases with a pure one definitely sometime, but that was developed later on. But you see, 94% of yield with 94% of enhancer selectivity, particularly the enhancer selectivity was really nice. But again I tell you, tertiary butoxide, tertiary butyl as substituent, you may ask me, sir, why it is 60%? I do agree. I told you that it's all about the ionic interactions, the cavities where the reactions happen. And it's very tough to exactly explain the changes in the substitutions and this enhancer selectivity. So 45%, certainly it goes down and it goes up here with benzyl, it goes down with tertiary butyl, enhancer selectivity goes down. So how do you explain? But that's not the important. The important chemistry is that what we use and what we used to use. That is important. So we rise fantastically on the field of stereoselectivity and also ease of reaction when we think of organocatalysis in this case. Okay, this was a time in 2005 when one of the most lovable persons, I met Morocco in numerous occasions, fantastic thin and lean person with long hairs. Okay, Morocco is from Japan. Kiji Moroka, full name. He started his chemistry as an independent researcher with his numerous backbones, ammonium backbones. But this one, I tell you that even anyone in the world is now working on this catalyst, or not catalyst, but the backbone. The backbone he made. This is the backbone what he has made of an ammonium salt. Fantastic work. This backbone is one of the best backbones where we can induce enhancer selectivities in any reaction. The moment you read his work, okay, it's something like this, an eye-opening for you. Why do I say it? Because we all work, or we will work in organic synthesis laboratories or any synthetic laboratories, and in any case, if a situation comes to you, your group leader or your boss comes and says you that you need to do this asymmetric transformation, and I want a fantastic enhancer selectivity. The first thing which comes to our mind as a student is, sir ने तो ये बोल दिया, लेकिन मैं शुरू कहाँ से करूँ? I mean to say, which ligand I'm going to use? Are we going to use BINAP? Are we going to use synchronine? Are we going to use anything else? But I tell you that this is a fantastic backbone. It's majorly very, very successful, as a whole, as inducing enhancer selectivity into any systems, any reactions. We have seen that. So it was the first report in 2025 in Pure Applied Chemistry by Keiji Morocco, where he showed these wide sections. He's just synthesized these molecules with very nice enhancer selectivities. He showed how we can make this backbone. We did not know what he has made, but he explained the structures. He told that this is the first time where we synthesize some ammonium phase transfer spiro type of catalysts, and they gave this nomenclature and published in JACS in 2023, but they did not show the application. They just synthesized them and put it through. Later on, this has become, I think, one of the most stalwart catalysts for inducing enhancer selectivity. Pure Applied Chemistry in 2005, one of the first reports where they were working on the protein chemistry, and they show that they use first time this backbone ammonium bromide, or I would say today's day we call it Morocco catalyst, and in alkylating this position of imines. See, we had also used in earlier cases, we showed this reaction, but you see the substrate scope. He has added allyl bromides, propargyl bromides, benzyl bromides, many bromides are alkylating this position. Potassium hydroxide, fantastic reaction with water, But one thing I did not understand in the reaction, why did they use argon? Why did they use argon? Because normally when we say that it's 50% of aqueous condition, okay, it's already water in it. And when there is water, there's no need normally to add argon. But they have used argon as an inert atmosphere. So this is a part which remains unclear to me after all these 20 years, that why exactly Morocco, because this is stable, this part is entirely stable in water. So actually they did not need to use argon, but I possibly feel often what happens, our students are overcautious. Even they don't need nitrogen, they add nitrogen in the reaction so that kuch kharab nahi hoga. So it's something like this. So they should have understood that they're using, or the student should have understood that using aqueous potassium hydroxide. So when you are using water in it, so there's no need to make it an inert atmosphere. But however, the enhancer selectivities in all cases, just see 99, 99, 99, 96, 99, very, very high enhanced selectivity. So I think this was one of the first applications where we use an organocatalyst to go for an alkylation of a glycine, and it gives us 98 to 99% enhancer selectivity. Catalyst used is 1 mole percent. Not only this, they have also used it for synthesis of pharmaceutically important natural products like ACE inhibitors. You can see they have done multiple step reactions, finally delivering this inhibitor with fantastic yields and enhancer selectivity. Okay, fine. Morocco goes on high, and now he comes up in 2005 in a report in Agrivende where they say that we make it unsymmetrical. Initially it was a symmetrical spirocatalyst. So if you just compare with this catalyst, see, we have similar backbones in one side, only there was a change in the fluorides. Now they say we come up with a more efficient catalyst and we have long chains like this. They describe it as more efficient catalyst. Why? Fantastic structure. You can see that they are well established structures, crystal structures, but they say that we get 98% and 99% enhancer selectivity published in Agrivende in 2005. But how it is superior? How this catalyst is superior? Same reaction, same alkylations, they call it superior. Kyun? Where? So we come back to the original thing what I say. When we say that we are developing, we say that we are developing when we say that see the catalyst amount they have used. How much catalyst amount they have used? 0.05 mole percent. You remember when we started, it was 10 mole percent Syncona catalyst. Okay, 1978, 2020, 2005, Morocco comes up in Japan with a system like 0.05 mole percent published in Agrivende. So just see the development. Okay, just see the development through 25 years. We come up with a very fantastic catalyst in this type of alkylation with very high yield and very low, catalytic amounts. Okay, but again, this is what they mention under argon, but they use 50% of aqueous potassium hydroxide. So that is somewhere we need to think. Okay, lot of other reactions what they mention throughout the chemistry. So Morocco had one of the biggest groups in Japan also till now. I think in any time not less than 60 students work with him. Okay, very, very big group in Japan. So lot of chemistry. In all cases they use 1 mole percent of catalyst delivering all these shots of alkylation, and this is an example where they show dialkylations as well. Why this is important? So let me ask you a question. Just forget it. If there is 2 hydrogens, do you have a reaction where you can do dialkylation in one step? Not step by step. Normally what do? We use sodium hydride, okay, or potassium tertiary butoxide. But have you tried this reaction any time? I'll take an alpha beta unsaturated ketone. There is a CH2 and this methylene. I'll alkylate all the 2 hydrogens in one shot. Very tough to do. Not possible. It's not done. You need to alkylate it first, one step, then you need to do workup, you need to purify in column, you need to characterize it, and then go for the second step. But in this case, Morocco says that, or he proves that his catalyst, which is catalytic with very high enhancer selectivity, goes for dialkylation, where I need to alkylate a CH2, which is alpha to any ester or whatever it is in one step, dialkylation. So you should mention the Morocco conditions, okay? Very good. Now, conjugate additions to alpha beta unsaturated ketones, okay. Have you done any reaction in nitromethane? So when we add nitromethane to any aldehyde, what is this reaction called? Sorry? Nitroaldol reactions. Okay, nitroaldol reactions are very good reactions to incorporate nitrogen into the systems because they're efficient, very fast, very reactive, and can be manipulated to many other nitrogen systems like amines and amides. In the same direction, Morocco try to find out if they can add this nitro backbones into the alpha beta unsaturated systems with their catalyst. And they found that yes, it's definitely occurring, but a mixture was available like 96%, the syn isomer, and also the 4% with anti. It happens to be in minus 20 degrees centigrade. So this is another functionalization what Morocco uses. Now, what is the name of this fragment? There is 2 nitrogens and 1 carbonyl. Any idea? You have something called, the nitrogen system. So, what will be this fragment called? Fragment. This fragment, urea is a molecule. Okay. What is this fragment called? Carbonyl, N in one side and the other N in other side. Urea is a molecule. What is in urea? NH2? CONH2. So I want to understand that if you remove one hydrogen from one nitrogens both sides, what is this called? What is lactam? What do you mean by lactam? There's a ring, there's a CO, and there is NH in one side. It's a cyclic amide, right? So now in the cyclic amide, carbonyl, nitrogen, carbonyl, carbon. Now this carbon I am replacing with another nitrogen. What I will call? Okay. So important question for examination. Okay, try to find out. So why this is important? Because we have found that in all rings, if a system like this happens, or if you get a moiety like this, carbonyl, nitrogen, that's very common, lactams, another nitrogen, it shows fantastic cell adhesion inhibitor activities. This is a very prominent cell adhesion molecules, and Morocco came up with this biaryl catalyst. They just increased this side. So they made this biaryl backbones. See the fragment changes. This was one fragment. This was another fragment. This is another fragment. So they're changing, they're playing with the catalyst. This is what you're doing. You're playing with the catalyst. And they're showing one by one, and all in good journals. This came in tetrahedron, not so high, but it's okay. He published Angle One Day, Pure Applied Chemistry, many things. He's just playing, what I feel. So you should enjoy the chemistry when you read. He's playing with the catalyst, changing the fragments, and using it in creation of very high yields and by enhancer selectivities when they do this reaction. Okay? Now, we come to the next part from PTC to enamine catalyst. What is what is an in and amine? What is an in and all? What do you mean in all? What is an in all? In all. In amine. So in all you have a alkene and all or alcohol, right? And in amine you're having an in and amine. Okay. So both this enols, you all know that how enol is important because we all know about aldol reactions, enantioselective aldol reactions. The best way to generate a CC bond without involving any metal catalysts. Okay, and that's true enantioselectively. In similar pattern, when we come to in amine catalysis, I think this is also done tremendously beautiful reactions. So if you see that how an enamine generates or catalyzes, so you start from a carbonyl and you generate an imine, you can react with any amine like this and generate an imine, you lose a proton, comes to an amine again, there is another fragment which is a double bond, there's an addition to this carbon and then you generate this fragment and the amine is freed again to go for another cycle. So this is what is a very simple explanation how an enamine catalysis can happen. It can come from your organocatalyst. Okay, fantastic simple proposition. So once I was attending to one conference in SIOC, Shanghai Institute of Organic Chemistry, and there I think Professor Macmillan was giving the end lecture and Dean Toste, Professor Toste from Caltech was giving the inaugural lecture. And Professor Toste started the conference in SIOC saying a word called perception. He told that I feel whatever I have done, it's just because of perception. On a lighter note, when Macmillan ended the conference, so one was giving the inaugural address and one was giving the ending address, fourth day. Then Professor Macmillan was also there in the first day and he was listening what Professor Toste was giving. And Professor Toste said that I worked with organocatalysis, I worked in gold catalysis and I feel that everything you do is perception. Macmillan in the last day said, not pointing him but to the audience, that someone said that the perception is the only thing that has made us work. But I feel it's not perception, it's only what? It's only dedication to work, nothing else. So the first, see, there is competition as I told you yesterday. There was competitions to tell that who has given the first arrows in chemistry. There was competition to first who will announce the correct steroid nucleus 50 years ago in MIT. There are competitions till now. So one person thinks, one stalwart thinks in chemistry that it's only perception, thinking that the mechanism should work like this. Whereas the other person thinks, no, it's not perception, is that how dedicatedly you are working in your fume hood. That gives you the results. Anyway, we feel both are correct. So this was the perception when enamine catalysis started. Okay, so the first one came up with some unknown groups, I think, Richard and Parrish. They say that they claim to have the first proline catalysis in very beginning, 1971, and they show that they use this proline 3% for an aldol type of cyclization. So it's a proline catalyzed, they generate the cyclic diketone from this type of 6-exocyclization, where they say that it's S-fluorine they're using as an organocatalyst, fantastic 6-exo with 93% enhancer selectivity, and also they use similar conditions where they show 71% enhancer selectivity. Yeah, okay, fantastic. So this was a starting where they say that this is nothing but an enamine catalysis and it's catalyzed by fluorine 3 mole percent. Not only this, now big shots something comes up, what I feel, and then some big shots start putting up efforts. So this is the first thing. List got Nobel Prize in organocatalysis. So his first reports were this. In 2022 and 2024, he reported the same enamine chlorine catalysis to generate this type of aldol type reactions. Yields were moderate, 60 to 90%. He generates this, he adds these aldehydes into this carbonyls using S-fluorine. 10 to 30 mole percent they used. Very high mole percent of porine catalysts. List group, very big group in Max Planck, right? Very big group. So they started with the good catalysis, but the only thing was 10 to 30 mole percent. But I already told you that we say that we want to measure the catalyst amount when we talk about this type of catalysis. Okay, so 5 to 35% chlorine catalysts in the next case. Okay, although the enhancer selectivities were good, 90%, 99%, but again, the results indicated 5 to 35 mole percent of B used. See, now you tell me, who was best, LIGO or LIST? You remember the person LIGO started organocatalysis in tetrahedron papers with 10% catalyst, and LIST starts a chlorine catalysis. So LIST was not the first. I wanted to highlight. LIST started chlorine catalysis, but LIGO started organocatalysis in 1978. LIST came much later in 2002, where he showed chlorine catalysis, but again with a very high amount of catalysis. Okay, now directly coming in, I don't explain because I personally feel that there are much other contributors, and I will show you that how others have contributed a lot in organocatalysis. Fantastic report in Science by 2002 by none other than Jacobson group. Okay, very nice report. Why this was important? Because this is the first time when someone said openly that the organocatalyzed reactions are mimicking natural enzymes. Okay, so I started with what? Simplified enzyme catalysis, right? But all this, we started with 1978, catalysts going on, organocatalysts being worked, LIGO, Morocco, LIST coming in, but no one said that this is mimicking enzymes. Two, when he...
So later on, inspired from his teachers, as has been expressed by him in one of the recent interviews, he went on to become a lecturer at Patna Science College, where he stayed for 15 years as a lecturer and reader. It was during this period that his very well-known book was written and published. He also discussed this thing with our students of IIT Indore in a separate interaction. So after this, he resigned from Patna Science College in 1994 to join as an assistant professor at IIT Kanpur. And he also mentioned in that interaction, when he was about to be promoted to be professor, so he resigned and joined as assistant professor in IIT Kanpur. So that in a personal interaction, you should ask what motivated him. Okay, that is also interesting. So his research spans across both the theoretical and experimental aspects of study of condensed matter systems using methods and techniques of nuclear physics. So you can see, the interdisciplinarity already is encoded. So he has published more than 130 research papers in journals having high scientific repute, and moreover, these have received over 1700 citations in total. Professor Verma actively works towards making physics reachable, understandable, enjoyable for the aspiring learners. As an effort in this direction, he has designed more than 600 low-cost experiments for the classroom setup. As all of you might have seen from the poster of the talk today, he will be shedding light on some of these. For someone who wants to follow the experiments in their technical details, they can be found on his personal webpage. And Professor Verma has also founded the National Anvashika Network of India, NANI, a flagship program of the Indian Association of Physics Teachers, IAPT. NANI conducts the National Experimental Skill Test with the help of several Anveshika coordinators from all over the country. This competition is awaited with great enthusiasm by the physics community of India. As a being who has spent the majority of life and career in enhancing the position of physics research in India by staying both on the main stage and backstage, that is, through outreach to students and thus inspiring them to choose physics as their career choices, as Professor Verma himself did, it is natural that his contribution be recognized as an esteemed level. Professor Verma was awarded Maulana Abul Kalam Azad Shiksha Puraskar in 2017 by the Bihar government, felicitated by the Honorable Chief Minister of Bihar, Shri Nitish Kumar ji, for his book Concepts of Physics, and for the NGO Shiksha Sopan that has established where value-based education is given to students coming from economically weaker, unprivileged sections of the society. He was then awarded Padma Shri in 2020, felicitated by then Honorable President of India, Sri Ramnath Kovind ji, for his significant contribution to physics education and science and engineering. It must be clear by now that one can go on introducing Professor Verma for whatever duration of time they wish to, but we must respect the constraint placed upon by time. And I now request Professor Verma to kindly deliver his much awaited Institute Public Lecture remarks. And I believe I was brief. Thank you.
Thank you, sir. Just before the start, I would request sir to present a memento or planter to the sir to welcome him.
Okay, so thank you very much for your kind introduction and conducting this whole show. Okay, so there's a poster. वो poster लगाना था. So you saw the poster, right? Did you find anything unusual in the poster? Do you find something which is special? How many of you are from schools? Okay, quite a lot. So observe this poster, 15 seconds more, and if you find something unusual or something which should be talked about specially, क्या फिर से जोर से बोलना? Educational experiments. Okay. Huh? Yeah. So what is wrong in that? My educational experiments. That seems okay. उसमें कुछ है क्या? आप बताओ, कुछ क्या देखा आपने उसमें गड़बड़ या unusual? यहाँ लिखा है 3:30 PM IST और बगल में घड़ी बनी हुई है और उसमें 4 बज रहे हैं। तो आपने शायद एक्सपेक्ट किया होगा कि 3:30 IST, तो 4 बजे से पहले क्या शुरू होगा? इसलिए आपने पहले से ही 4 बजा दिए। तो ऑब्जर्वेशन ना, साइंस अगर करना है तो सबसे पहली चीज होती है ऑब्जर्वेशंस। ऑब्जर्व कर, जिस चीज को मैंने देखा, सबने देखा, लेकिन मेरी आंखें अगर थोड़ा अंदर घुस के देख रही हैं तो फिर मैं साइंस करने के लिए उपयुक्त व्यक्ति हूं। और अगर मेरी आंखें नहीं देख पा रही हैं तो या तो फिर आंखों का थोड़ा इलाज विलाज करके देखना शुरू कर दो, और नहीं तो फिर देखना बंद ही कर दो। साइंस करो ही मत, और कुछ करो। दुनिया में साइंस के अलावा बहुत कुछ करने के लिए है, और ओवर एम्फसाइज साइंस को करना खतरनाक है। क्योंकि जो दैट अच्छा, हिंदी किसको किस आर देयर पीपल हु आर नॉट कंफर्टेबल इन हिंदी? ये बात मैंने अंग्रेजी में बोली है। अगर मैं ये हिंदी में बोलता हूं तो इसका कोई मायने नहीं था। So it seems that everyone is comfortable in Hindi. So whenever I switch to Hindi, there should not be, I should not be conscious about it. Okay. तो जो कोमल भावनाएं होती है ना, मनुष्य के दिल की, जो दिमाग की जो कोमल भावनाएं होती हैं, जिससे सोसाइटी चलती है, जो हमारी जो सॉफ्ट, लोगों के साथ प्यार करने का, लोगों के साथ अच्छा व्यवहार करने का, खुद को खुश रखने का, ये जो कोमल भावनाएं हैं, ये साइंस से आती हैं, साइंस से भी आती हैं। लेकिन जो दूसरे आर्ट के फॉर्म हैं, म्यूजिक है, डांस है, तरह तरह का स्कल्पचर है, ये जो आर्ट के फॉर्म हैं, वहां से और भी ज्यादा बढ़िया आती है। तो साइंस को ओवर एम्फसाइज भी करने का जरूरत नहीं है। अगर मेरे को साइंस नहीं पसंद है तो नहीं पसंद है, कोई बात नहीं। लेकिन अगर करनी है साइंस, देन यू हैव टू बी ए वेरी गुड ऑब्जर्वर। एंड वंस यू आर ए गुड ऑब्जर्वर, देन देयर मे बी मेनी क्वेश्चंस व्हिच विल कम इनटू माइंड। तो जैसे अभी कह रहे थे अपने डॉक्टर साहब कि डिड यू आस्क ए गुड क्वेश्चन टुडे? वो सवाल है, डिड यू आस्क, डिड दैट गुड क्वेश्चन अकर टू यू? तभी तो पूछोगे ना, वो अकर किया क्या? और वो अकर तभी करेगा व्हेन यू कैन ऑब्जर्व थिंग्स विथ दोज एक्स-रे आईज। ऑलराइट, सो लेट्स कम टू माय एक्सपेरिमेंट्स, माय एजुकेशनल एक्सपेरिमेंट्स. So in fact, there are this, when I was preparing this PPT during my transit from Lucknow to Indore, 2 hours flight. So later on when I finished, I found that it had 61 slides. Okay, and I had no time to revise and reduce. So there are 61 slides, but देखो हम कितना minutes उस पे लगाते हैं मालूम नहीं मुझको. All right, next. So this is part 1, which I have written non-intentional experiments. My experiments in education, but this in part 1, I did not intend to do these experiments, but finally I could do that. Yeah, next. Okay. So the first experiment is that there was no schooling for me and no homeschooling, nothing. Till the age of 10 years. At the age of 10 years, first time I was taken to a school. Before that, my father taught me some arithmetic, basic arithmetic, and some English, little bit words and little bit sentences, small, say, I go, you go, he goes, those kind of sentences, because my father himself never went to a school in the whole of the life. Okay, so I was not taught in the school or in home. And then I was taken at the age of 10 years for a school, Naveen Ganesh Pathshala, and then I was instructed by the principal of that school. In his chamber, he asked some questions on mathematics and Hindi and English and some general knowledge type or something. So he did some 15-minute test and then declared that he is fit for class 6, admit him in class 6, and I was admitted. Now this experiment, which I did not plan to do, the results were fantastic. The results were fantastic. आपको बताते हैं कैसे. Next. Okay, so no emphasis on English or English medium, nothing like that. Naveen Ganesh Pathshala was Naveen Ganesh Pathshala, and my father's name is also Ganesh. So probably that is why he took me to that Naveen Ganesh Pathshala. I don't know. Okay, next. No tuitions. Next. Right. Now, because till the age of 10 years, skipping all the classes 1 to 5 and absolutely nothing like nursery, KG, lower KG, upper KG, etc. I learned in those 10 years at the fastest pace. So that's the result of the experiment. Okay? Now if you look at this picture, this boy, his age is some 3.5 years. Now he has started going to school in Kendriya Vidyalaya IIT Kanpur. Now is he not learning? Is he not learning the thermodynamics? That water has phases, vapor perhaps he doesn't know, but liquid phase and the solid phase. And then this temperature is very low, so it feels very cold. Is he not learning that? So learning without the school, learning without syllabus, learning without an educator. No examination, no term examination, no homework, no restrictions, no periods, 8:45 to 9:00, you have to learn English, absolutely nothing like that. So this is the fastest pace at which a child learns, and that time is before the school system takes over. And for me, that time was extended to 10 years, and so I learned so many things. I learned to observe. I learned to derive my own conclusion. There was no one to tell me the conclusions. No one told me that this is cold and this is hot and this is this and it moves this way, it moves that way. No one. So I learned all these things to think, to observe, to think, to derive conclusions, to derive my own set of rules by which the nature goes, and so on and so forth. So that was my first experiment. Okay, next. Okay, yeah, so natural way of learning. This picture is similar. Yeah, next. Yeah, press the button. Okay, press the button once again. Yes, is the same message from this picture also. So next. Yeah, चलो आगे बढ़ाओ भाई. Yeah, okay. Now learning from events is the natural strength of everyone, right? Learning from the events. Our learning starts at day 1 after our birth. And this whole learning is from the events. We see some events happening in the surrounding, and from there we start learning. The whole language we learn, right? In the first 3 years or first 2 years, the whole one language we learn. Okay? कैसे सीख जाते हैं उसको? कोई सिखाता नहीं है, कोई बताता नहीं है, कोई टेक्स्ट बुक नहीं होती है, कोई प्रोग्राम्ड नहीं होता है, कोई टाइम टेबल नहीं होता है, बट लोग बोल रहे हैं और मैं सुन रहा हूं. तो जो हो रहा है वहां से लर्न करना, ये हमारी नेचुरल हैबिट है. एवरीवन हैज दिस स्ट्रेंथ. This is our natural strength to learn from the events. Okay? And that is being tried with the machines in the name of artificial intelligence. यही करते हैं ना? उसके सामने कुछ कुछ रख देते हैं। एआई में क्या करते हैं हमें पता नहीं है। आई एम नॉट ए कंप्यूटर साइंस स्टूडेंट एंड आई इनफैक्ट आई आस्क्ड मेनी पीपल हु आर वर्किंग इन दिस एआई कि आप एक इलिटरेट व्यक्ति को बताना है कि एआई में क्या होता है, क्या बताओगे? तो वो यही बताते, उसके सामने बहुत सारे सिचुएशंस रख देते हैं, उसके बाद वो एआई जो है उनको एनालाइज करता है और एनालाइज करके उसके कंक्लूजन्स निकालता है। दैट्स व्हाई वी ऑल द टाइम डू। वो एक नाम बड़ा बढ़िया सा हो गया आर्टिफिशियल, वो तो हम जन्म से कर रहे हैं, वो तो हम जन्म से कर रहे हैं, हम शुरू से यही तो कर रहे हैं। मेरे सामने बहुत सारी सिचुएशंस है, उनको मैं देखता हूं और वहां से मैं लर्न कर जाता हूं कि अच्छा इसमें ऐसा होता है, उसमें वैसा होता है। प्रेडिक्शन भी मैं करने लगता हूं। मैं प्रेडिक्शन करने लगता हूं कि अगर दूध ज्यादा देर तक रह गया चूल्हे के ऊपर तो उबल जाएगा क्योंकि मैंने देखा है पहले उबलते हुए, तो मैं करता हूं। दैट इज व्हाट एआई इज ऑल अबाउट। मेरे को जितना बताया, लोग जितना समझा पाए एक इलिटरेट व्यक्ति को, उसके अनुसार। सो वी आर ऑलरेडी ट्रेन्ड इन इस पूरे विधा के अंदर में। चलो नेक्स्ट। अच्छा ये बताओ भाई, स्कूल वाले और कॉलेज वाले और इंदौर वाले, आईआईटी इंदौर वाले, आपने न्यूटन का पहला नियम, गति नियम, कब सीखा? 10th में, 9th में? कब सीखा भाई बच्चे लोग? 9th में सीखा। जब 9th में, क्या 9th क्लास में, है ना, स्कूल के 9th क्लास में जब आप थे 13 14 ईयर्स के, तब आपने न्यूटन का फर्स्ट लॉ सीखा। नाउ थिंक ऑफ ए चाइल्ड ऑफ द एज 2 years प्लेइंग विथ ए टॉय, ओके, एंड देन कुछ हुआ, उसकी मम्मी ने वो जो दूध पीने के लिए बुला लिया, उसने टॉय रखा यहां, दरी के ऊपर टॉय रखा और दूध पीने चला गया। दूध गर्म हो गया, अब टॉय से फिर खेलना है। वो बच्चा कहां जाएगा टॉय लेने के लिए? जहां रखा था वहीं जाएगा। क्यों? उसको कैसे मालूम कि वो वहीं मिलेगा, दूसरी जगह नहीं मिलेगा? दूसरे कमरे में जाके नहीं खोजेगा, पड़ोसी के घर में जाके नहीं खोजेगा, छत पे जाके नहीं खोजेगा, गार्डन में जाके नहीं खोजेगा, जहां रखा था वहीं जाके फिर से उठाएगा। करेगा ना? हाउ डज द चाइल्ड नो अबाउट इट? बिकॉज द चाइल्ड हैज ऑलरेडी लर्नड इफ एन ऑब्जेक्ट इट एट रेस्ट, इट विल रिमेन एट रेस्ट। वो कहीं नहीं जाएगा, वो जहां रखा था वहीं मिलने वाला है। अनलेस एन एक्सटर्नल फोर्स एक्ट। यही है ना न्यूटन का पहला नियम भाई। तो बच्चे को पता था तभी तो वहीं पे गया है, नहीं तो दूसरी जगह जाके इधर उधर खोजता ना कि अपने आप चली गई होगी कहीं, मेरा टॉय कहीं चला गया होगा अपने आप। वो जानता है, आप भी जानते थे 2 साल की उम्र के अंदर में, 14 साल के तक इंतजार आपको नहीं करना था। और वो अनलेस वाला पार्ट भी आप जानते थे। इफ द चाइल्ड फाइंड्स दैट द टॉय इज नॉट देयर, वो तुरंत जाके पूछेगा, मम्मी उठाया क्या? मैंने तो यही छोड़ा था, किसने उठाया मेरा टॉय? हल्ला करेगा कि नहीं करेगा? यानी उसको पूरा न्यूटन का नियम पता है। An object at rest will remain at rest unless there is an external force on it. तो हम बहुत सारी चीजें देख के सीखते हैं, लेकिन जब हम स्कूल सिस्टम में आते हैं तो हमें कहा जाता है कि जो सीखा उसको अपने पास रख, जो हम सिखा रहे हैं वो सीख। फिर आप उसको सिखाते हो बड़े बड़े शब्द लगा करके, और वो बड़े बड़े शब्द को लोग समझते नहीं है कि क्या उसका मतलब है, तो याद करते रटते। तो आपको लगता है कि आपने 14 साल की उम्र के अंदर में फर्स्ट लॉ सीखा है। आपने उस समय में सेकेंड लॉ भी सीखा था और थर्ड लॉ भी सीखा था एट द एज ऑफ 2 years। अभी नहीं बताऊंगा, नहीं तो अगली बार मुझे नहीं बुलाएंगे यहां पे। लेकिन 2 साल का बच्चा न्यूटन का तीसरा नियम भी जानता है और दूसरा नियम भी जानता है, पहला तो जानता ही जानता है। ओके, चलो नेक्स्ट। तो मैंने अपने 7 साल बचाए ना, आप जब 3 साल की उम्र में गए थे स्कूल में, तब से आपकी जो नेचुरल स्ट्रेंथ थी उसको लोगों ने कहा इसको अब इस्तेमाल करने का जरूरत नहीं है, अब हम जो पढ़ाएंगे वो पढ़ना। तो आपकी नेचुरल स्ट्रेंथ को दबा दिया गया। मेरे देखो 10 साल के बाद वो धंधा करने की लोगों ने कोशिश की, तो 7 साल तो सीधे सीधे बचा लिए। और छोटे बच्चे को तो आप कुछ भी करो, उसको मजबूरी है, बड़े लोग जैसा करेंगे वो करना ही पड़ेगा। उस बच्चे में तो ताकत नहीं होती है, क्या करेगा, ज्यादा से ज्यादा रो लेगा, चिल्ला लेगा। लेकिन माता पिता जो कहे करा करना चाहेंगे वो करा के ही दम लेंगे। लेकिन बच्चा बड़ा हो जाएगा तब करवाना मुश्किल है। तो 10 साल की उम्र में मैं जब स्कूल जाऊंगा तो स्कूल सिस्टम मुझे करप्ट करेगा, इसकी संभावनाएं बड़ी कम है। मैं रेसिस्ट करूंगा। 3 साल का बच्चा रेसिस्ट नहीं करेगा। तो 7 इयर्स डायरेक्टली बचाए और पता नहीं कितने साल इनडायरेक्टली बचाए। Okay, so this is the experiment that I call it an experiment because this is an experiment. जो कोई नहीं करता है, जो कोई नहीं करता मैं करता हूं, वही तो एक्सपेरिमेंट होता है ना। जो सभी करते हैं वो तो सभी को पता है, तो उसमें एक्सपेरिमेंट क्या रहा? एक्सपेरिमेंट का मतलब है कि देयर शुड बी समथिंग जिसका रिजल्ट मुझे पता नहीं हो। आप डॉक्टर के पास जाते हो, पेट दर्द कर रहा है, डॉक्टर साहब एक दवाई दिया उन्होंने, पेट दर्द ठीक नहीं हुआ, फिर गए दूसरी दवाई दे दी उन्होंने, पेट दर्द ठीक नहीं हुआ। फिर आपने अपने दोस्त को बताया कि पता नहीं क्या हो रहा है, मैं तो इतनी दवाइयां खा रहा हूं, डॉक्टर ने बदल बदल के दवाई रख, पेट ठीक नहीं हो रहा है। तो आपका दोस्त कहता है अरे उसके यहाँ चले गए, अरे वो डॉक्टर तो ऐसा ही है, वो तो पेशेंट्स पे एक्सपेरिमेंट करता रहता है। तो जब रिजल्ट पता नहीं होता है उसको कहते हैं एक्सपेरिमेंट। पूछो जितने रिसर्च करने वाले यहां पे एक्सपेरिमेंटलिस्ट, ये सारे जो एक्सपेरिमेंटलिस्ट हैं जो रिसर्च कर रहे हैं, वो एक्सपेरिमेंट उसी को कहते हैं जिसका रिजल्ट पता नहीं होता है। और ये लोग पता करते हैं कि अच्छा ये होता है ये एक्सपेरिमेंट करने से। ओके, तो ये 10 साल तक स्कूल नहीं भेजना, ये तो सब लोग नहीं करते ना। तो मेरे पिताजी ने किया और हमें उसके रिजल्ट्स मिले, वो मैं आज आपके सामने पेश कर रहा हूं। ओके, चलो नेक्स्ट। So learning is always joyful and learning is the ticket to success. आपको 5वीं क्लास में कितने नंबर आए थे, 4थी क्लास के इम्तहान में वो टर्म टेस्ट के अंदर में कितने आए थे, मंथली टेस्ट के अंदर में कितने आए थे, या 8वीं क्लास में कितने आए थे, 9th क्लास में कितने आए थे, इट डजंट मेक एनी डिफरेंस। आप देख रहे हो, मेरे को तो एक भी नंबर नहीं आया ना, मेरे को तो एक भी नंबर ही नहीं आया, मैं परीक्षा ही नहीं देता, नंबर कैसे आता? और जब परीक्षा दी तब भी नहीं आया। जब क्लास 6 की पहली बार परीक्षा हुई मेरी, तो मुझे पता चला अच्छा परीक्षा नाम की भी कोई चीज होती है। सभी सब्जेक्ट में फेल हो गए, सभी सब्जेक्ट में फेल हो गए। तो क्या हो गया? तो क्या हो गया? आज तो मैं यहां खड़ा हूं ना, आपने बुलाया इतने प्यार से। तो लर्निंग इज द टिकट टू सक्सेस। आपने अगर लर्न किया है, आपने सीखा है, आपने सोचना सीखा है, आपने सोचना, आपने देखना सीखा है, आपने सोचना सीखा है, आपने खुद से सॉल्यूशन करना सीखा है, खुद से कंक्लूजन्स निकालना सीखा है, वो लर्निंग अगर आपने की है, तो आपको ना किसी नंबर की जरूरत है, ना किसी परीक्षा की जरूरत है, ना किसी चीज की जरूरत है। लॉन्ग टर्म में जिंदगी में आप बहुत तरक्की करोगे। और लर्निंग नहीं करोगे तो ये नंबर वंबर सब बेकार हो जाएंगे। ये ग्रेड कार्ड जो है ना, जिसपे बड़े बड़े नंबर लिखे रहते हैं, दहाई की जगह पे 9 लिखा रहता ही है, और इकाई की जगह पे भी कुछ कुछ बड़े बड़े नंबर लिखे होते हैं, और कभी कभी 3 अंकों की भी संख्या लिखी रहती है। किसी काम के नहीं है वो, किसी काम के नहीं है वो, नहीं काम आने वाले। अगर आपने ये सब सीखा नहीं है, देखना नहीं सीखा है, सोचना नहीं सीखा है, तो कुछ नहीं काम आने वाला है। वो आपके 75 हो, चाहे 85 हो, चाहे 95 हो, या 99 हो, या 100, कुछ नहीं होने वाला है उससे। लर्निंग ही आपके सक्सेस की गारंटी होती है। चलो नेक्स्ट। ओके, सो वन कैन लिव कंफर्टेबली विदाउट पासिंग जेईई। ये भी एक एक्सपेरिमेंट था। एट माई प्लेस एट पटना साइंस कॉलेज there was a big environment for going for JEE. I'm talking of late 1960s. Okay, late 1960s, 67, 68 की बात कर 1967, 68 की बात कर रहा हूँ. From that particular one single college, people used to say, maybe exaggeration, but they used to say that from a single institution, Patna Science College sends the maximum number of IITians in any year. So सबसे ज़्यादा कहाँ से एक इंस्टीट्यूशन से आने वाले स्टूडेंट्स को आप देखोगे तो पटना साइंस कॉलेज विल सेंड द हाईएस्ट नंबर ऑफ स्टूडेंट्स इनटू आईआईटी सिस्टम. दैट वाज इन एयर. सही था कि गलत था पता नहीं. कहने का मतलब देयर इज अ ह्यूज एनवायरनमेंट. एवरीवन वाज ट्राइंग टू गो इनटू जेईई. बट देन आई एक्सपेरिमेंटेड. कैन आई लिव विदाउट गोइंग टू जेईई? I did not fill the form of JEE. I straight away went for bachelor's program, BSc program at Patna Science College itself. I did my 11-12 from there, and then in the same college, I went for my BSc program, BSc Physics Honors program. Okay, so that was another experiment, and yes, the answer to this ये एक्सपेरिमेंट का जो रिजल्ट मिला है, यस आई कैन लिव कंफर्टेबली विदाउट पासिंग जेईई एग्जामिनेशन. चलो नेक्स्ट. ओके, +2 कर दिया. ये मेरे कॉलेज का फोटो है. हाँ चलो आगे नेक्स्ट. ओके, फिर ये भी एक तरीके का एक्सपेरिमेंट ही था कि गो फॉर ए यूजफुल कैरियर. ओके, मैं मास्टर किया हूँ 2 ईयर एमएससी मैंने किया है आईआईटी कानपुर से, और उसके बाद वहीं से पीएचडी किया जैसा अभी बताया डॉक्टर साहब ने. और उसमें भी मैंने वहाँ पे जहाँ मैं क्लास 6, 7, 8 के अंदर में फेल किया करता था अपने स्कूल एग्जामिनेशंस में. कई सब्जेक्ट में तो फेल करता ही था, 2-3 सब्जेक्टों में. शुरू में 8-10 में करता था, फिर बाद में संख्या 5 पे आई, 4 पे आई, फिर अंत में 2-3 पर आई, और उसके बाद जा करके सभी सब्जेक्ट में पास होना शुरू किया, बहुत लेट. ओके, और लेकिन यहाँ तक आते आते, एमएससी तक आते आते मैंने 9.9 के ग्रेड पॉइंट के साथ में अपनी एमएससी के अंदर में टॉप किया आईआईटी कानपुर में. पीएचडी के जितने कोर्सेज होते हैं, हर कोर्स के अंदर में अपने को ए ग्रेड मिला, 10 पॉइंट्स मिला, कोई झंझट नहीं हुआ, पीएचडी आराम से भी हो गई. देन आई डिसाइडेड to go for a faculty position at Patna Science College. This was a big experiment. क्योंकि मेरे को सबने बोला, all my professors at IIT Kanpur, all my well-wishers, all my friends, इतना अच्छा तुम्हारा करियर चल रहा है, you should not go for a small town like Patna. क्या करोगे पटना में जाके, क्या करियर होगा तुम्हारा? You should go for some national institute. आप IIS से जाने का बात करो, आप IIT जाने, आईसेर तो था नहीं उस समय में, आप IIT जाने का बात करो. What पटना? बहुत लोगों ने मुझे समझाया कि आप अपना करियर चौपट कर रहे हो, आप बस क्लासरूम में टीचिंग करोगे और कुछ नहीं करोगे. But I took that also as a useful career. Why useful career? Because आईआईटी सिस्टम में या बड़े इंस्टीट्यूट में जो फैकल्टी का रिक्रूटमेंट होता है वो बहुत ठोक बजा करके होता है, ऐसे नहीं होता. एंड whoever is selected is a great researcher, a great scientist और a great engineer. उसी का सिलेक्शन होता है आईआईटी सिस्टम के अंदर में, ऐसे वैसे का नहीं होता है. तो मैंने ये एनालाइज किया कि इफ आई डू नॉट ज्वाइन दिस सिस्टम एज फैकल्टी, then someone else will join मेरी जगह पे, और वो someone else जो आएगा उसको तो इतना ठोक ठाक करके जांच पड़ताल करके लाया जाएगा कि कोई बहुत अच्छा आदमी ही आएगा. तो मेरा क्या रोल रहा? मैं रहूं या न रहूं, आईआईटी को तो कोई फर्क ही नहीं पड़ने वाला है. आईआईटी will always get a good faculty, maybe much better than me. But पटना जहां कोई नहीं जाना चाहता, जिसको भी मौका मिल जाए वो बड़े इंस्टीट्यूट में जाना चाहता है, तो पटना में कौन जाएगा? फिर ऐसे छोटे कॉलेजेस में कौन जाएगा? फिर कैसा वहाँ का एनवायरनमेंट रहेगा, वहाँ के स्टूडेंट्स का क्या होगा? इफ आई गो देयर, आई एम कैपेबल ऑफ टीचिंग एट आईआईटीज. If I go there at Patna Science College and I interact with the students there will be a difference. एक फर्क पैदा होगा मेरे जाने से, तब मेरा लाइफ यूजफुल बनेगा. मेरे जिंदगी से अगर किसी को फर्क पड़ता है, दुनिया को फर्क पड़ता है, मेरी जिंदगी से अगर दुनिया को फर्क पड़ता है और सही दिशा में फर्क पड़ता है, तो मेरा लाइफ यूजफुल है, और नहीं पड़ता है तो मेरा लाइफ बेकार है. तो मैंने ये भी एक एक्सपेरिमेंट किया कि हम जाते हैं पटना, फिर देखेंगे ना, जो होगा सो देखेंगे. और जब हम एक्सपेरिमेंट करते हैं, दैट टाइम वी डू नॉट नो द रिजल्ट ऑफ द एक्सपेरिमेंट, रिमेंबर, तभी उसको एक्सपेरिमेंट बोलते हैं. मैं एक्सपेरिमेंटलिस्ट हूं, पीएचडी में एक्सपेरिमेंट्स किए हैं मैंने, तो वो कल्चर है मेरे पास. तो रिजल्ट पता नहीं है, इसलिए मैं ये काम नहीं करूंगा, कहीं गड़बड़ ना हो जाए. ये एक्सपेरिमेंटलिस्ट का कैरेक्टर है ही नहीं. वो तो सारे एक्सपेरिमेंट्स करता है, तो उसको रिजल्ट तो पता होता ही नहीं है. तो हमने ये भी एक्सपेरिमेंट किया कि चलो जो होगा देखेंगे, करो तो एक्सपेरिमेंट, जरा वहां पर जाकर के अपने जिंदगी को यूजफुल तो बनाओ. तो आई वेंट देयर, और किस्मत की बात देखिए, अगर मैं वहां नहीं गया होता, पटना में नहीं गया होता, और पटना साइंस कॉलेज में मुझे +2 पढ़ाने के लिए नहीं कहा गया होता, और मैं कहीं आईआईटी और ऐसी जगह के ऊपर हमने ज्वाइन कर लिया होता, तो कॉन्सेप्ट्स ऑफ फिजिक्स नहीं लिखी जाती. कॉन्सेप्ट्स ऑफ फिजिक्स नहीं लिखी जाती. So my experiment was really successful and it gave really nice results. वहीं से concepts of physics लिखी गई है. एक तो IIT सिस्टम में जो फैकल्टी मेंबर्स यहाँ बैठे हुए हैं, हंसते होंगे, लेकिन वो 15 घंटे काम करते हैं रोज. 13-14 घंटे तो करना ही पड़ता है उनको. 10-10 पीएचडी स्टूडेंट्स की जिम्मेदारी उनके सिर के ऊपर रहती है. वो इतने सारे, उनको अपनी इतनी बड़ी लैब चलानी है, उसके लिए फंड जनरेट करना है, और ये करना है, वो रिसर्च पेपर लिखना है, वो रिसर्च प्रोजेक्ट लिखना है, और पढ़ाना भी है जाकर के. 15-15 घंटे, 14-14 घंटे, 13-13 घंटे काम करते हैं ये लोग. ऑफिस आवर्स तो बहुत थोड़ा ही सा होता है. एक तो ऑफिस आवर होता ही नहीं, क्योंकि इनके ऑफिस की चाबी इन्हीं के पास होती है, और इनको कहीं दस्तखत नहीं करना पड़ता. हम इतने बजे आए, इतने बजे गए, बायोमेट्रिक, ये भी इनको नहीं करना पड़ता है. और उसका खामियाजा है, न इनके आने का कोई टाइम है, न इनके जाने का कोई टाइम है. और चले भी गए तो घर में जाकर के अगले दिन का लेक्चर ही बना रहे होंगे लैपटॉप खोल करके. तो कॉन्सेप्ट्स ऑफ फिजिक्स कब लिखते भैया? जब 15-15 घंटे आईआईटी का काम करेंगे तो कॉन्सेप्ट्स ऑफ फिजिक्स कब लिखेंगे? और 12वीं वालों से इंटरेक्शन भी नहीं है, उनको तो पढ़ा भी नहीं रहे, तो क्यों लिखेंगे? फिर हम इंजीनियरिंग फिजिक्स की किताब क्यों नहीं लिखेंगे? बीटेक फर्स्ट ईयर में अगर हमें फिजिक्स पढ़ाना है तो उसके हिसाब से हम लिखते. तो कॉन्सेप्ट्स ऑफ फिजिक्स कतई नहीं लिखी जाती अगर हमने ये एक्सपेरिमेंट ना किया होता पटना जाने का. ओके, चलो नेक्स्ट. गुड, अगला. ओके, गेट गुड, अगला. नाउ ये है गोइंग बैक टू स्कूल सिस्टम. आगे बढ़ो. यस, ये जब मैंने आईआईटी ज्वाइन किया, ये उसके बाद की कहानी है. ये सब होता चला गया, हमने कोई प्लान करके एक्सपेरिमेंट बहुत ज्यादा नहीं किया, ये सब होता चला गया. अपना जो संस्कार था, अपना जो थॉट प्रोसेस था, और जो हमने पहले 10 साल के अंदर में एक स्ट्रॉन्ग फाउंडेशन बना लिया था अपने मन के अंदर में, पहले फर्स्ट 10 ईयर्स के अंदर में, 0 to 10 ईयर्स के एज के अंदर में, उसका ये सब नेचुरल कंसिक्वेंसेस आते चला गया. इसीलिए मैं इसको अनइंटेंशनल एक्सपेरिमेंट्स कहता हूं. ऑलराइट, तो ये करने के बाद आईआईटी में फैकल्टी पोजीशन जब मैंने 15 इयर्स के बाद 1994 में लिया, बीटेक को पढ़ाना शुरू किया, तो आंखें खुली कि ये जेई पास करने वालों को एडवांस पास करके जो लोग जाते हैं आईआईटी में, जिनका नाम वाम निकल जाता है, उनको जो इतनी माला वाला पिन्हाई जाती है, मेडल वेडल दिया जाता है, कभी कभी सड़क के किनारे होर्डिंग्स में उनकी फोटो भी चिपकी रहती है, रिश्तेदार लोग बहुत बहुत बधाइयां देते हैं। लेकिन आईआईटी में आके, सर यहाँ का मुझे पता नहीं है, आप बता सकते हैं, जो लोग फर्स्ट ईयर में पढ़ाते हैं, जितने बच्चे आते हैं उसमें से कितने प्रतिशत को फेल करते हैं? कोई डेटा अगर मतलब कॉन्फिडेंशियल नहीं हो तो बताइएगा, अगर कॉन्फिडेंशियल हो तो मत बताइएगा, पब्लिक नहीं करने का हो तो मत बताइए। लेकिन मैं तो आईटी सिस्टम के बाहर आ चुका हूं तो मैं तो बता ही सकता हूं। At IIT Kanpur, we used to end up failing almost 25% of the students in the first examination. एडमिशन के 2 महीने के बाद जो पहला इम्तिहान होता है और फिर दूसरा इम्तिहान होता है, सेमेस्टर एंड होता है, तो सेमेस्टर जब एंड होता है, दोनों इम्तिहान हो गए, बीच में कुछ 10-10 नंबर वाले बीच के छोटे इम्तिहान भी होते रहते हैं, वो सब मिला के फाइनली रिजल्ट बनाया जाता है। तो रिजल्ट के समय में हमें 25%, लगभग 20 से 25% विद्यार्थियों को फेल करना पड़ता था। और करना पड़ता था इसलिए कह रहे हैं, हमें खुशी नहीं होती है किसी को फेल करने की, क्योंकि एज टीचर्स जो स्टूडेंट्स होते हैं हमारे दिल के बहुत करीब होते हैं। उन्हीं के कारण से तो हम टीचर हैं ना। हम अगर टीचर हैं, हम अगर प्रोफेसर हैं, तो हम अपने स्टूडेंट्स के कारण से प्रोफेसर हैं। हम अपने स्टूडेंट्स को दुखी नहीं देखना चाहते, लेकिन हमें करना पड़ता था। क्यों? क्योंकि हमारे पास में हथियार था फेल करने का और नहीं फेल करने का। आईटी सिस्टम जो स्कूल के बच्चे हैं उनको बता दूं, मैं कुछ भी बोल सकता हूँ ना सर। अब तो कोई मेरे ऊपर कोई प्रतिबंध है नहीं। आईआईटी सिस्टम में कितने नंबर लाने से पास करेंगे ये पहले से बताया ही नहीं जाता है। इम्तिहान लेने के पहले कोई पूछे कि सर कितने नंबर लाऊंगा तो पास कर जाऊंगा, या कितने नंबर लाऊंगा तो ए ग्रेड आ जाएगा, तो प्रोफेसर कहेंगे भैया जब मुझे ही नहीं मालूम है तो तुम्हें क्या बताऊं। तो ये पास मार्क कब डिसाइड होता है कि कितना पास मार्क करके इससे नीचे वालों को फेल करेंगे, इसके ऊपर वालों को फेल करेंगे, ये कब डिसाइड होता है? जब इम्तिहान खत्म हो जाता है, कापियां जच जाती हैं, नंबर टेबुलेट हो जाते हैं और एक्सेल के ऊपर बढ़िया सा ग्राफ बनाया जाता है। 17 नंबर वाले इतने विद्यार्थी है, 18 नंबर वाले उतने हैं, 25 नंबर वाले उतने हैं, 60 वाले उतने हैं, 70 वाले उतने, सुंदर सा ग्राफ बनाते हैं। फिर सोचते कहां पे लाइन डाले। उस लाइन के नीचे वालों को फेल करेंगे, उसके ऊपर वालों को पास करेंगे। तो आपको बताओ, ऑन द एवरेज ये जो लाइन डालने की बात होती थी, वो पास मार्क हमें कभी 32 नंबर रखना पड़ता था, कभी 25 रखते थे, कभी 27 रखते थे, कभी 30 रखते थे, कभी 34 रख दिया तो अच्छी बात हो गई, 40 तो कभी गया ही नहीं। कितने में 200 में। 200 में 35 नंबर का पास मार्क रख रहे हैं तो 100 लोगों को फेल करना पड़ रहा है। 400 का टोटल इंटेक, जब मैंने रिटायर किया था उस समय 400 का टोटल इंटेक था, और हमें करीब करीब 100 बच्चे हमेशा फेल करने पड़ते थे हर सेमेस्टर में। जब भी नया बैच आए तो पहले सेमेस्टर का रिजल्ट देखोगे और दूसरे का भी देखोगे, करीब 100 बच्चे फेल कर रहे 400 के अंदर में, और पास मार्क कितना रख रहे हैं? 30, 32, 34, 200 के अंदर में। अब क्या करें भैया, आईआईटी है, 0 पर तो नहीं रखेंगे ना पास मार्क को खिसका करके। 0 पर तो नहीं रख देंगे ना कि जो भी आ जाए, जिसका भी एडमिशन हो गया जेईई से सबके सब पास कर गए, ऐसा तो नहीं करेंगे ना। वहां से मुझे समझ आया कि हमारे स्कूल एजुकेशन के सिस्टम में ये 90, 95 नंबर लाने वाले, 97 और 98 लाने वाले बोर्ड के एग्जामिनेशन के अंदर में, और जेईई के अंदर में भी जो भी पास मार्क वो भी हालांकि कम ही होता है, वो भी कम ही होता है। हम अभी डेटा देख रहे थे 2 साल पुराना, आईआईटी दिल्ली ने कंपाइल किया है जनरल कैटेगरी में 30.4% पे ओवरऑल से पूरे इसका वो पास मार्क आया है कि उसके नीचे वाले एडवांस में नहीं क्वालिफाई किए, उसके ऊपर वाले कर गए। परसेंट में है वो डेटा। तो 100 में से 30 नंबर अगर आप ले आए हो तो आपने जेई एडवांस क्वालिफाई कर लिया और आपका आईआईटी में एडमिशन हो जाएगा जनरल कैटेगरी में। और एक सब्जेक्ट वाइज भी कट ऑफ होता है, वो सब्जेक्ट वाइज कट ऑफ तो और 10-12 नंबर का है। मैथमेटिक्स के 100 में 10 भी नंबर ले आओगे, लेकिन केमिस्ट्री में अच्छा कर गए, थोड़ा ज्यादा नंबर आ गया और वो 30.4 वाला क्रॉस हो गया तो भी आपका एडमिशन हो जाएगा। आप 10 ही नंबर, 90 नंबर गलत किया है, फिर भी आपको इतनी सारी बधाइयां मिल रही हैं, इतनी सारी मिठाइयां मिल रही हैं, इतने सारे फूलों के हार मिल रहे हैं। जरा सीबीएसई में 10 नंबर लाके तो दिखा दो क्या हालत होती है, क्या हालत होती है, कितने जूते पड़ते हैं फिर। नहीं भैया, आईआईटी का रुतबा है। तो यहां से मैंने वापस एक प्रयोग किया कि नहीं, हमें स्कूल सिस्टम में जाना है। मैं आईआईटी में आ गया हूं, आईआईटी में फैकल्टी हूं मैं, लेकिन मुझे वापस स्कूल के टीचर्स के साथ इंटरेक्ट करना है, उसको समझना है कहां गड़बड़ है, कहां गड़बड़ है। वो 11वीं 12वीं पास करके जो बच्चे मेरे पास बीटेक फर्स्ट ईयर में आ रहे हैं, कहां पे गड़बड़ हो रही है, उनकी ट्रेनिंग में क्या हो रहा है, स्कूल के सिस्टम में क्या हो रहा है। तो फिर से वहां रहते हुए हमने वापस वहां पे किया। चलो नेक्स्ट। अरे सो नहीं जाना भैया, बढ़ा दो। हैंग कर गया क्या कंप्यूटर? ओके गुड। तो फिर हमने वो जो 600 एक्सपेरिमेंट की बात कह रहे थे, हमने बहुत सारे छोटे छोटे, पहले तो पूरा जो एक्सपेरिमेंट किया और डेटा एनालाइज किया तो हमें यह समझ में आया कि हमारे टीचर्स को लर्निंग का जॉय नहीं मिल रहा है। उन्होंने जब भी अपना मास्टर्स किया होगा, अपना बैचलर्स किया होगा, अपनी स्कूलिंग की होगी, उस समय उनको लर्निंग का जॉय नहीं मिला और इसलिए वो लर्निंग का जॉय बच्चों में नहीं दे पा रहे हैं। और जॉय अगर नहीं मिल रहा है तो आप लर्निंग भी नहीं करोगे। जब तक आपको खुशी नहीं मिलती है, अरे वाह आज ये सीख गए, ये अगर नहीं मिलती है ना, तो स्ट्रेस में रह करके लर्निंग कभी नहीं होती है। मेरा इतना वर्कशीट का प्रॉब्लम नहीं बना, इतना होमवर्क था उसमें से इतना ही बना, ये नहीं हुआ, ये सवाल को लेके हम 1 घंटे से झींक रहे हैं। झींकने से काम नहीं होता है, स्ट्रेस के अंदर में लर्निंग नहीं होती है। हमारे टीचर्स को भी अपने एकेडमिक करियर में ये जॉय ऑफ लर्निंग नहीं मिला, ये हमें समझ में आया। और वो जॉय ऑफ लर्निंग स्टूडेंट्स को नहीं मिल रहा है, इसलिए उनकी लर्निंग नहीं हो रही है। लर्निंग नहीं हो रही है, एग्जामिनेशन केवल पास कर रहे हैं और इसलिए फिर आईआईटी में आकर के उनको प्रॉब्लम्स इतनी सारी हो रही हैं। तो ये जब डेटा एनालिसिस हमारे हुआ तब फिर हमने इस तरह के काम शुरू किए कि टीचर्स के साथ में खूब जॉयफुल फिजिक्स हम कर रहे हैं अब। ओके, वो काम हमने धंधा शुरू किया, वो एक्सपेरिमेंट हमने शुरू किया, छोटे छोटे एक्सपेरिमेंट्स बनाए और सबको खूब मस्ती के साथ में उसका फिजिक्स भी समझाया और ये सब भी कराए। तो ये सब चला। चलो नेक्स्ट। ओके, अब आया ये इंटेंशनल एक्सपेरिमेंट्स, जो कि ये तो होती गई परिस्थितियां और हम करते चले गए। उसके बाद मेरा हो गया रिटायरमेंट, तो ऑफिशियली अब मैं किसी को नहीं पढ़ाने के काबिल बचा। तो अब खुद को सोचना पड़ा कि अब मैं क्या करूं। पहले तो जैसे जैसे सिचुएशन मेरे को दिखती गई वैसे वैसे मैं करता गया, सिचुएशन ड्रिवन था वो। अब तो कोई सिचुएशन नहीं है, अब तो ब्लैंक है। तो फिर हमें अपना खुद से सारा प्लानिंग खुद से ही करना पड़ा, तो इसलिए मैं इसको इंटेंशनल एक्सपेरिमेंट कहता हूं। ऑलराइट, ये पार्ट 2 है मेरा। आइए, राइट, तो हम वापस स्कूल कॉलेज के सिस्टम में जाकर के बच्चों के साथ में, टीचर्स के साथ में हमने ये जॉयफुल लर्निंग का अभियान छेड़ा। हमने इस तरह के एक्सपेरिमेंट्स जनरेट किए कि लोग करें और लोगों को मजा आए और लोग करें। आप लोग करोगे क्या अभी एक एक्सपेरिमेंट मेरे साथ? हम कराते हैं, आप बैठे रहो अपनी जगह पे। आपने सब लोग अपना दोनों हाथ ऐसे आगे करो, एक 4 फिंगर जो है वो बाकी को समेट लो, केवल ये वाली उंगली रखो, एक दूसरे के तरफ मोड़ लो उंगली और दोनों को एक दूसरे से सटा लो और आंख के लेवल पे ले आओ या थोड़ा ऊपर। ओके, अब आप मुझे मत देखना, आए तो आप मुझे देखने के लिए, लेकिन मुझे देखना नहीं, आपको इस स्क्रीन को देखना है। और आपका जो हाथ उंगली है वो आपके बीच में आना चाहिए, लाइन ऑफ साइट के बीच में आना चाहिए, लेकिन उंगली पे फोकस नहीं करना। आंख उंगली देखने की कोशिश मत करना, बोर्ड देखने की कोशिश करना। कुछ अलग दिख रहा है क्या? 3 उंगली, किसने बोला 3 उंगली? हाँ, दिख रही है क्या 3 उंगली? 2 उंगलियां तो आपकी है, तीसरी बगल वाले के बीच में घुस गई है। दिख रही है क्या? अब जो आपकी दोनों उंगलियां सटी हुई थी उनको वैसे ही आप देखेंगे, उसी तरह बोर्ड को देखेंगे और उसको हाथ को बीच में रखेंगे, और जो सटी हुई तो 1-2 मिलीमीटर केवल हटा दीजिए, एक दूसरे से सेपरेट कर दीजिए, उतना ज्यादा नहीं, उतना कम, जस्ट 1-2 मिलीमीटर्स। बीच वाली उंगली का क्या हुआ? फ्लोट हो रही है, न इधर से जुड़ी है न उधर से जुड़ी है, लटक गई बीच में। अब इसकी ये हो गया एक्सपेरिमेंट। अब इसके बाद इसकी अगर हम फिजिक्स करना शुरू करेंगे, आंखों में कहाँ लेंस होता है, उसको हम फोकस करते हैं तो क्या होता है, उसका कर्वेचर क्या होता है, वो एक्स्ट्रा इमेज क्यों दिख रही है, हम उंगली नहीं देखना चाहते हैं फिर भी मुझे उंगली दिख रही है, वो एक्स्ट्रा क्यों दिख रही है, ये सारी फिजिक्स अब हम कर सकते हैं। ये है जॉयफुल लर्निंग। ओके, ये है जॉय। मजा तो आ गया भैया एक बार। और जब मजा आ गया तो एक क्यूरियोसिटी हो गई कि ऐसे कैसे हो गया, ये तीसरी उंगली कहां से आ गई, क्यों दिख रही है मुझे। अब एक मोटिवेशन मिल रहा है पढ़ने के लिए कि मेरी आंख का कर्वेचर कैसा होता है और लेंस का कर्वेचर सिलियरी मसल्स कैसे बदलती हैं, वो क्यों हमें जानना चाहिए। इसलिए हमें जानना चाहिए कि ये तीसरी उंगली कहां से आ गई, इसको जानना है। तो दिस इज द काइंड ऑफ एक्सपेरिमेंट्स वी आर डूइंग। हम उसको प्लान करते हैं और ऐसा ऐसा करते हैं, जॉयफुल लर्निंग कराने का कोशिश करते हैं। हाँ चलो अगला। 2 प्लेटफॉर्म्स में यूज करता हूं। एक है शिक्षा सोपान, विच इज एन एनजीओ स्टार्टेड बाय सम 4th ईयर बीटेक स्टूडेंट्स इन द ईयर 2001। अब उसके 24 साल पूरे हो गए हैं और 25वां साल जो है वो चल रहा है, रजत जयंती वर्ष है इसका। बहुत छोटा सा ग्रुप है ये, बहुत छोटा सा। आईआईटी कानपुर के 4th ईयर के बीटेक के स्टूडेंट्स ने 2001 में शुरू किया था। वो तो चले गए, 4th ईयर के थे ना, और हमारे माथे मड़ गए, चलाओ। और हम लोगों ने भी उसको कहा कि हाँ अच्छी चीज है, इसको चलाएंगे। तो हम लोग 24 साल से इस प्लेटफॉर्म को यूज कर रहे हैं। और यहाँ से शिक्षा सोपान का अपना एक बड़ा सा, नॉट बहुत बड़ा सा, एक छोटा सा ही कहो, 2 एकड़ टाइप का। यहाँ का कितना यहाँ का कितना कैंपस एरिया है? 535 एकड़ है। तो हम तो 2 एकड़ वाले हैं हम 2 एकड़ वाले हैं। उसी के अंदर में अपनी लैब्स वगैरह हमने सेटअप किए हैं। वहाँ पे स्टूडेंट्स आते हैं, वहाँ पे टीचर्स आते हैं, वहाँ पे हम कैंप्स करते हैं, इस तरह का जॉयफुल लर्निंग कराते हैं। तो शिक्षा सोपान के उस पर होता है। ये उसकी मेरी बाउंड्री वॉल है, उधर लोहे का दरवाजा आपको दिख रहा होगा, ग्रिल वाला, उसके बगल की बाउंड्री वॉल है। इसी के ऊपर हमारा ये नेम प्लेट इसी में लगा हुआ है। और हमारा 2-3 शब्द हैं, शिक्षा, संस्कार और स्वावलंबन। और नीचे का हमारा ध्येय वाक्य है, अंधकार को क्यों धिक्कारें। आगे हाँ अच्छा है, एक जलाएं। तो इसी से हम लोग प्रेरणा लेते हैं, इसी सेंटेंस से हम लोग प्रेरणा लेते हैं और काम करते हैं। और आईएपीटी इंडियन एसोसिएशन ऑफ फिजिक्स टीचर्स, इसको 1984 में ये शुरू हुआ था, कानपुर से ही शुरू हुआ था। और अभी भारतवर्ष का फिजिक्स टीचर्स का सबसे बड़ा एसोसिएशन ये है। और केमिस्ट्री बायोलॉजी वालों को भी अगर आप उससे भी कंपेयर करोगे तो उसमें भी सबसे बड़ा एसोसिएशन है। इसके 10,000 से ज़्यादा लाइफ मेंबर्स हैं। इसको भी, इस प्लेटफॉर्म को भी हम यूज करते हैं। हाँ चलो नेक्स्ट। ओके, अब पहला तो यही है कि लर्निंग फिजिक्स विथ एआई। और एआई का ए जो है वो हिंदी का है और आई जो है सो अंग्रेजी का है। ए इज फॉर अवलोकन, दैट इज ऑब्जर्व करना, एंड अदर थिंग इज इंटरप्रिटेशन। तो देखो क्या हो रहा है, देखो, क्योंकि मैंने कहा ना इवेंट्स को देख करके समझना ये मेरी नेचुरल स्ट्रेंथ है, हर व्यक्ति की नेचुरल स्ट्रेंथ है। तो हम उस तरह के सिचुएशंस क्रिएट करते हैं ताकि उसको लोग देखें, अवलोकन करें उसका और फिर उसको इंटरप्रेट करें। तो इस तरीके से करके अपना फिजिक्स सीखना, ये हमारा एक एक्सपेरिमेंट चला, ये बहुत बढ़िया एक्सपेरिमेंट चला। आपको दिख रहा है क्या वो जो शीशे के बर्तन के अंदर में हरे रंग की लेजर चल रही है पानी के अंदर में, क्या स्ट्रेट लाइन में चल रही है क्या वो लाइट? कैसा दिख रहा है आपको पता नहीं इतनी दूर से? स्ट्रेट लाइन में चल रही है कि कुछ ऐसा पैराबोला जैसा बना के चल रही है ना? तो अब ये है, हमने एक सिचुएशन क्रिएट कर दिया, लोगों को बताया नहीं कि हमने क्या किया, लेकिन हमने एक सिचुएशन क्रिएट किया, हमारे बर्तन के अंदर में कुछ पानी है, पानी जैसा कुछ है और हमने एक लेजर से उसमें लाइट डाली। अब वो लेजर सीधी रेखा में नहीं चल रही है, प्रकाश सीधी रेखा में गमन करता है, लाइट ट्रेवल्स इन स्ट्रेट लाइन, ये यहां नहीं हो रहा है। ओके, तो एक एलिमेंट ऑफ सरप्राइज लेकर के आओ, हमने सीखा इसको, एक एलिमेंट ऑफ सरप्राइज लेकर। लोगों को बहुत सारी चीजें पता है पहले से, लेकिन वो उसके अनुसार चीजें नहीं हो रही है, कुछ और हो रहा है। ऐसा ही होता है ना, जो मैजिशियन क्या करता है, आपको सब पता है कि ऐसे होना चाहिए वैसा, उसके अलावा कुछ हो रहा है, एंड देन यू आर सरप्राइज्ड कि ऐसे कैसे हो सकता है, एंड देन यू आर वेरी क्यूरियस कि हमें पता चले कि ये कैसे हो गया, ये कैसे हो गया। म्यूजिशियन कभी बताएगा नहीं आपको कि वो कैसे हो गया, उसकी दुकान नहीं चलेगी अगर बता देगा तो। लेकिन हम बताते हैं, हम पहले सरप्राइज करते हैं, पहले हम उनको सोचने के लिए मजबूर करते हैं कि सोचो 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 सोचो। उसके बाद कुछ लोग सोच लेते हैं, निकाल लेते हैं, कुछ लोग नहीं निकालते हैं, फिर हम डिटेल में उसकी सारी कहानी बता देते हैं कि हाँ भैया हमने ये किया वो किया वो किया। तो इस तरीके का कार्यक्रम जो है हमारा, आप उसको ऑब्जर्व करें और उसके बाद फिर उसको इंटरप्रेट करें। सो इट्स गोइंग ऑन। नेक्स्ट, यस, वंस अगेन ऑल पीपल आर वेरी हैप्पी डूइंग ऑल काइंड्स ऑफ एक्सपेरिमेंट्स। आगे अगला, ओके, ये कश्मीर का मामला है। हम लोग शिक्षा सोपान से अपनी टीम लेकर के कश्मीर गए थे, वहाँ रहे बहुत दिनों तक, और मुझे तो आप नहीं देख पा रहे होंगे, लेकिन मुझे ढूंढ जरूर पा रहे होंगे। ढूंढ पा रहे हैं क्या? मैं हूं क्या इस पिक्चर में? दिख रहे ना? बाल बाल मेरे लहरा रहे हैं ना थोड़े? हाँ, तो हम कश्मीर में इस तरह हम घूमते रहते हैं, हम जहां कहीं भी मौका मिलता है हम स्टूडेंट्स के बीच जाते हैं, हम टीचर्स के बीच जाते हैं, और उनके साथ ये जॉयफुल लर्निंग ऑफ फिजिक्स, ये हमारा एक्सपेरिमेंट अनवरत चलता जा रहा है। हाँ, चलो नेक्स्ट, मजलिस। ये एक अलग कार्यक्रम हम लोग ने शुरू किया है, मजलिस। मजलिस का मतलब जानते हैं ना, वो जहाँ शायर वायर लोग बैठ करके और एक चौकी के ऊपर गद्दा वद्दा बिछा करके चादर वादर सफेद रंग की डाल करके मुशायरा करते हैं, शेर सुनाते हैं, शायरी सुनाते हैं, उसको कहते हैं मजलिस। मजलिस लगी है, तो हम फिजिक्स मजलिस नाम का कार्यक्रम चलाते हैं, जिसके अंदर में कि जिस शहर में कार्यक्रम ये है, ये आउट स्टेशन एक्टिविटी है हमारे शिक्षा सोपान की। हम दिल्ली में, अभी नोएडा में कर रहे हैं, और फिर कुछ एक आध जगह और करने का भी प्लान है। तो हम वहाँ पर जा करके और टीचर्स का एक जगह इकट्ठा करके महीने में एक दफ़ा उनसे कुछ एक्सपेरिमेंट्स करवाते हैं वहाँ पे। वो लंबा एक्सपेरिमेंट होता है, वो 2 घंटे 3 घंटे वाला एक्सपेरिमेंट, 2 मिनट वाला नहीं होता है, वो करते हैं संडे के दिन। और 1 महीने में एक बार हम लोग ऑनलाइन मीटिंग करते हैं उनका विजन ब्रॉड करने के लिए। तो उसमें हम रिसर्चर जो हैं हमारे, या कोई बड़े अच्छे टीचर हैं या इस प्रकार के हैं, थोड़ा सा फिजिक्स से रिलेशन है, तो उनका ऑनलाइन फिर हम वेबिनार कराते हैं। अपने राजेश जी ने भी उसका ऑनलाइन दिया हुआ है इस मजलिस के अंदर में, और फिर से शायद आपको कांटेक्ट कर सकते हैं, बहुत दिन हो गए उसको। तो ये चलता है। हाँ, चलो नेक्स्ट, ये अन्वेषिका है। मैं इसकी थोड़ी सी बात करूंगा, मेरे ख्याल से 15 मिनट और लगेंगे मुझे। तो ये एक लेबोरेटरी है अन्वेषिका, ये IAPT का एक पार्ट है, इंडियन एसोसिएशन ऑफ फिजिक्स टीचर्स का, और इट इज ए लेबोरेटरी, एक ओपन लेबोरेटरी। हाँ, एक बार और दबाना तो देखें क्या आता है। हाँ, ओके, ये ओपन लैब है, और PLF इज फिजिक्स लविंग पर्सन्स। जो भी लोग फिजिक्स को प्यार करते हैं वो है PLF फेलोज, हमारे जो मित्र है। तो ओपन लैब का मतलब है कि, ओपन का मतलब ये नहीं कि ताला नहीं लगता है उसके अंदर में, ताले लगते हैं उसके अंदर में, लेकिन ओपन का मतलब है कि कोई स्ट्रक्चर्ड सिलेबस नहीं है। इट इज सपोज टू बी 1 टीचर 1 लैब। वो टीचर को जो मर्जी आए उस लैब के अंदर में बनाए, डेवलप करे, दूसरों को लाके उसमें से सिखाए, नहीं सिखाए। जो दूसरे आते हैं उनको भी स्वतंत्रता रहती है कि कुछ अपना आइडिया आजमाना है तो आजमा लो। तो ऐसे करके अन्वेषिका है, और हमारी इस समय में टोटल 31 सिटीज के अंदर में ये अन्वेषिका सेंटर चल रहे हैं। ओके, हाँ चलो नेक्स्ट। और अन्वेषिका में हम लोग बस इसी तरह के उछल कूद वाले धंधे करते रहते हैं, जिसमें लोग हंसी मजाक करें, लर्न करें और चीजें सीखें। और अलग अलग अन्वेषिका अलग अलग अपना प्रोग्राम्स बनाती रहती हैं। कुछ सेंट्रल प्रोग्राम्स हैं जो सभी करते हैं। नेक्स्ट, हाँ ये सब चल रहा है, ये सब अन्वेषिका। ये हमारी आंध्र प्रदेश की अन्वेषिका है, विजयनगरम शहर की। हाँ, हम बहुत सारे थे, तो हमने वो एयरपोर्ट एयर ट्रैवल के दौरान जो जो फोटो हमें दिखाई पड़ी हैं पटपट लगाते गए हैं। हाँ नेक्स्ट, इंदौर में भी अपनी एक अन्वेषिका है। यहाँ पर शिशु कुंज नाम का स्कूल है, उस स्कूल के अंदर में अरविंद पाठक नाम के शिक्षक हैं, उनके नेतृत्व में एक अन्वेषिका 31 में से एक सेंटर अपने इंदौर का भी है। चलो आगे। अब इसके अंदर में हमने कई सारे एक्सपेरिमेंट्स किए हैं। वन इज दिस जॉयफुल एग्जामिनेशन, ये भी अन्वेषिका के प्लेटफॉर्म पर है। नेशनल अन्वेषिका एक्सपेरिमेंटल स्किल टेस्ट कहते हैं इसको। एग्जामिनेशन पर हमने ये एक्सपेरिमेंट किया है। एग्जामिनेशन सबसे डरावनी चीज होती है ना। बाकी टाइम में तो आप कुछ भी कर लो, बगल वाले से भी बात कर लो, किसी की कुछ कपड़े वपड़े खींच लो, थोड़ा इधर उधर कर लो, बाल बाल नोच लो, कोई बात नहीं है, चलता है। लेकिन इम्तिहान के समय कुछ नहीं कर सकते हो। इम्तिहान के समय तो परीक्षा नहीं दोगे ढंग से, पूरे मन लगा करके, तो नंबर नहीं मिलेंगे। तो वो भी जॉयफुल हो, वो भी डरावना नहीं हो, उसमें भी स्ट्रेस नहीं हो, उसमें से भी लर्निंग हो। इसके लिए हमने एक खास तरीका, हम छोटे स्तर पर है, इसको स्केल अप नहीं कर सकते इस मॉडल को, लेकिन हमने छोटे के लिए एक मॉडल बनाया, कोई बड़े के लिए मॉडल बना दो इसी प्रिंसिपल्स के ऊपर। तो इसके अंदर हम क्या करते हैं, हमारा उद्देश्य ये है कि इट शुड बी एंजॉयबल एंड एडुकेटिव। चलो अगला। तो इस नेस्ट के कई सारे राउंड्स हैं। पहला राउंड स्क्रीनिंग राउंड कहलाता है, वीडियो बेस्ड है। एक मिनट से छोटे वीडियो होते हैं, उसके ऊपर क्वेश्चंस पूछे जाते हैं। फिर अगला ये प्रीलिम्स राउंड कहलाता है, ये इसमें 3 एक्सपेरिमेंट करते हैं, हम थोड़ा आगे बताएंगे। चलो नेक्स्ट। ओके नेक्स्ट, ओके नेक्स्ट। हाँ ये देखो, ये एक जो आप ये लिंक देख रहे हैं, अगर ये इसको लिंक को हम प्ले कर दें अभी, तो उसमें क्या होगा कि एक बॉटल होगी किसी के हाथ में, अभी हम उसको प्ले नहीं करेंगे। एक बॉटल होगी हाथ में, और दो बॉटल्स हैं। एक बॉटल है जिसका ढक्कन ऐसे ऐसे करके बंद किया जाएगा, ओके। एक बॉटल है जिसका ऐसे ढक्कन लिया जाएगा, ऐसे लेकर के उसको यूं 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 बंद किया जाएगा। और दूसरी बॉटल है जिसका ढक्कन चूड़ी वाला नहीं है। आपने देखा होगा ना, जो शैम्पू वगैरह आते हैं तो पट से ऐसे खोलते हैं, पट से ऐसे बंद कर देते हैं, उसमें चूड़ी नहीं करते हैं, वो ऐसा करके ऐसा खुलता है और फिर ऐसा बंद हो जाता है। तो ये 2 बॉटलें हैं और दोनों के ढक्कन बंद किए जा रहे हैं अलग अलग। अब उसके ऊपर से देखो एमसीक्यू सवाल है। हाँ, जब कैप स्क्रू हो रहा है तो उस समय की बात है, वर्क डन बाय द एयर इन द बॉटल ऑन द कैप इज पॉजिटिव है कि नेगेटिव है। जो एयर है वो कैप के ऊपर 0 कर रही है, टेम्परेचर ऑफ एयर इनसाइड का क्या हो रहा है, वगैरह वगैरह, इस तरह के क्वेश्चंस हैं। तो ऐसे वाले वीडियो के ऊपर सवाल बनाना, फिजिक्स के सवाल बनाना है, लेकिन सिचुएशन क्या है, जो हम घर में करते हैं, रोजाना करते हैं, सुबह से शाम तक करते हैं, नेचुरल लर्निंग। ढक्कन खोल रहे हैं। हमारा एक सवाल था, उसमें एक चिड़िया बैठी थी और वो चिड़िया उड़ी जमीन से और जाके डाली पे बैठ गई, वीडियो खत्म। 1 सेकंड का वीडियो है, लेकिन सवाल उसके ऊपर ऐसा है कि उस पर 2 मिनट लगेंगे उसको सवाल को बनाने के अंदर में। काइनेटिक एनर्जी का क्या हुआ, पोटेंशियल एनर्जी का क्या हुआ, टोटल एनर्जी का क्या हुआ, ये वो करके उसके अंदर सवाल। तो ऐसा इस तरीके का सवाल। और हमारे इस परिसर में जितने क्लास 9 से 12 के विद्यार्थी बैठे हैं, उनके लिए ये एग्जामिनेशन अब शुरू होने वाला है। 1 अप्रैल से इसके रजिस्ट्रेशन शुरू होने वाले हैं। अगर आप मेरे चैनल पे जाएंगे, यूट्यूब चैनल पे, तो आपको वहां पे भी एक वीडियो इसका दिखाई पड़ेगा, इसके बारे में डिटेल्स। और शिक्षा सोपान के साइट पर जाएंगे तो भी, और नेस्ट लिख करके गूगल सर्च कर देंगे तो भी आपको इसके डिटेल्स मिलेंगे। 9 से 12 तक के बच्चे इसमें भाग ले सकते हैं। हाँ चलो नेक्स्ट। सेकेंड राउंड का एक्सपेरिमेंट सबसे बढ़िया है, आवर एक्सपेरिमेंट योर डिजाइन। ये इसमें हम एक लिख करके भेजते हैं, जो स्क्रीनिंग से हमने करीब 1000 बच्चों को सेलेक्ट किया होता है, उनको हम लिख के भेजते हैं ईमेल के द्वारा। ये एक्सपेरिमेंट करना है, हम बताएंगे ये एक्सपेरिमेंट करना है, कैसे करना है ये आपका हेडेक है, वो हम नहीं बताएंगे। क्योंकि ये एक्सपेरिमेंट हम भेजते हैं वो घर में किया जाना है, लैब में नहीं किया जाना है, और घर में जो सामान उपलब्ध है उसी से किया जाना है। कोई साइंटिफिक इंस्ट्रूमेंट आपको खरीद करके नहीं लाना है या लैब से नहीं लाना है। चकला, बेलन, तवा, कढ़ाई, प्लास्टिक का डब्बा जिसमें आप चना दाल रखते हैं, वो सब, बॉटल्स तरह तरह की, रस्सी, रबर बैंड, टेबल, कुर्सी, घर में जो सामान रहते हैं उन्हीं सामानों से, आपका अपना मोबाइल फोन भी एक सामान ही है, उन्हीं चीजों को इकट्ठा करके डिजाइन करना पहले एक्सपेरिमेंट, कि जो चीज हम मांग रहे हैं वो कैसे मिलेगी, फिर उनको असेंबल करना, फिर उस पर एक्सपेरिमेंट करना, फिर उसमें डेटा लेना, फिर उसका ग्राफ बनाना, उसका टेबल बनाना, उसके बाद उसकी मैथमेटिक्स करना, और जो हम कहते हैं ये निकाल के लाओ भैया पानी का सरफेस टेंशन चाहिए, वो करना। तो ये हमारा सेकेंड राउंड होता है। और इसमें मैं आपको थोड़ा सा इसलिए डिटेल्स में बता रहा हूं कि इसमें इम्तहान के सारे नॉर्म्स जो होते हैं वो हमने तोड़ दिए हैं। आप देखना कैसे। हाँ, नो इन्विजिलेशन, 3 एक्सपेरिमेंट करने होते हैं, वन आफ्टर द अदर। एक करोगे तो दूसरा भेजेंगे। 5 दिन का समय देते हैं एक्सपेरिमेंट करने के लिए, और कोई नहीं कहता कि अपना कैमरा ऑन रखना, जिस समय आप एक्सपेरिमेंट कर रहे हो हम देखेंगे, हम नहीं देखेंगे। तो नो इन्विजिलेशन। और हम कहते हैं कि जिसको मर्जी आए उसको बुला लो अपने साथ। घर के लोगों को तो बुलाओगे ही, घर का जब डब्बा वब्बा मांगोगे तो मम्मी से को तो लाना ही पड़ेगा ना, तभी तो डब्बे मिलेंगे कैसे। बाहर से भी बुला लो, दोस्तों को बुला लो, अपने फिजिक्स टीचर को आ जाए तो उनको भी बुला लो, किसी को भी बुला लो, कोई इन्विजिलेशन नहीं है। नेक्स्ट, आगे बताओ। ओके, तो 5 दिन का समय है, कोई ऐसा नहीं है कि 3 घंटे में कॉपी छीन ली जाएगी और वगैरह वगैरह हो जाएगा, वो भी नॉर्म शैटर्ड है। नेक्स्ट, फैमिली मेंबर्स, फ्रेंड, टीचर, सबको बुला लो, एब्सोल्यूट फ्रीडम टू इनवाइट। और आगे बढ़ो। नेक्स्ट, अब जो हमने लिख के दिया कि ये करना है वो आपने कर दिया, एकदम बढ़िया कर दिया, एकदम हम खुश हो गए देखकर, अरे वाह क्या नंबर आए। तो आपको ज्यादा से ज्यादा मैं आपके कितने नंबर दूंगा? 100 में से 70, उससे ज्यादा मैं दूंगा ही नहीं। 70 नंबर में ही करना है मैक्सिमम, सबसे बढ़िया लगा तो 70 भैया, और उसके बाद फिर उससे कम। 30 नंबर क्यों लिखे मैंने, 100 का क्यों लिखा मैंने मैक्सिमम मार्क्स? वो 30 नंबर वो काम करने के लिए है जो मैंने नहीं कहा था उस पेपर के अंदर में। आप वो कर गए तो उस 30 में से भी फिर और नंबर मिलेंगे। तो जो हमने कहा वो तो आपने किया ही। अब आप उसके बाद सोच रहे हो, सोचने की क्षमता विकसित करनी है, और क्या कर लें इसमें से। उसके लिए कोई डायरेक्शन नहीं है, कोई डायरेक्शन नहीं है, इंडिपेंडेंटली आप सोच रहे। और बच्चे इतने क्रिएटिव होते हैं। एक बच्चे ने एक खास एक्सपेरिमेंट में इतना काम किया, उसने इतना एक्सप्लोर किया, उसके दाएं बाएं आजू बाजू का, और ये करके वो करके 102 पेजेस का उसने मेरे को रिपोर्ट भेजा। क्लास 11th का स्टूडेंट, एक एक्सपेरिमेंट का रिपोर्ट 102 पेजेस। कौन कहता है कि परीक्षा जो है दुखदाई होती है? लेकिन परीक्षा के जो नॉर्म्स, इतने टाइट नॉर्म्स बने हुए ना, वो दुखदाई होते हैं। और बिना रटे हुए काम नहीं होता है, सोचने की जरूरत नहीं पड़ता है, तो कुछ मजा नहीं आता है, याद है तो लिखा, नहीं याद है तो, इसलिए वो दुखदाई होता है। ये तो बड़े मजे, परीक्षा तो बड़े मजे की चीज है, हमने तो बड़े मजे मजे लेकर के किए हैं परीक्षाएं। हाँ चलो नेक्स्ट। 9वीं से 12वीं तक के बच्चे, और हमने यहां बोला नहीं, बीएससी और एमएससी के बच्चे भी भाग लेते हैं इस परीक्षा के अंदर में, और सबके लिए एक ही पेपर बनता है। जिस पेपर पे क्लास 9th का बच्चा एग्जाम दे रहा है, स्क्रीनिंग हो या ये सेकेंड राउंड हो, उसी पेपर पे एमएससी का बच्चा भी इम्तहान दे रहा है, उसी पे 12वीं का भी दे रहा है, उसी में 10वीं का भी दे रहा है। वो भी परीक्षा के सब कहाँ सिलेबस और क्या। और हमारा पूरा ये 12 साल, 2011 से ये परीक्षा शुरू हुई थी शायद, इतने साल हो गए, हमारे पास बहुत डेटा है। और वो डेटा बताता है कि जो सक्सेस परसेंट जो हम जो भी स्क्रीन करते हैं, 1000 को लेके जाते हैं, जितने प्रतिशत स्कूल वाले बच्चे जाते हैं, उससे कम प्रतिशत हमारे कॉलेज वाले बच्चे पास करते हैं। और जो स्कूल वाले पास करते हैं उसमें 9, 10th, 11th, 12th का कुछ नहीं है, 9th वाले भी पास करते हैं, 12 वाले भी पास करते हैं। आप देखो स्टैटिस्टिकल एवरेज बिल्कुल बराबर बराबर सा दिखेगा आपको। तो इस तरीके का ये भी नॉर्म शैटर्ड है। चलो नेक्स्ट। ओके, अब जो अगला जो तीसरा चौथा राउंड होता है वो हमारे सोपान आश्रम कानपुर पे हम 40 लोगों को बुलाते हैं, उनका होता है। हाँ, आगे बढ़ो। तो ये लोग आते हैं मेरे यहाँ, हम लोग सेटअप तैयार करके रखते हैं, उनको एक्सपेरिमेंट करने के लिए देते हैं और वो होता है। उसके अंदर में क्या तमाशे हम लोग करते हैं वो आप देखो। आइए नेक्स्ट आइए, अगला। ये ज्यादातर एक्सपेरिमेंट मेरे लैब के बाहर भी होते हैं, ज्यादातर बाहर ही होते हैं, कुछ अंदर होते हैं। सब आप देख रहे हो ना गार्डन पे, वो पेड़ वेड़ हैं और ये है, उसी में रस्सी वस्सी बांध दी है और उसी में एक्सपेरिमेंट्स हो रहे हैं नेचर के साथ। अगला, ये देखो ऐसे ऐसे, ये कपल्ड पेंडुलम का एक्सपेरिमेंट है, यहाँ कराते होंगे फर्स्ट ईयर में कपल्ड पेंडुलम का एक्सपेरिमेंट। मेरे यहाँ ऐसे होता है कपल्ड पेंडुलम का एक्सपेरिमेंट। और हमारे पास गाय भी है, तो गाय का जब छोटा बच्चा होता है नया, जब गाय हमारी बच्चा देती है, वो बच्चा जरा सा बड़ा होता है, इसके साथ बहुत खेलता है, कपल्ड पेंडुलम के साथ बहुत खेलता है। वो आके एक को हिला देता है और फिर दूसरा भी हिलता है और वो मजे से देखता है उसको, वो भी फिजिक्स लर्न कर रहा है। हाँ चलो नेक्स्ट। हाँ आगे। हाँ ओके, हम भी बैठ जाते हैं जब बच्चे एक्सपेरिमेंट करते हैं, तो हम भी बैठते हैं वहाँ पे। चलो आगे। यस, हाँ ठीक है, और आगे बढ़िए बढ़िए। ओके, ये मैं आपको दिखाना चाह रहा हूँ। जो हमारे इन्विजिलेटर्स होते हैं इस वाले में, इसके लिए नहीं होते हैं कि बगल वाले का कोई कॉपी नहीं करे, वो नहीं, हम कहते हैं उनको इन्विजिलेटर्स, वो एक्चुअली इवैल्यूएटर्स होते हैं, वही लोग नंबर देते हैं अंत में। तो उनको ये इंस्ट्रक्शन होता है, हाँ आगे वाला था ना, नेक्स्ट नेक्स्ट नेक्स्ट। हाँ, उनको ये इंस्ट्रक्शन होता है, एवरी स्टूडेंट मस्ट कंप्लीट द एक्सपेरिमेंट्स, ऑल 3 एक्सपेरिमेंट सक्सेसफुली। वो हम फर्स्ट सेकंड थर्ड और ये उतना नंबर करते रहेंगे। लेकिन कोई भी विद्यार्थी जो इस राउंड में आ गया है सोपान आश्रम में, 40 बच्चे जो बुलाए गए हैं, 40 को ये 3 एक्सपेरिमेंट करके ही यहां से जाना है और सक्सेसफुली करना है। जिम्मेदारी किसकी? इवैल्यूएटर्स की। हमारे इवैल्यूएटर्स पूरे टाइम वॉच करते हैं, और इसमें भी कोई टाइम का लिमिट ज्यादा होता नहीं है, किसी को 2 घंटे करना है करो, 3 घंटे करना है करो, 4 घंटे करना है करो, पूरे टाइम वॉच करते हैं। कहीं अगर उनको लग रहा है कि गलत राह पर चल रहा है, इसका एक्सपेरिमेंट फेल हो जाएगा, इससे होगा नहीं, वो जाएंगे उसके पास, को बताएंगे कि ऐसे नहीं ऐसे होता है, ये करो आप, तब आएगा। वो फोकस नहीं हो रहा तो ये करो तब फोकस होगा, ये रीडिंग नहीं आ रही तो ये करो तब आएगी। उसको ट्रेन अप करते हैं और सबसे एक्सपेरिमेंट करवा के तब भेजते हैं उसको। तो मेरे यहाँ जिसको अच्छे नंबर आए, फर्स्ट सेकंड थर्ड मिले, ढेर सारी स्कॉलरशिप मिली, पैसे मिले, प्राइज मिले, वो भी खुश, और जिसको कुछ नहीं मिला वो भी खुश। पहली बार इतने अच्छे अच्छे एक्सपेरिमेंट करने को मिले, पहले घर में किया, अब यहाँ पे किया, और सारे टीचर्स इतने प्यार प्यार से समझा करके उसको करा रहे हैं। फिर हम उनके साथ में और भी खेल तमाशे भी करते हैं, खास करके जो लोग फेल करते हैं इसमें। फेल करते हैं मतलब, फेल तो शब्द बहुत ही खराब है, फेल तो कोई नहीं करता है, लेकिन हाँ जो प्राइज में नहीं आते हैं उनके साथ भी हम बहुत सारे खेल। ओके, सो ये हमारा परीक्षा का एक्सपेरिमेंट है। आगे देखो तो कुछ है क्या? हाँ, रिसर्च लैब। हाँ, हमने एक अपने सेंटर के ऊपर एक रिसर्च लैब भी छोटी सी बनाई है, बहुत छोटी सी है, 5 लाख रुपए से भी कम लगे हैं उसके अंदर में। मटेरियल साइंस के कुछ चीज़ें रखी हुई हैं वहाँ पे। तो हमारे यहाँ इंटर्नशिप करने के लिए NIT से कई सारे स्टूडेंट्स हर साल आते हैं, महीने 2 महीने रहते हैं वहाँ पे, और इस रिसर्च लैब के अंदर में काम करते हैं, और वो काम आगे बढ़ाते हैं फिर अपने इंस्टीट्यूट में जा करके। और जगह जगह जो प्रेजेंटेशंस होते हैं, सेमिनार सिम्पोजियम होते हैं, उसमें हमारे स्टूडेंट्स जो यहाँ काम करते हैं वो लोग अपना प्रेजेंटेशंस देते हैं। और जो यूनिवर्सिटी है हमारे सेंटर से 3 किलोमीटर पर होगी, कानपुर की यूनिवर्सिटी है, वहाँ पर जो MSc के स्टूडेंट्स होते हैं वो हर साल यहाँ पे 5-6 स्टूडेंट्स आकर के इस लैब के अंदर में अपने डिसर्टेशन का जो प्रोजेक्ट MSc में करते हैं उसका काम यहाँ पे करते हैं, और उसको वो लोग वहाँ पे अपना सबमिट करते हैं। ये कल्चर यहीं से शुरू हुआ है, वरना MSc का डिसर्टेशन कंट्रोल C और कंट्रोल V से ही हुआ करता था। अब ये यहाँ से होता है, कम से कम उन 5 बच्चों के लिए हर साल जो कि इसमें आते हैं। ये भी एक हमारी एक्टिविटी है। ये एक्सपेरिमेंट भी बहुत सक्सेसफुल रहा है हमारा। और ये हमारे दीना चंद्र जी हैं जो कि सबको समझा रहे हैं। ये सारे 5 बच्चे MSc के हैं कानपुर यूनिवर्सिटी के, और उनके साथ में सब रिसर्च का प्रोजेक्ट है। हाँ चलो नेक्स्ट। ओके, इसको हम लोग सुरीला कहते हैं। ओके नेक्स्ट, ठीक है। ये हमारी सुरीला लैब की एक्टिविटीज़ हैं, कुछ आगे। ये सब बच्चे हैं, देखो कर रहे हैं, एक्सपेरिमेंट्स कर रहे हैं अपने। हाँ ऑलराइट, हो गया क्या? हाँ ठीक है, ये सब बता दिया मैंने। ओके हाँ, बस ये आखिरी है। ये जो JEE है ना, जी, वो जी नहीं है, वो जी का जंजाल है। इस जी के जंजाल से हमें फंसना है, इसमें फंसना नहीं है। और नहीं फंसने का क्या मतलब है? स्ट्रेस नहीं लेना। आप कभी लर्न नहीं करोगे अगर स्ट्रेस लोगे तो। परीक्षा में नहीं होगा तो मेरा क्या होगा, ये होगा वो होगा। इतना मैं तो 10वीं क्लास तक तो इतने अच्छे नंबर आते थे, हमसे सारे सवाल बन जाते थे, और हमें बहुत इंटरेस्ट था फिजिक्स करने में और मैथमेटिक्स करने में। और अब तो कोचिंग जाते 6 महीने हो गए, हमें तो कुछ हो ही नहीं रहा है, मुझसे हो ही नहीं रहा है। इतनी सारी मेल मेरे पास में आती है, हम सबको काउंसलिंग करते रहते हैं मेल के ऊपर। ये स्ट्रेस नहीं लेने का है। मुझसे अभी वो पॉडकास्ट किया मैंने 3 दिन पहले एक स्कूल के अंदर में, उनके इसमें, उसमें उन्होंने ये पूछा कि लोग फेल्योर से कैसे अपने को उसमें कैसे अपने को संभाल कर रखें कि फेल्योर से वो बहुत ज़्यादा व्यथित ना हो। और फेल्योर किस बात का? जेई का। जेई में अपियर हो रहे हैं और वो फेल कर जाएंगे या कर गए, उनको कैसे काउंसिल किया जाए। तो मैंने वो बताया कि फेल कौन करता है? फेल कौन करता है? जेई में पास नहीं होने को फेल करना कहते हो, फेल्योर कहते हो? इट्स नॉट ए फेल्योर। 20 लाख लोग अपियर होते, 20,000 पास करते, 19 लाख 80,000 बच्चे जेई का इम्तिहान पास नहीं करते। अगर आप कहो कि वो फेल्योर्स हैं, जिस देश के 20 लाख में से 19 लाख 80,000 बच्चे हर साल फेल कर जाए, क्या दुनिया में उस देश का डंका बच सकता है? आज दुनिया में अगर भारत की पहचान है, आज हमारे प्रधानमंत्री जी हर देश का सर्वोच्च नागरिक पुरस्कार उन्हीं को मिलता रहता है। जहां जाते हैं वहीं पता चलता है कि इस देश का सर्वोच्च नागरिक पुरस्कार इनको मिल गया, आज उसको मिल गया, आज वहां वाला मिल गया, आज वहां वाला मिल गया। पुतिन जी से लेकर के और ट्रंप जी तक सब लोग उनके साथ लालायित रहते हैं मिलने के लिए। जिस देश के 20 लाख लोगों में से हर साल 19 लाख 80,000 लोग फेल कर जाएं, फेलियर हो, ऐसा देश क्या डंका बजा सकता है अपने दुनिया के अंदर में? व्हाट इज फेलियर? तो फेलियर नाम का कोई चीज नहीं है। वो पास किए तो भी ठीक, नहीं पास किए तो भी ठीक। और हमने तो पहले ही कहा था ना कि हम जेई का फॉर्म नहीं भरेंगे, फिर भी हमने अपनी जिंदगी अच्छे से गुजार ली ना, और गुजार रहा हूं। तो जंजाल में नहीं पड़ना, वो अच्छी चीज है। IITs बहुत अच्छी चीज है, लेकिन IITs अच्छी चीज तभी है जबकि आप मजे मजे में पढ़ाई करोगे, मजे मजे में इम्तिहान दोगे, यहां आकर भी मजे मजे में इम्तिहान दोगे, तो आपको 100 में 17 नंबर और 18 नंबर के लिए संघर्ष भी नहीं करना पड़ेगा, आप अच्छे नंबर भी लेकर के आओगे। और जब आप स्ट्रेसफुल रहोगे, दिमाग के समोसा खा खा करके दिन गुजारोगे, हैं, और कचौड़ी खा खा करके दिन गुजारोगे। इंदौर खाने पीने के लिए वैसे प्रसिद्ध है, बड़े अच्छी अच्छी चीजें मिलती हैं रोड किनारे में। लेकिन आपने एक्सरसाइज करना छोड़ दिया, आपने बैडमिंटन खेलना छोड़ दिया, आप अच्छी ड्राइंग बनाते थे वो छोड़ दी, रिश्तेदार आते हैं तो आप कमरे में रहते हो, घर में बाहर नहीं निकलते हो, आधा घंटा बर्बाद हो जाएगा। ये सब जो झमेला है ना, ये आप अपने आप को कमजोर कर रहे हो। आप जेई में पास करने का वो प्रोबेबिलिटी भी घटा रहे हो एक्चुअली, क्योंकि थके हुए माइंड से जब क्वेश्चन पेपर पढ़ोगे जाके वहां पे, और वह नया क्वेश्चन आने ही वाला है हर साल। ये लोग 15-15 दिन का, 10-10, 12-12 दिन का, और अज्ञातवास में चले जाते हैं, है ना। अज्ञातवास किसी को मालूम नहीं होता है। पक्के से पक्का दोस्त भी होगा ना, तो उसको भी पता नहीं हुआ कि भाई साहब हमारे मेरी IIT में आके और जेई का पेपर बना रहे। हर बार नया सवाल बनाते हैं, वो तो नया सवाल मिलने ही वाला है। थके हुए दिमाग से अगर आप पढ़ोगे उस सवाल को तो अच्छा करने की प्रोबेबिलिटी कितनी बचेगी? बिल्कुल नहीं बचेगी ना। आपका तो माइंड फ्रेश होना चाहिए, उत्साह से परिपूर्ण होना चाहिए आपका माइंड, तभी तो करोगे। तो बहुत अच्छी चीज है जेईई करना। और हम कहते हैं जेईई करने की सफलता क्या है और असफलता क्या है, पास कौन है फेल कौन है। 2 साल आपने जिसको कहते हैं रगड़ के पढ़ाई की, रगड़ के पढ़ाई की ना, कम से कम 2 साल, ज्यादा भी कर सकते हो। हाँ, जल्दी स्टार्ट करोगे तो ज्यादा भी हो जाएगी, हालांकि आजकल 2 ही अटेम्प्ट वगैरह का सब रूल है, आप उधर नहीं पढ़ सकते हो, इधर तो पढ़ ही सकते हो। तो अगर आपने रगड़ करके पढ़ाई की है, जॉयफुली लर्न किया, याद नहीं किया, लर्न किया, आप सफल हो चुके। आपको जेई का कार्ड देखने की जरूरत नहीं है। आपने उतना सारा अपना स्किल बढ़ा लिया ना, उतने सारे आपने इक्वेशन सॉल्व कर लिए, उतना सारा आपको प्रैक्टिस हो गया, उतनी सारी चीजें आपको समझ में आ गई, आपने इतनी सारी लर्निंग कर डाली। अरे अब तो आप कहीं भी खड़े हो जाओगे ना जमीन पे, जरा सी जमीन चाहिए केवल आपको खड़े होने के लिए, आसमान तो फिर आप छू ही लोगे, क्या दिक्कत है। और जितना बोला जाता है ना कि भारतवर्ष का सबसे कठिन इम्तिहान है, अरे कुछ कठिन इम्तिहान नहीं भैया। जब बच्चों के बहुत इस प्रकार के मेरे पास फ्रस्ट्रेशन वाले मेल आने शुरू हुए तो हमने भी देखा कि क्या हो गया, आजकल जेई वाले कठिन प्रश्न बनाने लग गए हैं क्या मेरे रिटायरमेंट के बाद। तो हमने अपने रिटायरमेंट तक का तो हमें पता था, उसके बाद वाले जो पिछले के 6-7 साल के पेपर्स हैं वो सब हमने जेई की वेबसाइट से डाउनलोड किए और हमने पढ़ा, देखा। हमने कहा अरे इससे भारी तो हम बनाया करते थे, ये तो हल्के बनाने लग गए, ये तो और हल्के बनाने लग गए। फिर हमने कहा यार ये तो बड़ा अच्छा है, अगर ये पेपर आते तो हमारे जो रेगुलर फिजिक्स वाले टीचर हैं स्कूल वाले जो बोर्ड के लिए पढ़ाते हैं वो ये भी पढ़ा देंगे, उसमें क्या बड़ी बात है। अब तो उनके लेवल पे आ गया जेई, पहले तो उनके लेवल से थोड़ा ऊपर हुआ करता था, अब तो उन्हीं के लेवल में है, अब तो कर सकते हैं। तो मैंने एक पायलट प्रोजेक्ट लिया दिसंबर 2023 में, वो मेरा लास्ट एक्सपेरिमेंट है जो अभी चल रहा है। और हमने रैंडमली एक हमारे मित्र लोग, मैं तो व्हाट्सएप में नहीं रहता हूं, हमारी जो टीम है उन्होंने व्हाट्सएप के ऊपर एक मैसेज फ्लोट किया कि अच्छी वर्मा साहब जो हैं वो स्कूल फिजिक्स पीजीटीज के साथ में बैठ करके और जेई एडवांस के प्रॉब्लम सॉल्व करने का कैंप लगा रहे हैं, किसको आना है। रैंडमली, कोई ये नहीं क्राइटेरिया नहीं कि आप बहुत रेप्यूटेड टीचर हैं और आपका 15 साल का एक्सपीरियंस है और आप ट्यूशन पढ़ाते हैं, और ये कुछ भी नहीं, रेगुलर फिजिक्स पीजीटीज लिखा हुआ था जो ट्यूशन नहीं पढ़ाते। लोगों ने अप्लाई किया, हमने उनमें से 12 लोगों को ऐसे ही, हम किसी को जानते ही नहीं थे नाम वाम से, हमने 12 लोगों को सिलेक्ट किया, हमने कैंप किया 7 दिन, और 7 दिन के कैंप में रोजाना 1.5 घंटे का मेरा लेक्चर होता था इस बात के लिए कि सवाल पढ़ना कैसे, सवाल पढ़ करके सवाल को समझना कैसे, उसके बाद फिर उसको उसके ऊपर सोचना कैसे, प्लान कैसे करना, उसको बनाना कैसे। और आपको बताऊं हमने 7 दिन के अंदर में करीब 13-14 सवाल उनके साथ हमने दिखाए उनको कि देखो इसको ऐसे हम बनाएंगे। रोजाना मेरा 1.5 घंटे का होता था सेशन कि हम ऐसे बनाएंगे। तो हमने उनको इस प्रकार से वो करके और वो शुरू कराया, और बाकी के टाइम में भी हम दिन में पूरा हमने जो रिसर्च, वो सवाल आते थे ना जेई एडवांस में, उसके करस्पॉन्डिंग एक्सपेरिमेंट भी बना लेते थे हम, फैब्रिकेट कर लेते थे एक्सपेरिमेंट, वो उसको दिखा भी रहे हैं वहां पे। इन्होंने बोला कि एक चकती है उसमें से एक दूसरी चकती काट के निकाल दी गई है, तो हम भी एक चकती लेते थे और उसमें से काट के निकाल देते थे, देखो ये रहा सवाल। तो केवल सवाल पढ़ के ही नहीं, उसका बाकायदा फिजिकल करके भी कुछ लुढ़काना है तो हम भी लुढ़का देते थे इंक्लाइन प्लेन बना करके। तो करस्पॉन्डिंग एक्सपेरिमेंट कराना, फिर बाकी के जो बेसिक एक्सपेरिमेंट्स हैं वो कराना, दिन भर हम उनको इंगेज रखते थे, ब्रेकफास्ट से लेकर डिनर तक। और डिनर पे उनको हम लोग, और प्लस उसमें से एक रहता था कुछ सवाल हम देते थे मेरे सामने बैठ करके बनाओ, हम बताएंगे नहीं, लेकिन मेरे सामने बैठ के बताओ, हम हैं यहाँ पे, आपको गड़बड़ है आप पूछो हमसे, आके पूछो, हम नहीं बताएंगे, आप पूछोगे तब हम बताएंगे। तो जो कोई आकर के पूछता है, सब अलग अलग बना रहे हैं अपना अपना, वो हमने तो तरह तरह के सेशंस हमने दिन भर किए, ब्रेकफास्ट से लेकर के डिनर तक। और डिनर पे हम उनको एक होमवर्क तक पकड़ा देते थे, उसमें 5-6 सवाल होते थे, और आप जो मैं बनाता था और जो उनको होमवर्क मिलता था, सारे सवाल सिर्फ और सिर्फ जेईई एडवांस के पेपर से उठाए होते थे, एक भी सवाल कहीं और से नहीं लिया गया था, ना कॉन्सेप्ट ऑफ फिजिक्स से, ना और किसी सवाल से, ना और किसी सवाल से। बेसिक्स भी अगर मेरे को उनको बताना है तो भी जेईई एडवांस के ही प्रॉब्लम से हम बताएंगे। और वो होमवर्क के अंदर में 5-6 सवाल हम दे देते थे किसी किसी साल के आए हुए, और वो होमवर्क बना करके उनको दूसरे दिन सवेरे ब्रेकफास्ट पे हमें सबमिट करना होता था, और वो करते थे, वो सारे के सारे लोग करते थे, सबसे सब कुछ नहीं होता था। लेकिन ये जो एक था कि हम तो भाई जेईई का सवाल है, अरे हम कैसे अटेम्प्ट कर सकते हैं, नहीं, लोगों ने सबने अटेम्प्ट किए, और फिर हम उसका डिस्कशन करते थे। जब हमारे पास आ जाता था तो उसको स्टडी करके फिर हम उसका डिस्कशन करते थे। 7 दिन का कैंप इतना बढ़िया हुआ हमारा कि हमें लगा ये एक्सपेरिमेंट बिल्कुल ठीक है। फिर हमने दूसरा एक्सपेरिमेंट मई में किया, मई 2024 में, सेम रिजल्ट। फिर हमने वो इंसा को बोला, इंडियन नेशनल साइंस एकेडमी को, कि आप इसमें हमसे कोलैबोरेट करो और आप अपने सेंटर पे करवाओ और उसके पैसे वैसे भी आप ही भरो। तो इंसा ने ये वो जो है ना इंटरनेशनल केमिकल सोसाइटी ICS, उसको पकड़ा, उससे स्पॉन्सर करवाया, और हमारे रहने का और खाने पीने का खर्चा वहाँ से हुआ। इंसा के प्रांगण के अंदर में हमने अभी दिसंबर 27 से शुरू करके और 2 जनवरी तक ये कैंप किया है, फिर से जेईई का तीसरा। ये सबसे बढ़िया कैंप हुआ है, सबसे बढ़िया। लोग 7वें दिन इतने जोश खरोश में थे, उन्होंने इतने रील बनाए, ये किए, सबने हिप हिप फुट रहे, इतना सारा किया। वो ICS की जो वहाँ आई थी उनकी अध्यक्षा वैलिडेक्टरी फंक्शन में, वो देख करके बोली 7वें दिन भी इतना लोगों में जोश खरोश है, 7 दिन कैंप करने के बाद भी। ये सोल्यूशन है, जॉयफुली लर्न करना है, और स्कूल के ही टीचर्स अगर लर्न करा दे तो उससे अच्छी बात नहीं हो सकती। तो वो ये मुहिम है, ये एक्सपेरिमेंट है, और IITs के आप लोग हैं, आपके बहुत अच्छे अच्छे संपर्क होते हैं, ये होते हैं, वो होते हैं, आउटरीच के आपके तमाम प्रोग्राम्स होते हैं, इसको स्केल अप करना है, और केमिस्ट्री और बायोलॉजी भी लेके आना है, मैथमेटिक्स को भी लेके आना है। हम तो फिजिक्स कर सकते हैं, बाकी तीनों चीज़ हम नहीं कर सकते हैं, वो भी ले करके आना है। अपने स्कूल के टीचर्स को ही हम एम्पावर करना है, ताकि ये जी के जंजाल से सबको बचाया जा सके। थैंक यू वेरी मच।
Thank you so much, sir. So now I request Professor Raghunath Sahu, sir, to please present a memento to our respected guest.
So maybe before that, we can take a couple of questions, preferably from school students. Because one question, so one selfie, right? Otherwise, no pictures. Questions are important, eh? They have raised their hands. Yeah, so then mic देना पड़ेगा ना. हाँ.
Hello.
Yeah, please go ahead.
Sir, my question is that what do you think about the future of AI? Like it is comparable with human intelligence or not?
So the question is on future of AI.
Yeah, or it is comparable with, or maybe will comparable with human intelligence or not?
Yeah, you see, nothing can exceed human intelligence, right? So AI is a tool to my understanding, you know. So Professor Verma told me to reply to this. So, you know, it is a tool. So the way you use, the way you master it, so that matters.
Okay, sir.
It was there, it will be there also, nothing new. But, you know.
Okay. And my second question from Professor Verma is that recently you launched a book on calculus. So can you just brief to us on that?
Okay. So calculus is something which puzzles our students, because in mathematics syllabus generally a very little calculus is touched at the end of class 11, and then in class 12 we have more calculus. Whereas physics people from the very first lecture, when they start with those x equal to ut plus half at square, etc., they start using calculus. So it's a big gap. So that prompted us. In fact, my brother started writing this book, but could not complete it. So we completed that and we published it. So we have tried to do this calculus. Once again, very joyful learning. That is our principle, basic guiding principle for all activities. So the calculus book is also written in that fashion. You will see a lot of cartoons in that.
Yeah.
Some helicopter is going, and then people are standing on the, and then the food packet is being dropped, or some bank is there and someone is going and asking for the money and interest rate is written. Some magician is taking out from the cap varieties of things, and the audience is there and they are clapping. So you will see many such things where the whole learning experience is made in such a way that people are not serious and stressed. At the same time, the whole subject which is given, it is in utmost depth. And in fact, during this writing, 3 years I took, I learned so many new things in calculus which I did not know. So we have discussed all those things in detail, in different fashions, in different sections. And then at the end we have 2 chapters, guest chapters, written by stalwarts.
Okay.
And that is on calculus as it was developed in India in ancient times. From Aryabhat to that Kerala School of Mathematics, we have done a lot of calculus. We have developed calculus, the techniques of calculus, the applications of calculus in India. And I'm not expert on that. So I asked 2 of my friends, very competent friends. So they have written 2 guest chapters on Indian calculus as it was developed from time. So this book is very close to my heart, not only because I put 3 years in it, but also because finally when it has come out, it has very rich content and very joyfully written. So that's about this calculus.
Thank you, sir.
Hello, sir. First of all, it was a very wonderful talk. Sir, my question is like, what is the benefit of asking the big questions? I mean, one day I was thinking, like, I am doing my research on galaxies, okay. So I'm observing something which is like millions of light years away, and I thought for some time, and it doesn't impact a normal human being very much. And just like he's working on satellite imaging, it directly impacts us. So how is my work, like, you can understand, like, I thought my work is not very relevant as compared to him, because his work is directly impacting humanity,
Correct.
while mine is
Correct,
not.
correct. So switch over. You go to that field.
No. I mean, then I thought some more, and then I concluded that since the beginning of humanity, humans are very curious creatures.
Correct.
Like, we are always asking how does all this thing. So we can classify the things in 2 broad categories, one for our own satisfaction and one for our needs. So I want to know your take on this.
Okay, so that was in a lighter vein that you switch. You don't switch. It's a very beautiful area to work. Okay. Now, better. Now, tell me, if an artist has made a beautiful painting which only he understands and no one else, ठीक है ना? वो जब वो exhibitions वगैरह लगाते हैं, art gallery वगैरह, और मैं घूमता हूँ, मुझे कुछ पता नहीं चलता है क्या है, सब एक ही जैसे लगते हैं, लाल पीले नीले वो ब्रश चले होते हैं. I'm not able to make out कि क्या है इसके अंदर खास बात की वही इसको प्रदर्शनी लगी है. Does it impact the society? उसका क्या इम्पैक्ट है सोसाइटी के ऊपर, उसने ड्राइंग बनाया नहीं बनाया, मूर्ति बनाया नहीं बनाया, क्या इम्पैक्ट है उसके, ओके। बट क्या है ना कि इफ यू आर डीपली इन्वॉल्व इन ए क्वेरी, आप कम से कम खराब काम नहीं करोगे, है ना। आपका जो माइंड है वो माइंड हमेशा एक हायर प्लेन पे काम कर रहा है, और आपका फील्ड तो बहुत अच्छा है, बिकॉज यूर फील्ड विल टेल ह्यूमंस कि तुम क्या बातें करते हो, हम इतने बड़े उतने बड़े, कुछ नहीं हो तुम कुछ नहीं हो, हम तो गैलेक्सीज की बात करते हैं, ये क्या अर्थवर्थ क्या होती है, 6000 किलोमीटर क्या होते हैं, और तुम क्या होते हो, 6 फुट के आदमी। तो वो जो एक अहंकार मनुष्य को होता है ना, वो अहंकार का नाश हो जाता है, एंड पर्सन्स बिकम प्योर। तो ये आप इसको ऐसे भी सोच सकते हो, इट्स काइंड ऑफ एन आर्ट, इट्स काइंड ऑफ ए फाइन आर्ट, कि आपने एक ऐसे मॉडल तैयार किया, उसने एक पेंटिंग तैयार किया, उसने एक स्कल्पचर तैयार किया, आपने एक मॉडल तैयार किया, और वो मॉडल जो है वो कुछ ना कुछ बड़ा है, और आप उसके अंदर डीपली इन्वॉल्व हो, आपको मजा आ रहा है, अरे वाह कितना अच्छा, अरे अच्छा ऐसा हो गया, 2.73 केल्विन का मिल गया रेडिएशन, क्या बात है। किसी को कोई इंपैक्ट नहीं पड़ा, मिलना नहीं भी मिलता तो भी दुनिया वैसी ही चल रही थी। कौन सी खेती सुधर गई उससे, कौन सी खेती उससे सुधर गई, क्या हो गया, राइट। 2.73 से ना कोई मेडिकल इक्विपमेंट बना ना कुछ और। बट वो जो एक इंटेलेक्ट है वो जब होता है तो आदमी का जीवन खुद का एक प्रेरणा बन जाता है। दूसरे लोग भी देखते हैं कि अच्छा ये आदमी को कोई मतलब नहीं है कि टी शर्ट अच्छी है खराब है, मेरे पास में क्या है क्या नहीं है, क्रीज बढ़िया है कि नहीं, हमारे घर में वॉशिंग मशीन है कि नहीं, हमारे घर में सोफा है कि नहीं, आप उन सब से ऊपर उठते हो, है ना। तो ये है, एंड यू नेवर नो, पता नहीं भविष्य के अंदर में कभी कभी इम्पैक्ट पड़ भी जाया करते हैं। जब डिस्कवरीज होती हैं तो उस समय पता नहीं होता है, लेकिन कभी कभी पढ़ भी जाया करते हैं। लेकिन ऐसा नहीं है कि वो पढ़ेगा तभी वो इंपॉर्टेंट है, नहीं पढ़ेगा तब भी वो इंपॉर्टेंट। इंटेलेक्ट, और इंटेलेक्ट ऐसी चीज है, वो क्या डीएनए आरएनए की बात कर रहे थे ना, इंटेलेक्ट ऐसी चीज है कि अगर आपने वो इंटेलेक्ट का विकास किया है तो फिर वो शायद अगले जनरेशन में भी पास ऑन होगा, और आगे आने वाले लोग नहीं भी इस गैलेक्सीज में रिसर्च करेंगे तो भी उनका इंटेलेक्ट चूंकि बढ़ा हुआ है तो दे विल बी यूजफुल फॉर द सोसाइटी, ओके। तो नथिंग टू वरी अबाउट। हमने भी जब अपने रिसर्च किए थे तो हमने यही सब सवाल अपने से पूछे थे कि ये हाइपर फाइन इंटरेक्शन की एनर्जी 2.35 है कि 2.36 है, इसको निकालने से किसको क्या फायदा होने वाला है। जब हम वो मॉसबार इफेक्ट से और इतनी इतनी छोटी छोटी 10⁻⁸ EV की एक्यूरेसी से नापा करते थे एनर्जी, और खुश होते थे, देखो इतनी एक्यूरेसी से हम नाप पा रहे हैं अपने इंस्ट्रूमेंट से, तो खुश तो होते थे, लेकिन ये भी सवाल पूछते थे कि इससे किसको क्या फर्क पड़ने वाला है। तो वो है, लेकिन हमने तो एंजॉय किया ना, हमें तो मजे आ गए ना। और वो हेवी आयंस हमने जब उस वक्त उसके एक्सपेरिमेंट्स कर रहे थे तो हमारे जो स्टूडेंट थे वो ग्रेफाइट के ऊपर प्रोटॉन्स बम्बार्ड करके उसमें मैग्नेटिज्म पैदा करना चाह रहे थे डिफॉर्मेशन से, वो हो नहीं रहा था। तो हमने उनको कहा कि अच्छा कार्बन है ये, उधर से हाइड्रोजन ला रहे हो, और कार्बन और हाइड्रोजन की तो इतनी अच्छी पटती है, वो तो तुरंत मॉलिक्यूलर ये वो बना बनू लेंगे, तो कहाँ का ग्रेफाइट और कहाँ का मैग्नेटिज्म। तुम ऐसे करो, कार्बन को कार्बन से ही बम्बार्ड कर दो, ग्रेफाइट को कार्बन आयंस लाओ और कार्बन आयन से बम्बार्ड करो, तो फिर उनको कोई ऐसा कुछ नया करने का मिलेगा नहीं, तो फिर वो ग्रेफाइट ही रहेगा, सभी मिलकर ग्रेफाइट ही रहेगा, तो देखना शायद होगा। उसने किया साहब, निकल में जितना मैग्नेटिज्म होता है, निकल में जितना मैग्नेटाइजेशन होता है, उतना मैग्नेटाइजेशन हमें ग्रेफाइट में मिला। हाँ, इतनी खुशी हुई हमें कि ये जरा सी इंसाइट कि प्रोटॉन से नहीं करके हमने उसको कार्बन से बम्बार्ड किया ताकि यहाँ कोई केमिकल बॉन्डिंग वगैरह का चक्कर बीच में ना फंस जाए, एंड दैट गेव मी दिस काइंड ऑफ मैग्नेटिज्म। उस पेपर की भी बड़ी चर्चा रही, और जिस जर्नल में छपा उसने फ्रंट पेज के ऊपर हमारे वाले फोटो वोटो डाली, ये किया वो किया। हमें पता था कि इसका कभी उपयोग हो भी सकता है, अगर ग्रेफाइट से मैग्नेट बनाने की कला विकसित हो गई तो हो भी सकता है, नहीं भी हो सकता है, मैं तो नहीं करने वाला हूँ, मेरा उसके अंदर में मन नहीं है, मुझे तो अपने प्रयोग खुद के करने हैं। तो बट वो जो एक खुशी है, कैसे भी करके खुशी मुझे मिल रही है, मेरा इंटेलेक्ट का विकास हो रहा है, दिस इटसेल्फ इज एनफ। ओके,
Maybe the last question. There are several questions.
तो सर मेरा क्वेश्चन ये था कि आपने बताया कि आप न्यूक्लियर फिजिक्स में मतलब बहुत अच्छा महारथी है, एक तरह से बोल सकते हैं, और मैं भी एस्ट्रोनॉमी पढ़ता हूँ, तो मतलब एस्ट्रोफिजिक्स। तो मेरे पास एक क्वेश्चन था जिसका आंसर मुझे नहीं पता था। तो जैसे हर स्टार्स होते हैं तो उनकी एक लिमिट होती है कि वो उससे ज़्यादा मास को अपने अंदर नहीं रख सकते, नहीं तो श्रिंक करके ब्लैक होल बन जाएंगे, या तो सुपरनोवा बन जाएंगे, या नेबुलास बना लेंगे। तो मतलब हर स्टार का वैसे ही फ्यूजन लिमिट होता है कि वो आयरन के मतलब एटम तक फ्यूज कर सकते हैं, है ना, बाकी एटम्स को आयरन तक फ्यूज कर सकते हैं। पर उसके बाद के एटम, जैसे अपने पास 108 एटम्स हैं अभी, एलिमेंट्स के वो हैं, तो उसके बाद के एटम्स कैसे बने?
ओके, ठीक। हाँ, मुझे थोड़ा थोड़ा मालूम है, बता देता हूँ। कुछ गलत बताऊंगा तो आप सही कर देना। होता क्या है कि जो आपने सुपरनोवा की बात कही, और वो जो होता है विस्फोट, तो बहुत थोड़े समय के अंदर में बहुत सारा प्रेशर जनरेट होता है, बहुत सारा टेम्परेचर जनरेट होता है, और उस प्रेशर और उस टेम्परेचर के चक्कर में जो वो इंडोथर्मिक रिएक्शन है, एनर्जेटिकली पॉसिबल नहीं है, लेकिन बाहर से तो हम एनर्जी दे रहे हैं ना उसको, तो वो पॉसिबल हो जाता है ना, राइट? जैसे अपना फोटोसिंथेसिस है, कार्बन डाइऑक्साइड और पानी मिलकर ग्लूकोज बनाते हैं, नहीं बन सकता है, नहीं बन सकता है। ग्लूकोज के मॉलिक्यूल की जो रचना है, उसकी जो एनर्जी है अपनी, वो ज्यादा है, और कार्बन डाइऑक्साइड की और पानी की जो मॉलिक्यूल्स की रचना है, वो एनर्जी कम है। बट सूरज से चूंकि उसको एक्स्ट्रा एनर्जी मिल जा रही है, तो ये भी संभव हो जा रहा है, फोटोसिंथेसिस हो जा रही है। उसी प्रकार से आयरन के आगे नहीं फ्यूज कर सकता है, का मतलब है कि अगर आप कराने की कोशिश करोगे तो जो प्रोडक्ट न्यूक्लियस बनेगा, उसकी जो अपनी एनर्जी है, मास एनर्जी, वो अधिक है और ये कम है। जो कंस्टिट्यूएंट है वो कम है मिल करके, और वो अधिक है, इसलिए वो नहीं जा सकता है। सबसे टाइटली बाउंड है वो आयरन। लेकिन अगर बाहर से एनर्जी पंप कर दूं तो ले जा सकता हूं ना। तो वो जो सुपरनोवा का विस्फोट होता है, उसके अंदर में इतना प्रेशर और टेम्परेचर और ये और वो जनरेट होता है कि उससे वो एक्स्ट्रा एनर्जी मिलके उतने से समय के अंदर में बाद वाले सारे एलिमेंट खड़ 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 एक झोंक के अंदर में बन जाते हैं। वही फिर हमें दोबारा जब वो डिस्पर्स हो जाते हैं, फिर कभी इकट्ठे होते हैं, कोई नया स्टार बनता है, कोई नया प्लेनेट बनता है, तो फिर उसके अंदर में वो चीज़ें आती हैं। ठीक, ओके।
Okay, thank you. So let's end the program here. We are getting late also. Let's give a big hand. In fact, from IIT Indore, we are really thankful to you, sir, for coming to IIT Indore and for the really exciting session and educating our next generation, which way, joyful learning and, thinking of different situation, from situational learning and all that. So I think our science education has a bright future with this next generation. Thank you so much.